I never remember to record. And then people will ask, did you record it? And I always end up having to say, oh, damn it, I forgot. So, all right. Okay, so here we go. Now that everybody knows everybody, a little bit about me. My name is Scott. I got my ham license when I was 15 back in Maryland. I was always the engineering kid who didn't know he was an engineer exactly, although I kind of figured that that's what I was going to go into. I was always messing around with electronics, and I took, like when I had a chance, I took a class in industrial arts because I wanted to do industrial arts and learn how things worked and how to build stuff. And so when the chance came for me to take a ham radio class, because my dad told me there was a ham radio class being taught by the club at his work, I said, what is ham radio and why would I want to do it? So he dragged me over to a friend's house back in the mid 1980s, and he had a full size, if anybody knows what a Collins S line is, he had a Collins S line set up on his desk, which was glowing in the dark. And we made a contact from Maryland to Kentucky, which, was a fairly long contact, I guess, at the time, it seemed. I know now that it really wasn't that far, considering that, you can talk around the entire world using nothing but radio waves. But at that time, I'm like, yeah, that's pretty cool. Okay. All right. So what do I do? So they signed me up for class. I got my license. I did nothing with it for a couple of years until the time between high school and college, at which time I said, yeah, okay, well, I guess it's time to figure all this stuff out. And so I proceeded to get on the air, got my Morse code speed up, started passing exams. I had to pass a 20-word a minute code test to get my extra class license, and then 4 more written exams. So that was when, in the time period that there were 5 written exams to take. So I had 4 more to go. And so after 4 more exams, I had my extra. Then I became a volunteer examiner and started giving exams, became very involved with the University of Maryland Radio Club during that time, and proceeded to be a student member, and then kind of like a graduate adult advisor to the club for many years after that, until I moved out to Oregon. And since I've been in Oregon, I've been active for at least some of the time with the Valley Radio Club here. I'm fairly active with them now. I'm a firm believer in ham radio as a great form of STEM education. We have a local science museum called the Eugene Science Center. It used to be called WizTech. It used to be called the Science Factory. And about 7 years ago, I proposed that we put a station in the museum as a teaching tool. And so that's been operating up until the time that COVID hit, every Saturday during that time period. So I was very happy to be over there and get people on the air and show them what this ham radio thing is. And I'm also a very I can't say I'm a serious contester, but contesting is basically radio sport. I really do enjoy that part of it, where you basically try to make as many contacts in as many places in a fixed period of time as possible. I'm also what they call a paper chaser. So I do some of the emergency communication stuff, but for me, the exposure, the interest has always been more from the science and engineering side of things. And I tend to teach the class that way as well. So that gives you hopefully a lot of understanding as to exactly why things work the way they do. And once you know why things work the way they do, it makes a lot more sense, I think. All those things that, like you said, you had to study for the exam and you passed the exam, but you're not really sure why. So by education and training, I have a master's in electrical engineering with a focus on electrophysics and communications. And by employment, I'm a factory automation engineer. So electronics and controls and electrical stuff, power distribution. So things like that, a lot of factory automation. So if you've ever seen something like how it's made and they show a picture of the inside of a factory and things moving from place to place and machines working, that's the stuff that I do. So for me, this is fun. So that's why I'm here. And there's also a long-standing tradition in ham radio called Elmering. Elmering basically is teaching others, so you can be an Elmer. Anybody can be an Elmer. I've always enjoyed being an Elmer to other people. Part of it is the fact that I like to talk, I guess. And part of it is the fact that I feel like there are a lot of things that I actually know that a lot of people maybe don't. And so I do have something to offer. Not to mention, just, having opinions to offer as well. But so anyway, that's why I'm here. And I thank you all for being here. So here we go. Does anyone have any questions before we start? Okay, I don't hear anything, so let's go. All right, so given the fact that we have this thing called amateur radio, how in the world did we even get here? So the first thing I'm going to do is bring up an explanation of how it is that we got here. And I do use a lot of like multimedia type resources. And the first of which we're going to bring up is Arrl. So Arrl is the American Radio Relay League. It is the member organization of ham radio operators in the United States. It's got about 160,000 members at this time of these roughly 750,000 licensees in the United States. So the FCC governs who gets a license and the fact that, they're qualified to operate. And they also handle all the legal stuff. And the ARRL is the member organization that represents us in front of Congress and things like that. So the big part of ham radio, the thing that allows us to exist is this thing called Part 97. So Part 97 is the rules and regulations of the Code of Federal Regulations that the FCC has laid out. So right here, notice we have this thing called basis and purpose. These are the 5 things that basically are amateur radio and say what we are supposed to do and what we're allowed to do. So number 1, recognition and enhancement of the value of the amateur service to the public as a voluntary non-commercial communication service, which basically means we can't make any money doing what we do. This is not something that you do in order to, further you can use it to further your job, but you can't use it to earn money. So if you have a business and you're out in the field doing something, you need to be using a business band radio. In other words, you can't use ham radio to conduct business. Continuation of the extension of the amateur's proven ability to contribute to the advancement of the radio art. Believe it or not, we'll get to this. There's a lot of radio, even in places you don't think of today. Encouragement and improvement of the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. People might think, oh, well, we've developed everything that we can, Masood, right? We've developed everything we can with regard to communications, and there's nothing left to do. And I believe that could not be further from the truth these days. Expansion of the existing reservoir within the amateur service of trained operators, technicians, and electronics experts. There are a lot of people, as technology has become smaller and smaller, who will, for instance, use a cell phone and not have a clue as to what is inside it. It is a black box, right? Getting into the world where things are a black box, it's kind of a dangerous thing, because then it's a black box and you have absolutely no idea what's inside it. Well, how did it get there? What are the fundamentals that allow it to work? I liken ham radio as basically the ability to take this cell phone or an FRS radio or a ham radio that runs the digital mobile radio and understand what's going on underneath the hood, and then actually be able to play with it and actually build your own car, for instance, except that it's on the radio. And finally, continuation and extension of the amateur's unique ability to enhance international goodwill. So in the world, over the 110 years that ham radio has existed, there have been a lot of things that have gone on in the world that have been political. Ham radio is one of those things that has always been, and hopefully will continue to always be, apolitical. So just as an interesting story, when I was right out of college and applying for a security clearance, I was asked on my US government security clearance form, do you know anybody or have interactions with anyone from a country that the United States deems to be hostile? And they said examples: Eastern Europe, Soviet bloc. So I had to list, okay, well, I've got, people in Hungary and Romania, East Germany, Czechoslovakia, Soviet Union. And the question was asked, well, how do you know all these people? And I said, ham radio. And they said, oh, you're fine. In other words, this has always been, viewed as a way for people to sort of bridge the gaps between political divides around the world. So it's and because of that, it's a chance for people to, make friends in countries that they wouldn't necessarily make friends in or wouldn't be allowed to. All right, so that is why we exist. We've existed as amateur radio for over, like I said, 110 years. And the way we came into existence was that in the late 1800s, there was a lot of experimentation going on with regard to radio waves. What are radio waves? What is this thing called electromagnetics? I mean, how does this stuff even work? So, of course, if there were some unknowns, there would be people who would start experimenting. And they realized, okay, well, if I can make an electromagnetic wave at a given frequency and have a piece of wire and it tends to radiate power, I can pick it up with another one and then I can modulate it and put a signal on it and have communications from point to point. And besides, people have been doing telegraph since the 1840s. So how different could this be, right? I mean, we know that we can turn a telegraph signal on and off and send code back and forth. So he said, okay, well, if we can do that over these radio waves, oh, look at that. We can actually have communications from point to point for over long distances. So people were experimenting at that time. They gave themselves their own identifiers, their own call signs. And it was decided in World War I, well, this could be a really useful thing for the military. So everyone who was a radio experimenter at that time was basically used as part of the military in a military service because communications suddenly became important. And well, after World War I, said, we did all this stuff, all us experimenters, we're doing such a good job here. The military said, okay, but we're going to conscript all these frequencies that we find useful to military service. And that was everything 200 meters and longer, which is really fortunate because, as it turns out, the larger the wavelength that you use, which we'll get to shortly, the larger the antennas you have to use. And also, it turns out that they don't travel all that well around the world. They said these short waves, which is anything shorter than 200 meters in length, which doesn't seem all that short, right? That's why we have this thing called shortwave radio, even though it's really not all that short. We're going to leave those for all you experimenters. And there became known as this thing called a ham, which was basically, depending on the origin story that you believe, a ham is basically a ham-fisted hack. So somebody who doesn't really know what they're doing because they're not professional. So that's who we are. We are the ham-fisted hacks. And so, of course, if somebody calls you that, well, you have to be proud of it. And so we are the ones who started experimenting with those shorter wavelengths that we determined be able to transmit signals all over the planet. And around the 1930s, there became a movement to rein in some of the chaos in call signs and allocate actual call sign prefixes to different countries. So at that time, the United Nations basically said, okay, well, we're going to assign different call sign prefixes to different countries. And in the United States, you have W, N, K, and then AA through AL. And if you're in Britain, you have M or G, or in France, you have F, and any part of the British Empire, your call sign can start with a letter V, which is why Australia is VK, and India is VU, and Anguilla is V2. So, and in Canada, you have Victor Echo, VE, or VA, or VC. So that basically reined in some, some order from the chaos. And that's why we have call signs today that all fit this rule. You may also notice that if you travel internationally, every airplane is also tagged with an identifier from the country in which it's registered. Those also follow the same rules. Those rules were formed at about the same time. All right, so here we go. We are going to start, actually, this is going to sound kind of weird, but if we're following along in the book, does everybody have the book, I hope? All right, it's a free book, and like I said, it's pretty good. It's laid out in a way that I think makes a lot of sense. We're actually going to start on page 24, because this is the one place that I don't agree with how the book is laid out. I think that radio waves have to come first, because it's a fundamental of what we're doing. So the first thing that we do is describe something called a frequency. All right, okay, so let's say, with what frequency do you go to the store? Let's hear an answer from somebody.
Once a week.
How often do you go to the supermarket? With what frequency?
Every week, once a week.
I can't hear anyone.
Every week,
Once
once a week.
month.
Once a week, they say.
Hold on. Okay, here, let's try that again. Okay, with what frequency do you go to the store?
Once a week.
Once a week. Okay.
Once a week.
Every time my wife tells me to.
Yeah, okay. All right, so one time per week. All right, that is a frequency. It is a thing per unit time. So that is a frequency. We'll call that little letter F. One time per week. All right, I actually go to the store more often than that, but that's okay. That's a frequency. If I were to double that, let's say that it was talking about me, I would say that I go to the store roughly 3 times per week, because we tend to run out of things occasionally and I need to go make a short trip. So my frequency has now been increased to 3 times per week, right? So that's all a frequency is. It's a number of things per unit time. And the unit of frequency that we use is named after Heinrich Hertz. So one thing per second is 1 hertz. By definition, that's a thing that happens every second. So let's say that I clap my hands and I do a slow clap. Once per second, what would be the frequency of that clapping?
1
Once per
hertz.
second.
That would be
hertz.
1 hertz. Okay. So if I were to double that and I clap twice a second,
2 hertz.
that would be 2
2
hertz. If I could do it fast enough and do it 1,000 times per second, my hand would be blazingly fast, and my frequency would be 1,000 times per second.
1 kilohertz.
That would be 1 kilohertz, or 1,000 hertz. And now we start moving in, as Masood mentioned. We're going to start using prefixes, and we're going to start using placeholders. So a kilo is 1,000. So that actually is 1 kilohertz. All right. So let's say that I could clap my hands 1,000,000 times a second.
1 megahertz.
That would be 1,000,000, which would be
Megahertz.
that would be big letter M. So that's 1 megahertz or 1 million times per second. So we now have this thing called frequency. Okay, so we are now going to take this frequency, because a frequency is just a unit of something that happens every second. We're going to take this thing called a frequency and we're going to combine it with something else. So let's say that I'm walking down the street and I'm moving at a velocity of 1 meter per second. All right, that is a velocity, right? That's a speed. If I'm walking down the street, that's a velocity because it has because it has direction, but my speed is 1 meter per second. Okay, so let's say that I'm clapping 1 hertz. I'm clapping 1 time per second. Every time I clap, I have moved how much further down the street?
1 meter.
1 meter.
1 meter.
Yeah. Okay. So I have moved 1 meter per second. So every time I clap,
Hmm.
I have now moved 1 meter further. Okay. So if I were to plot this out over time, I could see this being a clap, and this being a clap, and this being a clap. And those are separated by what distance?
1 meter.
1 meter. Yeah.
Lambda.
All right. So those are all, every time I clap, it's 1 meter apart. So if you didn't know what was making it, well, okay, you could say that those claps are now 1 meter apart, right? So that would be a distance of 1 meter each time. Okay. So now what we're going to do is we're going to introduce something called a wave. In particular, this is a crudely drawn sine wave. So a sine wave is, let's say that this is a circle. A sine wave is a plotting of, as we travel around this circle at a given speed, how far away from this axis we are at any given time. So at our starting time, we're right on the 0 line. As we come up to here, we get up to the top. As we get over to here, we're down to the minus. As we get here, or sorry, we get down to the minus, and then we get back to 0. So we have 1, 2, 3, and 4. 1, 2, 3, and 4, and then back to point number 1. And this repeats over and over and over and over. And what's nice is, of course, that a lot of things in the world, a lot of things in the universe are cyclical. A lot of things in the world are spinning. And because they spin, they make nice little patterns that look like circles. So this is actually a very convenient graph. This is known as a sine wave. Okay, so now we now have this thing called electromagnetic energy. Okay, so we have this wave which travels over a certain distance over a period of time. So let's say that it takes 1 second for it to go from here to here. And let's also say that we have something that's moving at 1 meter per second. How much distance will actually be covered in that time? So if we have a time of 1 second and a speed, a velocity of 1 meter per second, we can do some simple math and say 1 second times 1 meter per second, and the seconds cancel out. And how far have we gone?
1 meter.
1 meter. So this distance that is now covered is 1 meter. So if we were to look at this in space, we would actually see that the distance that's covered as that particle goes around and around and around and up and down would actually be 1 meter in distance. This
Is this
is
where
known
we
as,
get the different bands for 1 meter, 2 meter, etc.?
yep. And this is known as a wavelength because this is a wave. That's known as a wave. And the space that it covers is known as a wavelength. But what is important to know with regard to this? What did we have to have? We had to have a frequency, 1 hertz, and we had to have 1 time, and we also had to have this 1 meter per second. So we needed a velocity. So now what we have is we have several things that are now combined. We have a frequency and a wavelength, and we can write this formula. V, which is velocity, is equal to frequency
F lambda.
times wavelength, or V equals F lambda. So for those of you who are taking college physics, and actually for all of us too, velocity, because we're actually looking at, let's say we're looking at the speed of sound. Let's say we're actually looking at, if you've been to a baseball game and you've been unlucky or lucky enough to sit way out in the bleachers and you see a ball get hit. What do you notice about it? Does the crack of the bat, does the crack of the bat line up with what you see?
There's a time delay.
No.
There's a time delay. That's right. And the
Time
reason
delay.
there's a time delay is that this travels at about 300 meters per second. That's the speed of sound, roughly, at the surface of the Earth. So if we were to take a look at the speed of sound, we have a frequency and we have a wavelength. Well, there's a delay there. So if we were to say that, okay, we have a frequency, the crack of the bat is 1,000 hertz, more of a ping sound, what would the wavelength be? Okay, well, we could actually just do the math, move a few things around, divide both sides by letter F, and find, excuse me, our Greek letter lambda in meters is equal to V in meters per second divided by our frequency in things per second. Okay, notice that the seconds cancel out here. And so now we have V divided by F, and our units is now meters. And we'll call this a cycle because it's 1 full cycle of a wave as it travels. So what is our wavelength? It's now 300 divided by 1,000, 0.3 meters. Okay, so if we were to trace it out, we would see that as the crack of the bat, the sound of the crack of the bat travels, we would have wave fronts that would be 0.3 meters apart as it travels through space. So we would actually have compression and rarefaction of air. Now, sound waves are very different from this other thing that we're working with, because sound waves travel at the speed of, everyone?
Sound.
Sound. Okay.
And
Now we're going to look at something else, which is this. Anybody know what this thing is called?
Spectrum of frequencies.
Right. This is and in particular, this is the electromagnetic spectrum. So the electromagnetic spectrum is made of waves all the way from frequency 0 up to frequency infinity. And all the way from at the left, wavelength infinity, all the way up to wavelength essentially 0. So what we're just looking at here is, notice that our frequency starts on the left end at 30 kilohertz, 30,000. The next one is 300 kilohertz, which is 10 times as big. The next one is 3 mega, which is 3 million. The next one is 30 mega, which is 30 million. The next one, 300 mega, which is 300 million. So each step is 10 times greater than the previous one. So this is a logarithmic scale, base 10 logarithmic scale. And within each of these areas, these are each known as a certain, with a certain moniker. So from 3 to 30 megahertz, this is known as HF, which is high frequency, because way back in the day, HF was assumed by the military to be really high frequency. Well, because the military got those really lower frequencies. So HF is high frequency and it's 3 to 30 megahertz. Well, as we figured out how to build electronics that could actually make higher frequencies than that, well, it turns out there's a lot of frequencies higher than that. The next group is 30 to 300, which is VHF, or very high frequency. The next group is 300 to 3000 megahertz, which is ultra high frequency. And then there's EHF and SHF, and which is extra high frequency, and super high frequency above that, because it turned out you actually had to name them something. Right around the 3 gigahertz mark is this transition where we go from classical radio to this thing called microwave. And micro because they're really small. And can anybody guess where you might find something called a microwave?
In the kitchen.
In the kitchen. Okay. And why is it actually called a microwave oven?
Because of the frequency,
So-
wavelength of the frequencies they are using.
Yep. And in fact, the microwave oven operates at about 2.4 gigahertz. And this frequency is chosen because that is approximately the resonant frequency of water. So by shaking the water molecules back and forth using radio energy, what you do is you add heat to them. Motion is heat, and that causes you to heat up whatever you're trying to cook.
Content.
Yep. Okay, so now I want everybody to notice also, we have this thing all the way at the right end of the spectrum, which starts with red and ends with purple. What is that?
The visible light spectrum.
That is the visible light spectrum. So what is to the left of visible light? To the red?
Infrared.
Infrared. That's right. Infrared, we feel as heat. And to the right of the purple, the right of violet,
Ultraviolet.
see ultraviolet, which is a shorter wavelength than violet. And that serves to it has more energy than violet. As you go to the right, you get more and more energy, which is why all the way to the right of that, you have this thing called X-rays. They were mysterious because they could pass right through you. Well, as it turns out, radio and microwaves and infrared energy and all the colors and ultraviolet and X-rays are all part of the same thing. They're all part of this thing called the electromagnetic spectrum. And we think of it as light, right? So the first thing I want to ask is, if you look at, let's say you look at my coffee thing here, what color would you say this is?
Orange.
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 Why is it orange?
Because it's reflecting that orange color.
Yeah, and in
because of
particular,
the frequency.
there's a particular wavelength and frequency
Yes.
of light.
The atoms of the product that's made of.
Yep. They are reflecting this particular color. That is the same reason why this is yellow.
Yeah.
It's reflecting a different wavelength. The other question is, why do we know that one is orange and one is yellow and this is green? Why do we know the difference?
Because of the radiation emitted by the electrons when they jump from one orbit to the other, that spectrum is different.
But that's actually not, but if you think about it, why do we know the difference?
So they told us in small the colors, the name of the colors.
Right. Well, they taught us the name of the colors, but why can we even tell the difference?
Because we can see it.
Because we can see it. Our eyes are specifically designed to pick up the differences in colors. Our eyes are very good at picking up colors. Now, if we look at this map again, what do we see? How much bigger is the electromagnetic spectrum than the colors?
Very big.
It's
very
huge,
big.
right?
Huge.
Okay,
Yeah.
so what is the only difference between radio waves and light waves?
Their frequency,
Their frequency and wavelength. That's it.
wavelength.
In other words, if we could see radio waves,
Mhm.
we could see them just like we do light, just like we do color. But we're not designed to do that. So what do we have to build in order to be able to see these things? Noel?
Sensors, radios, sensors,
Radios, sensors,
antenna, any material that can feel and react to those waves.
Yep. So basically, if you think about it, the only reason that we can't see those things is because we're not designed to. So what we've done is created these machines, right? Essentially sensors that are able to pick up these different wavelengths and turn them into some format that we can understand. You know, in some cases that might be an infrared camera. We can't see infrared, but it's there. We know it's there. We build a camera that can see at those particular wavelengths and frequencies and convert them to a false color image that we then know what to do with. The same way with radio waves. I mean, we're on the radio all the time. This phone has 4 different radios in it, 4 different antennas operating at 4 different frequencies. How does it know which one to pick up? Because we built it that way. And not only did we build it that way, we can also go the other direction, the same way that we can actually make a light that puts out electromagnetic energy at a given frequency. So we can say, oh, this is a warm white light. This is a cool white light. They have different color spectra that make them look a different way. We can make a radio transmitter that puts out energy at a particular frequency so that somebody else can see it on the other end. All right, so that is what we're here to do. So that being said, here is our first thing. How fast do radio waves travel through space?
Speed of light.
Speed of light, which is the letter C, which is roughly 3 times 10 to the 8th meters per second, or 300,000,000 meters per second, or roughly 7 times around the Earth per second.
Mm.
Or if we were to look at coming from the sun, 8 light minutes.
Yeah.
It takes roughly 8 minutes for light to get here from the sun.
Yeah.
So, okay, so given this fact that radio waves travel at the speed of light, and the speed of light is our new velocity. Velocity is equal to C equals 3 times 10 to the 8th meters per second. How about if we have now a velocity zipping along and we have a frequency of 1 hertz? We can write our formula again. V is equal to F times lambda. But in this case, we're going to use the letter C. C is equal to F lambda. And we're going to rearrange it. We have our velocity. We have our frequency. So what's our wavelength? Is equal to 300,000,000 divided by 1. What would our wavelength be?
3 into 10 to the power 8 meters.
Right. So 300 million meters.
Meter.
That's a really long wavelength, isn't it?
Yeah.
Everyone, what do you think? 300 million meters long.
Oh, yeah.
So we can't really do a whole lot with that. It's not terribly practical because for the most part, antennas that we build have to be at least a quarter wavelength long. So if we had an antenna, if we had a wave that was 300 million meters long, the antenna would be 75 million
Meter.
meters long. Or 75,000 kilometers in length. That would be a minimal antenna for us, or about 40,000 miles long, which is bigger than the Earth's diameter by quite a lot, right? So this is not a practical wavelength to use. So let's pick something that's a little more practical. Let's take a frequency of 1 million. Let's go with 1,000 hertz. Okay. So we have our formula again, C equals F times lambda. And I'm going to write up here something that's a little bit helpful, C and F and lambda in a circle. All right.
Yeah.
And we know that C is 300 million. All right. And we have our frequency in hertz and our wavelength in meters. Well, this is still a really big number. So what we're going to do is we're going to knock out 6 zeros. So this now becomes 300. And we're going to put a placeholder here, which is in megahertz.
Megahertz.
All right. So we're actually going to pick 1 megahertz, 1 million hertz. That's something to work with. So now what we have is we're going to plug this into our frequency, and we have 300 million.
Over 1 million.
The way that this works is actually we conveniently say we don't know this one, so we're going to cover that up. And now we have 300 million divided by our frequency.
Million.
And now we have these cancel and these cancel, and we have 300 meters long, right? Which is about 1,000 feet. Okay, so we're starting to get into the realm of being useful, because if we have something that's a quarter wave long at 1,000 feet, that's a quarter wave, that's about 250 feet. That's actually something that we can build. It's still pretty big, takes up a lot of space, but it's something that we can build. And so now if we were to pick something, let's say even a higher frequency instead of that, let's go with a frequency of 10 million.
Megahertz. 10 megahertz.
Right? So let's go with 10 million, 10 megahertz.
So quarter lambda will be 25.
Right. So then we have okay, so we're going to erase this, and we have 300 million divided by 10 million. All right, somebody give me the answer. That would be 30 meters. That's about 100 feet. We can definitely work with that, right? 100 foot long wavelength. We can build a quarter wave. That's 25 feet. That is definitely doable. A half wave is 50 feet. So we can work with this frequency very well, I think, right? And it turns out now, okay, well, what's our wavelength? Our wavelength is, as we just calculated, 30 meters. So a 10 megahertz frequency translates to a 30 meter wavelength. So as something travels through space, as electromagnetic energy travels through space at a frequency oscillating up and down, every time it goes through one full cycle, it covers a distance of 30 meters. And this is actually really important because this feeds into how we build antennas. An antenna is basically, it becomes our mouth and our ears. So this is going to be really important. Okay, so let's see what, okay, so now we're looking at the book. What type of wave carries radio signals between transmitting and receiving stations? That would be known as electromagnetic wave. An electromagnetic wave has two components to it. As it moves this way through space, you have in this plane, because this is actually three-dimensional. And then in the vertical direction, you have this. I'll finish it out. There we go. Okay, so this is actually a three-dimensional thing. This follows what's known as the right-hand rule. If everybody holds up your right hand and you take your thumb and your index finger, you'll notice that those are perpendicular to each other, right? Okay, then if you take your middle finger and stick it straight out, you will see that each of those fingers, each of your three fingers is perpendicular to both of the others, right? So what you have created is basically an XYZ space where this is your X, this is your Y, and this is your Z. So if you have one going this way and one going this way, your result is the middle finger. So if you have your electric field and your magnetic field, this is the direction, the middle finger, that the energy is traveling. This is known as the pointing vector. And so let's see, if I look at this and I say E cross H, so the E field in this case would be my red. E cross H is Z, or is S. So the direction of energy flow would be this direction. And this would be my electric field. And this would be my magnetic field. So basically what this means is that as electromagnetic energy travels through space, you have electric fields and magnetic fields that travel along with it, but that are perpendicular to the direction that it's moving. But what's important is that the wavelengths are exactly what you think they would be in space. So if you have a frequency of 30 megahertz, this translates by our formula to 10 meters. If you were to be able to measure the distance between this point and this point, that would be 10 meters long. Again, this is very important when it comes to designing and building antennas that become our mouth and our ears for moving energy back and forth. Okay, so the two components of the radio wave are the electric and magnetic fields, because it's electromagnetic energy. How fast does it travel through space?
Speed of light.
Speed of light. Okay, and the speed of light is about what?
300 million meters a second.
300 million meters a second. And the distance that it covers as it travels?
10 meters.
The distance, well, what's it known as? The distance that it
Wavelength.
covers is called a
Wavelength.
wavelength, because this is a
Wavelength.
wave and the distance covered is a wavelength.
I got a question. If
Yes.
it's probably getting ahead, but if I don't fill this hole now, I probably won't understand it later.
Go for it.
If you rotate the polarization of the antenna, won't the magnetic field be the other way,
Yes,
horizontal,
it will. Yes, it
and
will.
the electronic will be vertical?
Mhm.
Okay.
Yes, it will. And we're going to get to polarization a little later. But yes, exactly. The polarization is designed as the direction that the E field is oscillating, the electric field. And yes, if your polarization is crossed, you expect it to be this way, and it's actually this way, you will basically get very little signal received or transmitted. You'll get very little energy transfer. Okay, so very important. We're going to draw this graph, or this little formula, 300 and F in megahertz and lambda in meters. And I keep using this circle over and over. So basically what this means is that 300 is equal to F times lambda. If you don't know one of them, what you do is you cover it up, and then you have this divisor bar, and you can say 300 divided by frequency. So that's a what I found to be a very convenient way to do the algebra for you in case you're not particularly great with algebra. So what happens to a radio wave if its frequency goes up? What happens to its wavelength?
It's shorter.
It gets shorter. So as the frequency gets higher, the wavelength gets shorter because the math says so. How do we identify frequency bands? We conveniently, instead of saying
By the wavelength.
by the wavelength. So instead of saying, for instance, here's the band plan. So
Oh,
these
good.
are a lot of bands that we have available to us. Notice that we have 18.068 to 18.168. We call this the 17-meter band.
So where can we get this graphic?
It's part of it's actually included in the zip file that I sent to everybody.
Okay.
So from 28 to 29, or up to almost up to 30, this is not exactly 10 meters, but we call it the approximately 10-meter band because it makes it easier to keep track of things. Again, by hard math, 15 meters, 300 divided by 15 would be 20. In actuality, our band covers from 21 to 21.45. We just call that the 15-meter band, and actually the shortwave broadcasting bands use the same they use the same basic terminology. Okay, very importantly, one of these I can almost guarantee will be on, oops, I picked up the wrong thing. One of these I can almost guarantee will be on your exam. Okay, so notice right here, we have these things called HF, VHF, and UHF.
Yes.
All right, I will ask these over and over and over. HF covers from 3 to 30 megahertz.
Yep.
VHF covers 30 to 300. UHF covers 300 to 3000 megahertz. We replace the mega with a 3 gigahertz in that case because the numbers get really big. So that's known as the UHF spectrum, VHF, or HF, VHF, and UHF spectrum. And one interesting thing to note, even though they have the same exact amount of space on this drawing, because it's logarithmic, how much room is there between 3 and 30 megahertz?
That is 27 megahertz only.
Right? How about between 30 and 300?
That is more than almost 300 megahertz.
Right, so
270
270.
megahertz.
270.
270.
Mm.
And between
Hmm.
300 and 3000,
27 megahertz.
well, no,
2700
2700.
megahertz.
2700.
Yeah.
Right. Okay. So basically what that means is that each of those spaces is 10 times bigger than the previous one. So if I were to say that a given signal, for instance, takes up, I'm going to draw a signal. All right. Say here's my center frequency, and here's, let's say, +1 megahertz and -1 megahertz. How much room does this whole thing take up?
2 megahertz.
That takes up 2 megahertz. Okay, so if this is 2 megahertz in width, and I look at HF, which covers 3 to 30 megahertz, and this is only 27 megahertz wide, how many of those signals could I put in there?
13.
I could put about 13. Yeah, 13 and a
Yeah.
half signals. Okay.
Yeah.
How about between 30 and 300?
We can put 135.
Yep. So 270 megahertz, that's 135 of the signals.
Yeah.
And between 30 and 3000,
You can say
1,000.
13,000.
1,350 of them. So
Yeah.
which do you think, which of these bands is more valuable to
The
signals
shorter band.
to companies that want to use broadband, where there's a very high data rate, because high data rate takes up a lot of space.
Hmm.
So they don't so much care about the high frequency bands because you really can't put much in the way of high data rate signals there. You can put a little more in this VHF band, and you can put an awful lot in this UHF band. So this UHF band and frequencies above that are really, really, really coveted because you can make a lot of signals fit into that space. And on top of that, what do you think about the antennas? Let's say, down here at the left, are these big or small antennas?
With a big
Oh.
antenna.
These are big antennas. This
Big
might,
antenna.
right? So let's say we pick 10 at 10 megahertz. This would be a 30-meter antenna. How about
Yeah.
way up here?
It's only
That
small
antenna would be
antenna.
That antenna would
Three-
be like 300
Point-
Point
centimeters.
3 meter.
0.3
Point 3
meters.
meter.
Yeah.
Yeah,
0.3 meter.
really, really small, which means
Mhm.
that it's very easy to stick one of those inside a cell phone.
This isn't on the test, is it?
Nope.
The-
Antenna.
okay,
Nope.
good. Because I didn't remember reading this, and I was like, this is kind of new to me.
Yep, but that's why we're doing it, because this is why things make sense in the world. That's why I cover these things, because there's all this stuff around you. There's all this stuff around you that is there, but isn't really ever explained. And this is why they are the way they are.
Is that divider that you had the negative hertz and the positive hertz? What's that again?
That's just the
Is that
zero
the carrier
line.
wave?
Yeah, if we were just to define a center frequency for a particular signal, to say
Okay,
that it extends above one and below one, wherever we happen to put that.
so the upper and lower bandwidth.
Yeah.
Okay.
So
When the book we could find the chart that we were just using with the megahertz and that long chart you were just using right now.
which one? This one right here?
No, the other one that I had, like the HF, the VHF, the 30 megahertz, and to the
Yeah,
P.
the steps. Mhm.
Oh, yeah. I actually, let's see. I think it's in the book, but I mean, not exactly like this. But if you want, you can feel free to. Yeah.
Yeah,
If you
that one.
put it back on the screen, I took a picture of it with my.
Right. I was
I'm
going to
using
say
an
you.
iPad, so I took a picture, so now I have it as a photo.
Yeah.
I will do that right now. Give me one
Yeah.
second.
In fact, I'll
Or if
leave
you
that up.
can save your screen or something like that.
Good idea. If I can find my camera.
Scott?
Yeah.
Can I ask a quick question? Yeah, can you just tell us, without getting into a whole bunch of technical stuff, where would ELF and ULF be
Way at the
useful?
left. Where would they be useful?
Yeah, basically, or
Um,
how can you address those waves in general?
those would typically be used for like communicating with submarines.
Yep.
And basically things that, basically water tends to cause a lot of attenuation for a lot of radio waves. But the longer the frequencies or the longer the wavelengths, the lower the frequencies, those tend to get a lot deeper into water and earth for that matter. Because
Yeah.
the wavelengths are so long.
So they use them for like doing different studies of seismic activity and different things like that, right? with
Yeah.
them?
Yeah, and communicating with submarines.
Sure.
So there's like, VLF communications with submarines.
Right.
Doesn't
But-
UHF and VHF is only line of sight, right? Unless you have certain conditions.
Typically, yeah. Yeah, UHF and VHF are typically line of sight. But if you think about it, looking down through, 10,000 feet of water, technically it's line of sight, right? But it tends to attenuate those frequencies a lot. All right, you guys ready for a 5-minute break?
Sure.
Okay, 5 minutes. I'll go and hit the
Good.
bathroom and I'll see y'all in 5 minutes.
Okay.
Tenemos 5 minutos de break.
Bebé, ay, bebé, me siento una cosa. Mira, mi primer pega American Dream,
¿Cuál de ellas?
la de San Juan Lidia con el montañés.
Ay, me para la cintura. Ay. ¿Eso yo? Hey, what's up?
All right, any questions?
Yeah, I'm one of those people who's definitely like a black box kind of thing. As you were describing the like bands and how much
Mhm.
room they have, is it basically possible to overcrowd one and make it so like what happens, if
We
does
can
that make
do that.
sense?
We can do a demonstration right now. All right, so let's say that we had an audio band, right? Here we go. Let's say we have our audio frequency band from 0 to 5,000 hertz. And a typical person's voice is, let's say, 1,000 hertz wide. And we could somehow work it out that each of us had access to just one. So, this person's voice would be between 0 and 1,000. Then another person would be between 1,000 and 2,000. And another one would be between 2,000 and 3,000, and then 3,000 and 4,000, and 4,000 and 5,000, right? Everything's good, right? You could actually tell the difference between them by filtering and just listening to one of them. All right, so here comes the problem. We don't talk like that. All right, so I need 5 people, including myself, who are going to be unmuted. All right, here we go. And ready? On the count of 3, I want you to say your address. All right. City, state, zip code. Ready? 1, 2, 3.
Chris?
3662 Vine Maple Street, Eugene, Oregon, 97405. Okay, could anybody hear anybody? Right, and
only
that's
for you.
only me?
Yeah.
All right, let's try that again.
Zoom might make priority to the presenter.
Okay,
whose
well,
audio-
I'll just shut up then. All right, you guys do
Yeah.
it. Ready? 5 people. Ready? Go.
35 Ash Grove.
10204 East
32932 Smith Road, St. Helens, Oregon.
All right, notice we're all using, we might be able to pick up one, right? Or pieces of, but the problem is that now we're all sharing the same bandwidth because everybody's voice is by and large covering the same set of frequencies. So that's what happens. You basically get into a situation where you get lots and lots of interference and nobody can use it. Or maybe maybe the strong one wins, and that's it.
So I see a lot of that whenever my brother's doing the radio contest, whenever we're trying to make multiple contacts.
Mhm.
That's exactly what happens with too many people on the band. You can only hear certain amount, or barely anything of your call sign.
Yeah. Yeah. You don't really stand a chance. So, okay. Well, let's see. Now we've covered what is known as RF. RF stands for radio frequency. That's basically all those frequencies that are not visible light and not X-rays and not ultraviolet and not infrared. So now we're going to start actually using these things. So I assume everybody's back. I know I am. Got my coffee going, lots of coffee. All right, so the first thing we're going to draw is a very simple representation of
Atom.
an atom. Okay, what is at the center of this atom? What's at the middle?
Nucleus.
Nucleus. What charge does a nucleus have?
Negative.
Positive.
Positive charge. So this is our protons and our neutrons. All right, and what is whipping around the outside in
Electrons.
valence shells? We have electrons. We have them having a negative charge. Okay.
Negative charge.
All right. So this is the basic, this is the fundamental thing that we have to understand when talking about current and movement of electrons. Electricity is essentially the movement of electrons. So we're going to have a couple of devices here. We're on page 4, by the way, in case anyone wants to follow along. So this thing is called a battery. A battery has a positive terminal and a negative terminal. So the first thing we're going to say about this battery is that a battery has an E, which is an electromotive force. It's the ability to move electrons from place to place. The bigger the battery, the higher the voltage, the bigger its ability to move electrons. All right, so now we're going to have this piece of wire, which is typically made of copper or something like that. And we're going to have this thing called a resistor. A resistor, we're doing basic electric theory, a resistor has the ability to resist the flow of electrons. So basically, if a battery pushes hard, a resistor pushes back in a way. It basically says, nah, okay, depending on how hard you push, that's how much I'm going to allow through. If you don't push very hard, I'm not going to allow very much through. If I have a big resistance, if I have a very low resistance, I'll say, whatever, come on through. So, and then we're going to take this and complete the loop and make an entire loop. And this loop is known as a circuit from the word circle, because as you can see, we now have a completed circle from the battery through a piece of wire, through our resistor, and all the way back to the opposite side of the battery. And the measure of how much a resistor fights the flow, this is measured in a unit called ohms. So the volt is named after volta. The ohm is named after Georg Simon Ohm. The amount of current, the amount of electrons we have flowing is the letter I for impulse. And this is measured in amperes, named after ampere. Now, notice that all of these, so we have the ohm, the ampere, and the volt. Ohm, ampere, and volta were all 1800 scientists who studied electricity. So they were in the right place at the right time. They did some good studies, and now their names are forever linked to electricity. So one thing that I will say is, okay, so we just drew this atom here. What is the charge on an electron?
Negative.
Plus or minus? It's negative. Okay. Well, given that, now look at our battery. It has a plus terminal and a minus terminal. which terminal do you think the electrons should probably come out of?
The negative.
Yeah, because it's the negative terminal. And in fact, our electrons come out of the minus terminal and they flow around the circuit this way. And they end up going back to the positive thing. However, for those of you who've ever taken a physics class, which way does current go? By definition,
Positive to negative.
it goes
Positive
out
to
of the
negative.
positive and flows around this way and comes out through here. And why is that?
Conventional current, we used to call it.
Right. And that is because they made a mistake. Almost 200 years ago, they made a mistake because they didn't know what an electron was. They didn't know that there was a thing called an electron. They knew that there must be something called an electron, but they didn't know what the charge was. So they said, well, it must just come out of the positive. And that mistake was made a long time ago, and we still live with its results today. So for the sake of everything that you do from now on, you'll just keep in mind that electrons actually flow out of the negative and up to the positive. But for the sense, for the sake of what we're doing and for the sake of all your calculations, current flows out of the positive and around and comes back into the negative. So we just all have to live with that mistake. And trust me, as an electrical engineering student, it was very hard to get over that because, you know, it goes against the laws of physics. Well, the laws of physics weren't known yet. So
Yeah, it gave me a lot of headache too. As
Everyone.
An electrical engineer.
yeah, everyone.
Yeah.
All right. So now we know that the flow of electrons as they move through a piece of wire and through our circuit is actually opposite, but we're just going to ignore that fact. We're going to erase all these little red arrows and say that, okay, current is like water flowing through a stream. If you think about a stream bed, right? And you don't have a very high starting point, how fast is the water going to be flowing through here?
Not very fast.
Not very fast. How about if this is a waterfall and this is the top and this is the bottom?
Quite a bit faster.
It's going to go a lot faster. It's going to have a lot more potential energy, right? It's going to have a lot more ability to push that water over the falls. So let's now take this and make it a nice level stream again. And now I'm going to put, being that I'm in Oregon, I'm going to put, I'm going to put a nice little beaver dam here because the beaver is Oregon's state animal. So what's going to happen when the water gets to that beaver dam?
It'll stop flowing.
This is basically a resistance to flow. It's going to object to the flow of water. And, you know, some of the water will flow around it, and maybe some will flow through, and maybe some will flow over. And as that happens, it's going to diffuse, it's going to slow down. Basically, this resistance is a resistance to flow. So in this particular case, we don't have a beaver dam. What we have is this resistor. And what a resistor is a calibrated device, which is, okay, so let's first take a look at what wire is made of. Let's take a look at what wire is made of. What is wire?
Any metal.
Right? It's typically copper or silver. It could also be aluminum. And what all these have in common,
They're conductors.
they're conductors. And what makes them conductors?
The
Free
electrons flow.
lot
Electrons
of
flow free.
electrons available.
Yep. So basically what you have is if you push an electron here, the electrons that are held by this particular atom are loosely held. And they're kind of like, you know, they kind of play loose. And if one electron drifts into this area, it might take it in, but in order to make up for it, another one comes out. It encounters another atom here, and here's the electrons floating around, and it drifts in. And because it drifts in, another one pops out. So basically you have one going in, even though you have other atoms in the way, you have one going out. So this movement of electrons is known as current. The more electrons you have passing across a certain point in a second, if you have more electrons passing, that means you have more current. By definition, 1 amp is 1 coulomb of electrons per second. So you're not expected to know this, but just keep in mind, anyone know how big a coulomb is? It's 1.6, if I remember right, times 10 to the 19th electrons. That's a lot of electrons. Electrons are really, really tiny. So the next time you see a current flow of 1 amp, realize that it's an insane number of electrons moving. That's why we use something called an ampere, because the number
that's
doesn't
per
make a lot of
second.
sense.
Yeah, in 1 second.
Per second. That's
Yeah.
1 amp. That's a lot of electrons moving across a point. Okay, so now what we've established is that we have our plus and our minus. This battery is creating an electromotive force, and it's measured in volts, which is trying to get a current flow through the resistor and out, back, and into the circuit, into the other side. This resistor has a certain number of ohms of resistance that is being provided to resist the flow of current, which is measured in amps. And this is governed by something known as Ohm's law. There's that name ohm again. E equals I times R. I will often draw this like this, the same way that I did before, so that if you have two values that you know and one that you don't, what you would do is, let's say in this particular case, I have a 12-volt car battery, so 12 volts DC, and a resistor of, let's say, 1 ohm. Okay, what is the thing that I don't know?
Current.
Don't know my current. So what I will do is I'll take my current and cross it out. And now I have E divided by R. So my current I is equal to E divided by R, which is 12 volts divided by 1 ohm, which is 12 amperes. And that's how I would, that's my first calculation of something known as Ohm's law, to figure out what my current would be. Okay, so how much voltage does a mobile transceiver typically require? Mobile transceivers will typically run off of a car battery. And nominally it's 13.8 volts because it's a lead acid battery. But it's nominally 12 volts. So the question was, is resistance man-made or, well, a resistor is a man-made thing, but resistance is an intrinsic property to a material. So let's ask this question. All right, what do you call something that allows current to flow?
Conductor.
That's called a conductor. That's
And
called a
it's gonna-
conductor.
And an insulator.
Right, okay. And give me some examples of a conductor.
Metal.
Gold, copper.
Copper, not all metals.
Right.
Copper, gold, AU,
Silver.
silver, aluminum's actually really good.
Aluminum, good conductor.
Ion.
Okay, now let's think about things that don't conduct electricity very well.
Glass.
All right,
Glass,
that'd be an insulator.
wood.
Rubber.
Right, glass, wood, rubber, other things.
Air.
Dry air. Dry air is an excellent
Dry air.
insulator. How about water?
No, that would be more of a conductor.
It's a
Uh,
conductor.
Not if
Pure
it's
water.
deionized. If it's deionized water,
Ionized,
it's
true.
a
Pure
pretty
water,
good.
no.
It's a pretty good insulator. However, most water, like salt water,
Mm.
is a great conductor. How about paper?
Insulator.
Good insulator. Yep.
Dry
So-
dry paper.
Yeah, dry paper. Yes. Okay, so those are if you look at how they are, what they contain, what they actually are, the overriding thing that you'll find is that in a conductor you have essentially a lot of electrons that are loosely held and available to be moved. And in an insulator, your electrons are tightly bound and not available, because that is in fact what current is. Current is the movement of electrons through a particular point. So if your electrons are not available to be moved, a new electron that comes in is not going to be accepted and find another electron to push away. Now, what can you do to this electron to make it go through?
Charge it.
You can put more voltage on it, because voltage is electromotive force. It's basically the force necessary to move an electron. So what that means is if you charge it more and give it more oomph, what can happen to this insulator?
It can become
Break down.
conductive.
Yeah,
It
you
can
can
become a
become-
conductor.
Yeah, right. You can make it conductive,
hmm
at least for a little while. If you have something that is designed as an insulator, let's say this is a sheet of paper and something flows through it, you can actually damage it, right? You've actually punctured the insulation.
Catch on fire.
Yep. Or it just destroys it, and then it no longer provides a good path. This is also something that you see if you're outside. Does anyone live on the East Coast?
Yep.
Anyone ever seen this outside?
Yep.
All right.
Mhm.
So air has a dielectric constant of about 10,000 ohms, or sorry, 10,000 volts per inch, if I remember right. So how do you make lightning if air has that much resistance?
They charge the heck out of it.
Yeah, if you make 20 million volts, well, you can make, you can jump that gap pretty well. And then once you do that, the path that it makes becomes ionized. It has electrical charge to it, which is why once it makes a path, the rest of the lightning often follows the exact same path, because now it's got a nice path to follow.
Hmm.
Okay. What is the name of flow of electrons in an electric circuit? That'd be known as current. Electrical current. What's the units of measurement for current?
Ampere.
Amps.
Ampere. Very good. Okay. Next, if I have a piece of wire and current is flowing directly from left to right always, what is that known as?
Direct current.
Direct current. Okay, how about if over time my current flows this way and then changes direction? It alternates
Alternating
direction.
current.
That would be known as an
Alternating.
alternating current,
AC.
and that would be known as AC. Okay, and this is known as DC. All right, so now we have two different flavors of current. Now, here's a question. If I were to make a graph, and I would have current flowing in the positive direction and current flowing in the negative direction, and it goes like this, and then it switches and goes like this, and then it switches and goes like this, switches and goes like this, back and
AC.
forth. That would be AC. That is really ugly AC, right? But this is alternating current, right? Now, this is also known as a square wave, but it's alternating current. Now, if I could also, let's say, how would I make this? I would switch something on and then immediately switch it off. How about instead, I did something like this. And I had something rotary, went around like this over a period of time. And my voltage was the distance in this direction from the zero line. And I were to graph this as it made a circle. This may actually look familiar, right? Because we talked about this a little bit before. Well,
You got a sine wave.
you have a sine wave. And it comes over and down again to here, and then back up to here. Well, what do we know that goes around and around in a circle?
A wheel.
A wheel, that's right, a wheel. And what can a wheel be used to turn?
Generator.
A generator, yeah, okay, great. So now what we have is a sine wave being generated by a rotating device. Well, that can be in a power plant. So what we've got is basically this thing called sine wave being generated by rotating machinery. If you look at almost every power plant that we have ever built, you will find like a commercial plant that runs off of steam that can be powered by nuclear or a water wheel or anything like that. You will find that it is operated by rotating machinery. A turbine runs off of steam, and it spins around and around and generates sinusoidal current. This is actually very, very profound for what we do as far as distributing power, which we'll get to a little bit later. So given that we have this thing called AC, how fast, if we were to somehow make that travel through space, how fast would it go? Considering it's an electric thing. How fast would that wave travel?
Speed of light.
Yeah, it would travel at about the speed of light. Well, in reality, this doesn't actually travel at exactly the speed of light. But if we were to make an actual wave out of it, it would travel at the speed of light. And what does this have? How many times per second in our power system does this go up and down?
60 cycles.
It has
50 hertz.
depends where you are. Yes. In some parts of the world, this is 50 hertz. In some parts of the world, this is 60 hertz. Depending on where you are. If you're in South America, it's 50 hertz. If you're in Europe, it's 50 hertz. Or if you're in the US or Canada, it's 60 hertz. All right, but this is alternating current. And how many, let's see, if this is alternating current, what is the voltage of the alternating current in our electrical system in the United States and Canada?
110.
110, some people call it 120, 117,
110 to 120.
115. It's somewhere in that range.
240.
Yes, there's also 240.
480. There's a whole lot of them.
There's also 208. There's 480.
277.
277. If you live in Canada, you have 347 and 600 or 575.
277's lighting.
Yeah, I do a lot of work in Canada. And so depending on how your system is set up, depending on where your ground is and what shapes are, this is actually called Y power. This is delta power. And this would be a split phase. And this is how you get 240 in your house, for instance. This is how you get 480. And then if you go from here to here, this is 277. And I could go on and on about electrical power. But most importantly, what frequency is, no matter what the voltage is, what frequency is in the United States is this operating at?
60 hertz.
60 hertz. 60 hertz. Okay. Let's see. We already did conductors and insulators. All right. So back to Ohm's law. Ohm's law. Somebody want to tell me what Ohm's law is again? If I draw this triangle, what's on the top?
Voltage.
Voltage.
Which we use letter E.
E.
All right.
E.
And down below?
R and I.
I and R. Okay. So once again, the nice thing about this little triangle is that if you don't happen to be particularly good at algebra, all you have to do is be able to draw the triangle correctly, or draw the circle correctly and cross it out. Some people do it as a triangle. I do it as a circle. So let's draw a simple circuit. And we're going to have a circuit where we have a current of 3 amps. And here's our resistor. And we're going to have a 90-volt battery. Okay, by Ohm's law, what is our missing thing?
Resistance.
Resistance. Okay, and how do we calculate that? What are we left with?
90 divided
by
by 3.
E divided by I, which is, so we have R is equal to 90 divided by 3 is
30.
30 ohms. That must be a 30 ohm resistor right there. Right, and that is how we do Ohm's law. So now, I mean, there are many examples. The nice thing about this is, okay, well, I could do this any way I want. I mean, you know, if you look at the exam pool, the question pool, you'll find that there are about 15 different basic Ohm's law questions, right? The way that an exam is created is that you're only going to be given probably one question from that section, but you don't know which one it is. So would you rather memorize all the questions or just know how to calculate it?
Memorize the formula.
Right, you memorize the formula and know how to calculate it. So if you have a circuit that looks like this, and they say that it's, let's say a 200 volt power supply, 200 volt DC power supply. And we have a resistance of 25 ohms. What would the current be? Okay, we do the same thing. EIR. We don't know the current. We have E divided by R is 200 divided by 25.
500.
That would be 8. So we'd have a current of 8 amps because we have E divided by R. So that's it. You just do the same thing over and over. No matter what they throw at you, it'll always work the same. Let's see. And actually, a long time ago, there was no such thing as a question pool. Basically, somebody would give you an exam and you would not know what was on the exam. They'd just say, solve this equation. You know, here's your circuit. Tell me what the answer is. So, all right, so let's look at series and parallel. Series and parallel. Okay, so let's say that you're watching a TV show and you go from one episode to another. That would be known as a series, right? Because you're watching them in order. Let's say that you're watching 2 football games at the same time. You're watching 2 screens at once. They would be in parallel because they're happening at the same time. This is a series circuit. Okay, which one takes more time to watch?
One
Series.
show after another. Yeah, the series.
Right, that was series would take longer to watch. The parallel would be happening at the same time. Okay, so now what we're going to do is say, okay, we're going to look at our series circuit. Here's our battery. And let's say this is 3 ohms and this is 6 ohms. How much resistance would an electron that's sitting on that wire moving through encounter? Well, it would encounter 3 and then it would encounter 6 more. So what would the total be? It would be 9 ohms. So in a series circuit, the resistances, or if you want to think about it, the amount of time necessary divides, but it's not really. It's really just that they add together. In a series circuit, resistances add. Okay, but now let's draw this in a parallel circuit. And let's say that this is 5 ohms and 5 ohms. Okay, so let's say that you are on an electron that's flowing through this circuit. If I were to make this second resistor disappear, how many different directions could you go?
One.
You could just go one way. All right, but how about if I bring it back? How many different ways could you go?
2.
You could go 2, and each of them has equal resistance, which basically means that half of the electrons would go this way and half would go this way. So all in all, each of them only encounters there's only half as much stuff trying to get pushed through each one. So what happens in a parallel circuit is that it follows this, that's parallel, R1, R2 over R1 plus R2. If they happen to be equal, it's equal to 1/2 of the resistance. If they happen to be equal, it's 1/2. So if I have a 5 and a 5, what is the end result?
2.5.
2.5 ohms.
5 ohms.
They actually divide. They actually get smaller. If they're not equal, then the answer will follow that formula right there. So what that means is if you have a really, let's say that in this particular case, I have a resistor that is 100,000 ohms, right? Well, 100,000 ohms is providing a lot of resistance. What do we know about water when it flows? Water takes the path of
Least resistance.
least resistance. So most of the water is going to go, most of the current in this case is going to go which way?
To the 5
The
ohm.
5
To the
ohm.
5, which basically means that this 100,000 ohms is essentially going to play a very, very small part in changing the overall resistance because it's such a high resistance. And in fact, it's such a high resistance that you might at some point consider it to be one of those. And what would that be called?
Open circuit.
That is an open circuit,
Mhm.
which basically has an almost infinite resistance. Essentially, it's not a connection at all. Okay, so let's go back up to our series circuit. So let us say that we have our current flow through these two resistors, and I could put a meter across this one that would measure voltage, and a meter that would measure voltage here. Okay, so what do I know about the current that is flowing through those two resistors?
Same.
It is exactly the
Same.
same because the current has to go through both serially. It has to go through one and then the other. All right, so now could I not use Ohm's law right here and right here separately? I bet I could.
Mhm.
All right, so now what I'm going to do is do Ohm's law on the first one. And I'm going to do E equals I times R. And we're just going to say that this current, we're going to pick it at 1 amp. All right, so E is equal to I times R. What is it in the first resistor? It's 1 times 3 is
3.
3 volts. How about in the second one?
6.
Equals 1 times 6 is equal to 6 volts. So what that means is we actually have different voltages that are being dropped in a way across each of them. So this obviously is a 9-volt battery. So if I have a 9-volt battery, it's actually going to cause this to measure 3 volts and this to measure 6 volts. So this is also really important because it also means that the sum of all the voltages around a circuit is what?
0.
It's 0. If I start at 0, I'm going to write this thing as a ground. Ground is our definition of 0 volts. If I go this way, I start at 0, then I go up to +9, and I come, and this is obviously a loss, so this is a -3. So that now makes it 6, and then -6, I'm back at 0.
0. Yeah.
So this is a loop. This is known as our Kirchhoff's voltage law, or KVL. Basically, it says that the sum of all the currents, the sum of all the voltages around a circuit, no matter what path you take, has to be 0.
So what happens if the volt was like a 12 volt? Would just go to the ground remainder?
No, you're well, let's do that. Okay, so in other words, we're going to draw a 12-volt battery, right? Okay, so we'll draw a 12-volt battery. We're going to have our resistors, 3 ohms and 6 ohms. Okay. So what's our total resistance?
9.
9. What's our current? E equals I times R. What's our current?
E over R, 12 over 9.
Right. So we have I is equal to E over R is equal to 12 ninths. Is equal to 1.33 amps.
1.33.
Okay. So now we'll look at our 3 ohm resistor. E equals I times R. What's our new current?
New current is 1.33. New voltage here will be
1.33
3.99.
times 3 is
3.99.
we'll say 4 volts. Well, if that one's 4 volts, what does this one have to be?
5.
E equals I times
Oh,
R.
yeah.
1.33 times 6. That should be 8 volts.
Mhm.
So there you go. The
There's
law
your
still
current.
holds.
Okay.
Okay.
Has to hold. So what it really means is that it bumped up the current to make sure that everything still works. Because it had to. Because the law says so. Okay, so now let us take a look at this. If I were to, this is another pretty profound thing to realize, is that if I have this circuit and I have 12 volts here, we just proved this. If this is 3 ohms and this is 6 ohms, are the currents going through both things exactly the same?
No.
Yes.
Yeah, they have to be.
Yes. Series,
Can't go anywhere.
in series circuit.
Right, in series.
Current is the same.
Current is the same. How about the voltages across each one that I measured?
Different.
Those are different, right? This actually can function if we draw this differently. Let's draw this like this instead. Okay, I'm going to draw ground. How many volts is ground for reference? That's 0 volts. This is plus 12 volts. And this is a 3 ohm resistor and a 6 ohm resistor. If I were to measure the voltage right here, we just said that this is how many volts right here? That would be 4 volts. And we have to go according to the law. So this is at 0 down here. This is plus 12. Well, this is now minus 4. So we're at plus 8. And now this is obviously a negative 8. And we're back at 0. So if I were to measure the voltage across this V out, how many volts would I get?
How did you get the plus 8?
8. Well, that's how much voltage is left
Oh, okay.
as we go around the circle.
Okay.
So we would get
0 volts.
We would get 8 volts out of a power supply that was a 12-volt power supply. This is known as a voltage divider. And when we do this, all we know is that the current going through the 2 voltages is exactly the same. The voltages that you see across each resistor are proportional to the resistors themselves. So they're going to, they will probably be different depending on the resistors you pick. All right, so now there is a problem with this circuit. And the problem with this circuit is, let's say that I want to run my house and all my lights in my house like this. What is the problem with this circuit if I try to run my house like this?
Can't supply a lot of current.
Well, let's say you could. Let's say you could.
If
Well,
one light bulb
so
goes
that-
out, the entire string goes out.
That's right. If one bulb goes out, you break your entire circuit. That becomes an open circuit and all your lights go out. This is the classic Christmas tree lighting problem. So what happens is if you break one, you break the whole thing. So now what we're going to do is draw it like this. We're going to draw our parallel circuit again. And why would this be a better circuit? Because if we knock out our first light, what happens to the second light?
still fine.
It stays lit up. Yes. This is a much better way to do a lighting circuit.
I was gonna say it gets brighter too.
This actually wouldn't, because if this is our voltage, how much voltage will you see across that light all the way on the right? You'll see the standard voltage, right?
Full voltage. Yeah.
If you put a light here in the middle, how much voltage would you get there?
Same voltage.
Same voltage, which means that so long as your power supply can deliver enough current, the current gets divided based on the resistances that it encounters, and that the voltages stay the same.
Okay. Just for,
Minus-
sorry, I was gonna say just for fun.
Oh,
Can you draw the circuit that shows why lights get dimmer as you go down the line?
Mhm.
What?
that's a series circuit again. So if I were to do that,
Yeah, but you still get a voltage drop down the line.
yes,
you
you
know?
do. Let's say you had a whole bunch of these and they're all equal, right? And let's say this is a 3 ohm and a 3 ohm and a 3 ohm and a 3 ohm load, and this is a 12 volt power supply. What would be the total? What would be the total resistance of those four?
12 ohms.
12 ohms. What would my current be?
4.
1 ampere.
It would be 1 amp.
1
Right.
amp. Yeah.
So, okay, so now what would the voltage on each of these be? E equals I times R. Would be 3 volts. Okay. Well, here we go. Here's the next part of Ohm's law. P equals I times E. I could draw it like this.
Power watts.
That would be power in watts, right? Okay. Let us say let us ask how much power is being delivered by the whole circuit.
12 volts.
Right. Well, here's power in watts. And here's our current, 1 amp times how many volts?
12.
Is 12 watts. Okay. So now, how much is being consumed by each of those lights?
12 watts.
It is not.
1/4.
Oh, no,
1/4. Yeah.
3 watts.
Yeah. 3
So
watts.
it's 1 amp, because they all experience 1 amp times 3 volts is equal to 3 watts.
Mhm.
Okay. That's each of those 4 bulbs. What if each of those bulbs is rated as a 10-watt light bulb and you're actually allowing it to consume 3 watts?
Ah.
It's okay. Under
It's gonna be-
power, under the rated power.
It's going to be
Dim.
very dim.
Dim.
Yeah. And the more things you add in series, the lower the voltage is. And because power is equal to volts times amps, the lower the voltage, the lower the wattage, the more power, the less power you're going to have.
They call that the forward voltage out of each.
Yeah.
Right, I got you. That's what it sounds like. Thanks.
Mm-hmm. Okay, so in a parallel circuit, very importantly, I'm going to draw a sine wave here, 120 volts. In this circuit right here, you have the same voltage across every one of your devices. This is how we do electrical design. Because what it means is if something happens, a fuse blows here, everything else still works. So in a parallel circuit, you get the same voltage across everything. What happens to the current at the junction of 2 components in parallel? What happens to the current?
Divided according to the resistor.
Divided according to the resistors. That's right. So it is also true that if I were to erase this right here and redraw that, I would have some current flowing here and current flowing here. So where would the highest amount of current be seen in all of these things?
The lowest resistance path.
Where would in this entire circuit, where would you see the most amount of current flowing?
The first one.
In the
Right.
sum of the
Yeah.
right after the battery, right after the battery before it reaches the first resistor.
Right. So that would be right here. Oh, why can't I draw this today? Man. There we go. So in that area of the battery, right up to here and right down to here, you will have the maximum current draw. So what does that mean for your wires?
Heating up.
So you might
has to be high enough.
to handle the full current. Yeah, exactly. So by the time you get down here, those wires all the way on the right might be actually pretty small. When you're all the way over here, the wires might be pretty big. If this is your house, let's say that this is power coming into your home. What that might mean is that coming in, if your service is, let's say, rated at 200 amps, this actually could be like a 3/0 cable, which is like as big as my pinky finger.
Yeah.
By the time you get down here, this might be a number 12,
Mm-hmm.
which is a much smaller wire because it's not expected to ever see as much current. Okay. So let's see, DC power. We already did that. What's the formula? What's Ohm's law for power?
P over.
P equals I times. Everybody likes pi, right?
Right.
PIE. Just draw it like that. Okay, so let's do one right here. When the applied voltage is 13. Let's just do one like this. 13, we'll pick an example. 13.8 volts DC. And we're pulling a current. Okay. By Ohm's law, how much power is this consuming? P equals
138.
I times E is 138 watts. Hey, there's nothing magic about this. This is all just basic arithmetic. Okay. And they're just all kinds of different variations of the same thing. So now what we're going to do is math for electronics and conversion of units. This can trip some people up, but it's really not all that bad. I sent everybody a cheat sheet that had it that had this in there. But so we're on page 12 of the book right now. It says math for electronics and conversion of units. Okay, so I'm going to draw a unit, and my unit is anyone ever heard of that unit?
No.
A blub? I made it up. All right. Okay. This is my new unit that I've now created. It's called a blub. I don't know what it is. I don't know what it's used to measure, but that's my unit. Okay. So if I wanted to have 1,000th of a blub, I would go 0.001, and I'll call this a BL. That's my my lettering for it. It's a 0.001 BL. Actually, I'll call it a BB. There we go. So I have now written 1/1000th of a blub. Does everyone agree with that?
Yes.
Okay. So I could now take this 0.001 and replace that. I would go and say, okay, well, I have 1, 2, 3, and now I have 1 dot, but I've now consumed 3 spaces, right? I've consumed 3 zeros. If I were to write 1/1000th is equal to 1 divided by 1,000, is everyone in agreement with that?
Yes.
Okay. I could also write this as 1/10 times 1/10 times 1/10. Everybody agree with that?
Yes.
Okay. Each 1/10 by definition is 10 to the -1 power. That's convention. So I have 10 to the -1 times 10 to the -1 times 10 to the -1. If I have the same base, I can now add the exponents. So that's 10 to the -1 minus 1 minus 1 is 10 to the -3. This is by handling powers, bases and powers of 10. So I could actually rewrite this as 10 to the -3 blubs. Now, I could also rewrite this and say, if I look at this chart that's given to me on page 12, 10 to the minus 3 or 1,000th is also known as a milli. So I could replace that letter. I could replace that 10 to the minus 3 with the little letter m, and that would be 1 milliblub. I now have a milliblub. So 0.001 is the same as a milli. If I had, let's say, 1,000 blubs, I could rewrite that and say that's 10 times 10 times 10. I could also say that that's 10 to the first power times 10 to the first power times 10 to the first power. That means 10 to the something. 10 times 10 to the first power is 10. And then I could also say those are the same bases, and I could add the exponents, and I get 10 to the 1 plus 1 plus 1 is 10 to the third. And we also know that's 1,000, so we've now written it two different ways. Now we're going to add a third way to write it, which if we look at our chart, we know that 10 to the third can also be replaced with a little letter k, which means kilo. So my new unit is a kiloblub. That's 1,000 blubs. I could also make, let's say, 1,000,000. And this I could rewrite as 10 to the 6th, which I could say is mega, which it is. And that would be 1 megablub. Now, here's the other thing that I could do with this. I can say that if I have 6249000 of these things. Okay. Now, the way that I would start is here's my decimal point. 1, 2, 3, 4, 5, 6. I've now moved it over 6 places. And now here's my decimal point, and here's the information that's interesting. And that's 6.249 times 1,000,000. Well, what do we know that 1,000,000 can be replaced by?
Mega.
Mega, big letter M. That's 6.249 megablubs. Okay. Well, now what I'm going to do is say, well, a blub is a stupid unit. I'm going to replace this with a hertz. I can call it whatever I want, right? Okay. So now 6249000 hertz. I can do the same thing with it. 1, 2, 3, 4, 5, 6. That becomes 6.249 times 1,000,000 hertz. It's equal to 6.249 megahertz. And now we're using a unit that people actually recognize, that we use all the time. And we could make that unit just about anything. We could make it amps. We could make it ohms. We could make it farads for capacitors. We could make it henries for inductors. We can do it we can do anything we want with it. So that's how you would convert from one unit to another. So if somebody were to say, for instance, on page 12, we have 1.5 amperes. How many milliamps is it?
1,500.
That'd be 1,500, because we can rewrite this 1.500. We can say 1, 2, 3 times, now we moved it 3 places. So we have to account for those 3 places that we moved. So we shifted it to the right 3 places, which means we actually have to do something going the other way so that it all equals out, because we can't change the basic number we started with. We now have 1,500 times 0.001 amps. 0.001 is a little letter M, and that's 1,500 milliamps. And that's how we convert from one unit to another. The reason that we do this is because sometimes we deal with things that are insanely big or insanely small. For example, let us say that we have a brand new computer. Right? Let's say in your brand new computer, you've got a hard drive that was 2400000000000 bytes on the hard drive. All right. hey, all right, I got 2,400,000,000,000 bytes in my hard drive. Well, okay, good for you. That's a big number, right? We don't really need to know all those digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 2.4 times 10 to the 12th bytes. Anyone know what 10 to the 12th is?
Nano?
Tara.
Tera. So your new hard drive is 2.4 terabytes. And now you don't have to worry about all those extra zeros. That's why we do this, because those zeros take up a lot of space on your paper. We could go the other way too. We could go that we can say, okay, my new capacitor is 0.00000000016 farads. All right. Well, let's start moving zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So now we have 16 times 10 to the minus 12 farads because we moved it 12 places. What is 10 to the minus 12th equal to by that chart?
Pico.
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 So that's now 16 picofarads. When you go to buy a capacitor, you can very easily look up a 16 picofarad capacitor and probably find something. Again, that's why we do this. All right, so after decibels, we're going to take a break. We are on to decibels right now. All right, so Alexander Graham Bell did a lot of work with regard to sound power and various other forms of power. How big is something compared to something else? So what it was determined was, everyone's familiar, at least to some degree, with the Richter scale, where the number on the Richter scale determines the power of 10 or some other base to which it is raised. So what that means is that something that's a Richter that has a Richter scale rating of 3 compared to something that's a 2, the 3 is a lot bigger than a 2, right? And a 4 is much bigger than a 3, and a 5 is much bigger than a 4. What it means is that a 5 compared to a 2 is 3 orders of magnitude bigger, right? This is how we're familiar with knowing, like, you know, an earthquake. We had a 2.2 earthquake here some years ago in Eugene. That was a little nothing, but I felt it shake the house. That is very different from a 7.2 earthquake, which might, you know, knock everything down around us, right? Well, if you think about it, 2.2 is like, you know, 60% is like 30% of 7.2. It doesn't sound that much smaller, but because it's a logarithmic function, it makes a really big difference. So the way that a bell works, it's a way of comparing two things against each other using logarithmic values. It's equal to the log base 10 of P2 divided by P1. This is not on the exam, but it's important to understand where it comes from. So what a bell is a way of comparing how much bigger logarithmically something is than something else. So if I had, let's say, something that was 10 times bigger, let's say P2 was 10, a value of 10, and P1 was a value of 1. And I plugged this in, I said the log base 10 of 10. That means the power to which 10 has to be raised to get that value. So 10 to what power is 10?
1.
1. That would be a power increase of 1 bell. Well, okay, because a bell is actually a pretty big unit, they factored in a factor of 10. They changed this number and multiplied it by 10. So that's called a decibel, which a lot of people have probably heard of. So that is 10 log base 10 of P2 over P1. If we still use that value of 10 here and 1 here, we get 10 log base 10 of 10. And we can calculate log base 10 of 10 again is 1. We get 10 times 1 is
10.
10 decibels. So going up by a factor of 10 gives you an increase in decibels of 10. So now what we're going to do is something a little tricky to just show how this works. Let's go up 10 log base 10 of 100 divided by 1. So we went up by a factor of 100. That's 10 log base 10 of 100. What power does 10 have to be raised to get to 100? 10 to what
2.
power gives you 200?
2.
Or gives you 100? Exactly. That would be 2. So that's 10 times 2 is 20 decibels. So basically what that means is that every time you go up by 10 decibels, what do you do to your value?
Add 10 dB.
Well, yes, but it also makes the thing that you're measuring 10 times greater.
Mhm.
So what would 30 decibels be? If I was at
1,000
30
times.
decibels, that would be 1,000 times. If I was at 40 decibels, what does that mean?
10,000 times.
That would be 10,000 times. Or also you notice there are 4 zeros there. That's 10 to the 4th. So this is actually really profound because it allows us to measure things that are really, really big or really, really small. For instance, let's say that I have a transmitting station. This is why it's so important in radio. And I have a receiving station on the other end. And between this path, between what on the path between one and the other, I have a loss of negative 120 decibels. And I start transmitting with 1 watt on this end. How much power will actually be there at the other end? Well, I can say negative 120 is equal to 10 log base 10 of something divided by 1, because we're starting with 1 watt. And I can actually figure this out. That means that I have negative 12 is equal to log base 10 of something. And I can take both sides and raise them to the 10th, raise 10 to that power. And by doing this, I end up with a question mark. That's the question mark. I have 10 to the minus 12th watts at the other end, or 1 billionth of a watt. Or if I look at my chart, I have 1 picowatt. So this is actually really important because it allows you to compare things that are really big and really small. The thing that's also really cool about this is that if I now take this system and say that I have a 1 watt transmitter on this end, and I have an antenna, and I have a receiver on this end, and I can say that this receiver will only receive things that are, excuse me, negative 120 decibels compared to a watt, which is again 0.00000000001 watts. So we see why we do that. We see why we have all these numbers. Well, I have a path loss of negative, let's say 125 decibels. Well, if I start off with 1 watt and I need something bigger than negative 120, what happens when I have 125? If I lose 125 decibels on that path and I needed at least 120 to be heard, am I going to be heard?
No.
I am not. I am not. So what can I do to fix this?
Add antenna
Bump up the watt.
gain.
Yeah, I can either bump up the power, but let's say I'm not allowed to by law. What I can do with
Add
an antenna,
bigger antenna gain.
yeah. So what I can do is I can pick an antenna that in this particular direction has a gain of, let's say, 10 decibels, and another one on this end that has a gain of, let's say, 5 decibels. So those are positives. That's actually, instead of loss, those are gains. And I just simply add them together. So I have negative 125 plus 10 plus 5. What's my new number?
110.
Negative 110. Well, negative 110 is bigger. It's close. It's a larger number than closer to 0. It's less negative than negative 120. And all of a sudden, my system that didn't work does work. This is the other kind of stuff that we do when we actually get into building antenna systems and radio systems and understanding why conditions sometimes are good and conditions sometimes are bad.
Are antennas rated by the negative decibels?
They're actually rated in usually gain. Antennas, and we'll get to this, I think this afternoon. A fundamental antenna is called a dipole, which is a half wavelength long. This has 0 decibels compared to a dipole of gain. By adding elements to this antenna, for instance, making it into one of these, a 5-element antenna might have a gain of 10 decibels compared to a dipole in this direction. It's always measured in one direction. So in other words, it will provide you a 10 decibel gain. And we already kind of covered this. 10 decibels is 10 times. It will provide you a 10-time effective power gain in the forward direction. So what that really means in this case is that if I have a 1-watt transmitter, but I'm using an antenna with 10 decibels of gain, that will look as though I have 10 times the power in that one direction. It will look like I'm transmitting with a 10-watt transmitter to the rest of the world. And that's all that really matters, how the rest of the world that you're intending to hear you sees you.
And Scott, is there any way of increasing the receptibility on the receiving end?
Well, yeah, I noticed I put a better antenna there too.
Yeah, so that 1 picowatt would look like 50, I don't know. What is it?
Yeah, it's a little bit more. The 5 is difficult because it's not linear.
Right.
So there are only 2 things that you really have to remember about decibels. 3 decibels is approximately equal to 2 times. And 10 decibels is exactly equal to 10 times. This is the fundamental takeaway of this section. Those are the 2 things that, to be totally honest, even seasoned engineers who do this stuff really need to know. That's all we really know by heart, because you can calculate almost anything from there because everything just adds. So let's say that I have an antenna gain of 9 decibels. All right. So what things do you see there that make up 9? How would you break up 9?
333.
333. And every time you do a 3 decibel gain, what do you do with the power?
Double.
You double it, which basically means that 9 decibels is approximately equal to
2 times 2 times 2.
Right. 2 times 2 times 2. So it's 3 dB plus 3 dB plus 3 dB is equal to 2 times 2 times 2, which is
8.
8x. 9 decibels is 8 times.
Hey, Scott, got a question for you.
Yeah.
Okay, it's funny. I'm looking at a extended antenna from my helium miner, and the antenna I'm looking at right now is an 8 dBi.
8 dBi, yep.
So how would you figure it out at an 8?
Okay, well,
Since it's not.
Well, the other thing is that it's a dBi. I is isotropic.
Okay.
Right? And that is an antenna that has the same gain in every direction, which does not exist. So a dipole, dBd, is equal to dBi plus 2.2. So what that really means is compared to this imaginary antenna, this isotropic radiator, which again does not exist in nature, your antenna is 8 decibels better. So, I mean, if I were to look at that, you could say 8 is equal to 3 plus 3 plus 2. Nah, the 2 is not so great. But, we can approximate that and say that this is 2 times 2 times about 1.5. So it's about 6 times. About. I mean, you can calculate it exactly using the formulas, but really all you need to know is that, 8 decibels is a pretty good antenna, but you also need to know what it's compared against, whether it's like 8 dBd versus 8 dBi. Those are 2 very different things because the dBd is already a higher gain than dBi is. All right, so now that we've covered that, we can say this. So 10 dB is equal to how many times?
10.
10 times.
10 times.
How about negative 10 dB?
Negative 10.
Divided by 10.
Yeah, it's 1/10.
Okay.
Because if we were to write this, 10 to the minus 1 power is 1/10. So essentially by going down 10 decibels, you cut your power by 10 times. So let's say that you have a 1 watt transmitter or let's say that you have 1 watt coming into your antenna, which is a lot of power. You have a cable that has 10 dB of loss. How much comes out the other end?
So it's
minus
1/10 is gone, and you will have
be 10.
0.9 watt.
I want to ask again, what is 10 decibels of loss? That would be
1/10.
negative 10 dB gain.
Hmm.
How much power is that?
0.1 watt.
Yeah, that's 1/10.
0.1 watt.
That's 1/10 times. So if you have 0.1 watt coming in here, what comes out the other end?
0.1 watt.
0.1. Where does the rest of the power go?
In the cable loss.
Yeah, what does it turn into?
Heat.
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 So it's 0.9 watts of heat. So that is also very important factor that if we're talking about conservation of energy, what is power? Power is in watts. What is power?
Energy.
Energy per unit time. What do we know about conservation of energy?
Remain same.
Yep. Energy can neither be created nor destroyed, just changes form. So if I put 100 watts into something, and I know, let's say that I take from a transmitter and I can actually measure at the top of my cable that I have 20 watts coming out into my antenna, how much power am I losing?
80 watts.
80 watts. And it's turning into heat. That is heating my cable. So that may be great if my intent is to keep my cable from getting ice on it, but it's not going to work real well. And that's why it's important to understand what decibels are and how all this stuff works. All right, 5-minute break, everyone.
Okay.
Yep.
I know I need it.
Doing great.
Thank you. Hi, Joel.
Hey, good to see you. You're doing a great job this morning.
Thanks, man.
Hey, Scott, is all this recording going to be available in a link here for review and study later on?
That's the goal. Yeah,
okay, good.
I've been asked to record before, and I'm recording it. So
very good.
All right, see you in 5 minutes.
All right, thanks.
All right, returning. Ask all your questions, everybody. Did we chase anybody away?
You ain't that lucky now.
Well, you know, I have to say that this is actually really good because normally I end up with from the number of people that sign up, I have about a third who never show up.
Wow.
So I want to say, well, you know, it's a free class. You get what you pay for, right? And if you
And Scott, I want to thank you for dedicating so much time of your personal time to this, because you're really helping me out. I need something other than a book to read to get through this stuff.
I'm glad.
Yeah, thank you very much.
Yeah, absolutely.
It is really much appreciated.
Good, good.
Now, who does the exam?
It depends. Oh, that's actually an important point. Okay, so do we have a lot of people taking the exam tomorrow?
I am.
I
Okay.
heard there were 7.
Okay.
I am.
Okay. So the exam, the stuff that I sent out had a link to the Anchorage Amateur Radio Club VEC, which is the remote testing outfit that I work with. I'm also I'm also a volunteer examiner, have been for a long, long time. You're not required by any stretch of the imagination to take an exam online. Depending on where you are, you can also choose, you know, to go find in-person exams, although that's a little harder to find right now because of COVID.
Yeah.
If you're in Eugene, we have a very active group of examiners who are more than happy to set up an exam for you, like a one-person exam. You just have to announce it on the air. Somebody actually mentioned that to me yesterday, that they were going to hopefully do that, and I don't know if they actually got to do it, but I can give you information with regard to that. The other thing is that if you're not ready to take an exam, but you do want to take a remote exam, you can sign up for ARRL or GLARG or Anchorage ARC for any one of the normally scheduled 6-day-a-week exams that they do. So anyway.
I was lucky enough to take my technician exam with Scott back in 2020, the start of COVID. And it was with Anchorage. So at that time, they didn't have 100% virtual testing. So Scott was my VE on location.
Actually had to be there on site. So this by the way, this is Joel, N7JDL. Go ahead and introduce yourself, Joel. You got 15 seconds.
Hi, I'm Joel Lavin. Live here in Eugene, Oregon. Have known Scott for quite some time, but have been involved with ham radio since 2020. And he's been a great mentor to me in the amateur radio world.
Great to know that.
An elder.
Yeah,
Scott, do you
booked
run
an online exam? Go ahead.
Oh, are you going to run any other classes for, general extra stuff like that?
I've never done an extra. I did my schedule is such that, remember I said I do factory automation stuff?
Right.
I travel.
Yeah.
So I've basically been able to, because we haven't been traveling as much in the last year and a half. I've been able to do more teaching because my wife said I need to get another hobby. So so I can kind of, not bother her so much. So teaching has been really good for me. And I just did a general class last month. And that was the first time I've done that. I've done like 25 of these.
Wow.
Over the last 5 years.
Can you skip the technician and go right to general?
You have to pass everything.
That's what I thought. Okay.
How the test tomorrow will be conducted?
How it gets, basically, if you've signed up for an exam, you're on the roster, and because the Because the list of examinees is pretty big. What'll happen is that you'll get a phone call from the session coordinator, and you basically need a computer with a webcam and a phone or an iPad or something, because we need to see your face, and we also need to see the screen and the keyboard. So 2 devices. You basically go in on the phone or iPad without any audio, so that we just get video feed. And we use a site called exam.tools, which if you've done hamstudy.org, it's the exact same site. It's just the official, vetted version.
So basically, they're watching you while you're taking the exam online.
Yep.
Got it.
Yep. 3 examiners in the room with you.
Yeah, I'd have to travel pretty far to take a monitored test. So I'm grateful for the internet.
Well, and actually this remote exams actually started with the Anchorage ARC, because there was a need for people to be able to take exams even before COVID in really remote places. So, I mean, they've been doing it for like 7 years.
Wow.
Well, you look at Alaska, and, good luck finding a team of examiners in like Nome or something.
Yeah, my brother's way up near Eagle.
Yeah. So, I mean, the Anchorage and Fairbanks, you'll find examiners, locally, but good luck outside of that. It's not really practical to fly 3 people up or fly the candidate down just to take a
So
test.
what is the introduction of Anchorage for someone who doesn't know?
Anchorage, Alaska.
Yeah.
I mean, the Anchorage Club, Anchorage Ham Club, what's that? It's for Alaska?
Well, they actually do exams all over the place. So, and they're the ones who are giving our exams tomorrow. So here, like if you haven't signed up and you want to.
Scott, real quick question.
Yeah.
I believe I heard you said you're going to make the recording available of this training. Is that right?
Yep.
And the next question is, any chance that the general class that you just taught is available for viewing?
I think there was quite a bit of it. I didn't get the whole thing. Somebody reminded me like an hour in. Yeah.
If you could send me that link, that'd be great. I'd be happy to watch it.
Okay.
Hey, Scott, I had a couple questions.
Yeah.
If you take the test and you don't pass, is there like a waiting period before you can retake it?
And if you just barely failed it, it's a really good chance they'll give it to you again.
Okay. And the next question is there like an email list we can get onto for the next time you're doing a class like this as just like a way to freshen up again?
Well, I have an annoying habit of everybody who signs up, I just copy them on future stuff.
Cool.
So I've got about 500 or 600 people on that list.
Wow.
So yeah.
Scott, after you pass the exam, how long does it take to get your course done?
It depends who you go through. I mean, if you're doing it
I'm doing it with Anchorage.
because it's on a weekend, the FCC computers don't run
Okay.
until Monday morning. So typically, Monday morning.
Oh, okay.
They've had some issues where it hadn't popped out till Tuesday sometimes.
Okay.
But if it's on a weekday when their computers are running, if they get it in at the, right before the top of the hour, I think their batch runs once an hour. So it could actually be out, 15 minutes later.
Oh, wow.
So
Okay.
yeah, it's pretty fast.
Yeah, I thought we had to wait 2 weeks.
I had to wait. I had to wait for a month and a half.
Wow.
Yeah.
Another good tip on that is to go and register at the website first. So you have an FRN. And I don't know if you're going to go over that, Scott, today, but since we're talking about testing.
But there's basically the FCC has a federal registration number or FCC registration number. You have to have an FRN before you take any exam anywhere. So you need to go sign up for that. And that's
That
just
was in the
basically,
link too.
yeah, just if you go to the FCC website and, you look up, or you just go to Google and look up, sign up for an FCC FRN, it'll take you right there.
Yeah, I have mine. I did that.
Quick question, Scott.
Mhm.
Doing a vanity call sign, usually I looked up online and it says that some people have waited a few months.
No,
Is there, because I've been waiting about 2 weeks.
it's 18 days.
18. Oh, okay. Okay.
Yeah. And actually you can see if it's in process and it made it past the red light authorization
Yes.
and it was available, then you just have to, it's just 18 days.
Okay. So just basically just a waiting game.
And that actually comes from when they were charging and had to wait for money to clear.
Right.
And because the FCC is going to start charging again in the next couple months.
For the vanity call?
Yeah, for any license transaction, including a new license. It'll be $35 with the FCC. So that includes a vanity call. So if you want a vanity call, you should do it before they implement the fee.
Yeah.
What's a vanity call?
What is a vanity call? A vanity call is like a call like, and notice Joel, N7JDL, those are his initials.
Yeah.
So basically, it's like a custom made one, correct?
Right.
Three guesses what my first name is.
Yeah. KO6 Bob.
Yeah. That's awesome.
All right. We are on to schematics, electronic components, circuit diagrams. Okay. What electrical component opposes the flow? We're on page 15, by the way. The flow of current in a DC circuit.
Resistor.
Resistor. It looks like this. That is a resistor. If I make this with an arrow across it, that makes it variable. This is also known as a pot or potentiometer. And a potentiometer will basically have a rating that will be something like 0 to 50 K ohms. Now the little letter K makes sense, right? So it's 0 to 50,000 ohms. But it'll say like 0 to 50 K. So that's known as a potentiometer. Where might you find one of those? For instance, in a volume control circuit. I see Bob's hand up.
I'm sorry, I'll cancel that out. I already got my answer.
Oh, okay. Okay, let's see. What type of electrical component consists of 2 or more conductive plates? Okay, so we're going to draw this. That would be a capacitor. And a capacitor is kind of a weird device.
I'm sorry,
Because-
what page are we in the book?
We're on 15.
Thank you.
So if I draw a capacitor and a battery, and I charge this capacitor up, then all of my plus charges coming out of the plus on the battery will accumulate over here, and all the minus charges will accumulate over here. And once it's completely charged, what can I do? Not a lot. It's just completely charged up. And inside this capacitor, what we have is a space filled with a dielectric or an insulator. And what it does is that, what do we know about plus and minus charges? What do they like to do with each other?
Cancel.
They like to attract each other too before they cancel.
Oh, okay.
So if these plates were allowed to touch, they would pull each other together and they would touch and they would allow the circuit to discharge. However, the spacing in between keeps them apart. So they have capacity. The capacity is how much charge they can store. And they are separated by a material inside, which could be air, it could be paper, it could be glass, it could be mica, lots of different things.
Silicon.
So now, once I charge that up, what happens if I disconnect it? If I disconnect the battery, what happens to the capacitor?
It's just storing.
Start dispersing
It
its
starts
charge.
distributing
where?
its energy
To where?
through the circuit.
Yeah, but what circuit? The circuit that I have doesn't have any place for it to go.
No.
It won't go anywhere.
Heat?
It'll just save it there. They'll just stay there. The charges will just stay there.
Does it
Until they have
have,
somewhere to go.
Stored.
Go ahead,
Okay.
Lucy.
Well, I was reading something earlier where if it was an open circuit, that the capacitor would like leak. Would it be like residual energy? You could get a charge off of it?
Well, I mean, when you say leak, it doesn't have anywhere to go. If you have if the dielectric is good, is solid, you know, if it's a good dielectric and there's very little leakage,
Then it's just
like,
stored.
yeah, it'll be stored. I mean, if you've ever, has anyone ever seen a TV, like the old school TV with the picture tube?
Yeah.
All right, where you had, essentially this was a capacitor. You had one plate and another plate. And this is like a metallized surface. So what would happen if you disconnected a picture tube?
Usually get shocked.
You could get a good solid shock because these operated at 20,000 volts. And you could have a picture tube that has been separated from its television for 10 years and still have a charge on it.
Okay.
Can you explain charge so I can understand it without, you know?
Just this.
Positive.
You just have negatives, which are, I mean, these are electrons. And this is, if you want to think of it, a lack of electrons. Or it has, like, the electrons that are normally floating around in this material got pulled away. And you end up with a positive charge, a net positive charge. So that's it. Just basically, you have a preponderance of electrons or you have a lack of electrons.
Kind of like a battery.
Yeah. So
Okay.
now if I were to look at this capacitor, you know, originally these are just plates of metal, you know, if they're aluminum, they have a set number of electrons in each place, right? Well, if I've got now a surplus of electrons on the one, and I've yanked all the extra electrons away on the other side, I have a charge. Well, if I have, let's say I have a plus and a minus right here, what do those want to do?
Combine.
They
Well,
want to pull each other toward each other.
Yeah.
Well, we're physically holding them apart, but the act of them pulling toward each other creates an electric field. They actually create a voltage in between the two that is trying to pull them together.
Kind of like a Tesla coil, how it would jump.
Yeah, more or less. I mean, it's a high voltage, yeah. But basically, it's just they're trying to make the jump between the two.
Does this work if they're separated by a larger space, or is it they have to be a certain?
If you have
distance?
a larger space, your capacitance will increase. Your ability to withstand higher voltages will go up. So yeah, your capacitance won't necessarily change, but your ability to withstand higher voltages will.
Okay, so if the space is like, let's say 3 meters, just I'm over exaggerating, you need a lot of power to try.
You need a lot of voltage
to get a charge.
You need a lot of voltage to get anything across.
Okay.
And that's why a capacitor, like a really compact, small capacitor, which has, if we were to draw this in real size, which has like that big of a gap, if that was air, you would not be able to withstand much of a voltage across. If you fill it with a different material like glass, even a very thin layer of glass would likely be very much more resistive to arcing than just air. And that's why your capacitors all have a voltage rating as well. So they have a capacity or capacitance, and that's measured in farads, and then they also have a voltage rating. Okay, so your units are farads, and it stores energy in an electric field internally.
So in a practical circuit, Scott, the capacitor can be discharged with a IC of some sort, or like when practical use, what's a capacitor? Storing energy for potential energy to be released back into the circuit, or
usually, yeah. I mean, there are several functions of a capacitor.
Right.
I mean, one is in a power supply as a filter. Essentially, it's a storage and decaying device to smooth out to smooth out voltages. The other thing which we haven't gotten to yet is if you look at how a capacitor is built, right? It's two separate plates. And if you want, I can go into that right now that we're talking about capacitors. You know what? Let's just do that. Okay. This is why I love teaching, because I never know what we're going to get into. All right. So, okay, let's say that I have this battery that I've now drawn. And there's a plus and a minus terminal. All right. The plus of the capacitor charges up to plus, and the minus charges up to minus, right? Okay, once the capacitor has reached full capacity and it's full, how much more charge can I dump into it?
Zero.
Zero, it's full, right? It can't do anymore. Sorry, that should be a minus. All right, now what I'm going to do is I'm going to take this and I'm going to take this battery and flip it. All right, I just reversed the polarity of the battery, right? So what's going to happen to all the minus charges that are here on the right side?
They're going to flow.
They're going to flow back to the positive terminal of the battery. What's going to happen to all the positive charges on the other side?
Same thing.
Negative.
That's right. They're going to flow to the negative. Well, okay, but once that's done, then what's going to happen?
Equilibrium at rest.
Well, no, because you're now going to basically be where we started. And now what do we do? Well, the battery is still connected to the capacitor, right? So which is going to be your new negative side?
Left.
The left. Right? And how about which is going to be the new positive side?
Right.
Okay. And how about if I then take this and I switch it again and I make this the positive? What happens?
It'll just reverse.
It reverses again, and then this becomes
negative.
Oh, so making an alternating current, my man.
Yep. And now this is, so basically what happens to the charge on the capacitor?
It just reverts.
It keeps flip-flopping, right?
Yeah.
Okay, so here's what I call the moment of truth on this. Let's say that I am running this into a black box and I don't know what's inside it. Okay.
Okay.
So this is a black box. All right. And I charge this up. I connect a DC circuit, my battery, to it, and I see current flow. What will happen when what will happen when this thing in the black box, which we know is a capacitor, charges up? When it fully charges up, what will happen?
Nothing.
Nothing.
It'll act like an open circuit.
It'll act like an open circuit. So what happens is, if I were to draw current versus time, I would see that there was a lot of current and then it would drop off and I'd see no current flow for eternity, right? The current would completely disappear. I'd get nothing. This would now look like an open circuit. And what is this voltage known as? What kind of voltage is this? That's DC. It's a battery, right? All right. Now I'm going to take this and instead I'm going to have a voltage source that looks like this. Everybody see that little sine wave in there?
Yeah.
Okay, a sine wave is an indication of what?
AC.
AC. Okay, and what did we just say happens if we put a capacitor in that box and we put AC on it? The current will flow this way.
Only one way, yeah.
But then when it changes, what will happen? You'll have current moving this way, right?
Right.
And then current will start moving this way. As we change, then current will start moving this way. Well, as far as that power supply is concerned, what is inside the black box?
the opposite of what's outside.
What is that? What is that known as?
Capacitor.
Oh no, if I just drew a line.
Oh, short circuit.
That is a short circuit.
Mm.
So if we have AC going into a capacitor, what will it look like?
Short circuit.
A short circuit. But if we have DC going into it, what will it look like?
Open circuit.
An open circuit. Basically,
Yeah.
what it means is that a capacitor has a double life in that it reacts completely differently from AC and DC.
Is the opposite then true for inductors?
Yep. There we go. Here we go with the next one. Okay, so an inductor. Okay, and a capacitor stores energy in an electric field. So what we're going to do now is draw a coil. Okay, so here's the next leap of faith that I need from everybody. Hold up your right hand and wiggle your thumb. Okay, the direction of your thumb is the current. So the current is going in the direction of your thumb. Now take your fingers and roll them forward in the only direction that you can. A current generates a magnetic field. So if I have a current flowing in this direction, I have a magnetic field that will go on top, it will go into the page, and on the bottom, it will come out of the page. So it looks like this. So I have a magnetic field that's making loops out from the bottom and back behind. If I were to reverse the current, the magnetic field would come out this way and dash line this way. Okay, so if a capacitor stores energy in an electric field, how does an inductor store energy? What do you think?
Magnetic field.
In a magnetic
magnetic
field.
field.
That's right. And in fact, if I have a coil and the current is flowing this way, basically my magnetic field looks like this. You may have actually seen something that looks like this in the form of an electromagnet. That, you know, you take like a nail and you wind a piece of wire around it, and you can pick up paper clips. That's called an electromagnet. That's a DC electromagnet. It generates a magnetic field and it has a north and a south pole. All right, so once that energy is created, what do we know about energy?
Cannot be destroyed.
Cannot be created or destroyed. It just changes form. So if we have a battery that is now pushing a current through this coil, everything's happy. What happens if we then separate the battery and a capacitor? What happens if we have a capacitor and disconnect it? It stores a charge, right?
Right.
What happens if we disconnect an inductor?
It stores the magnetic energy.
Not
It
very well.
collapses. It
Not very
collapses.
well. There's nothing to support it. So what ends up happening is that this energy, which is now floating around in here, it's like, okay, well, what do I do now? There's nothing to support this magnetic field, which basically means that now I have this magnetic field floating around here and there's no way to get rid of it. Well, unfortunately, there is a way to get rid of it.
Could you ground it?
You can put a diode across it and give it a path to go, or what will happen between these two terminals? It's energy between two terminals. And how does it dissipate energy?
Heat.
Heat and a spark. Anyone ever heard?
Sap.
Anyone have a car that's old enough to have points?
Yep.
Oh.
That's what points are.
Oh.
Basically, what points are is that if you have a coil in your ignition system, you charge up the coil. You basically you run the coil, and then you break the coil open. The points create a gap, and all that magnetic field energy has to dissipate somewhere, and you give it those points. The points are then connected to the spark plug. You generate your spark, it travels down and ignites your fuel. So that's actually using magnetic field energy for good rather than evil. The problem then, of course, is that if you have a magnetic field like this, what did we say happens if you hook it up to DC?
Turns into a open circuit.
No, it turns into an electromagnet. That's
Oh,
actually, but it looks like this. Maybe a little bit of resistance there to limit the current, but really it's basically a short circuit.
Short circuit.
Short circuit.
Right? So if you were to try to stick an alternating current into here, you would be continually building and then collapsing the field in here. You'd be having it try to switch direction. And what we determined is that a magnetic field doesn't really like to change. It fights it. It fights back by trying to put voltage out onto its terminals, fighting the change. So what that means is that an inductor, which has inductance, and it's measured in henries, and its letter is L, stores energy in a magnetic field. And if we try to connect this to a DC circuit, an inductor will pass DC, and then a capacitor will pass AC, and an inductor will block AC, and a capacitor will pass, but will block DC. So, can you guys see where this could actually be profound and really important? Let's say that we had a circuit where we had question mark volts, and it's a combo of AC and DC. You don't know what it is. Well, okay, we can do this, and we can do this. What would go out this way, the AC or the DC?
Which way?
Out to the right.
DC.
That would be DC. What would go down through the capacitor?
AC.
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 What have we now done with this?
Splitted the paths of AC and DC.
Yeah, we've actually been able to separate AC and DC. This is really important if we're building a power supply. Because what are most power supplies run off of?
AC.
You plug them into the wall, right? And what do they produce?
DC.
They produce DC. You plug this into your computer is not going to be real happy if this is an AC, if this thing is producing AC. It wants nice clean DC. So inductors and capacitors are the fundamental building blocks of things that we know as filters. And these can operate in the extreme, in which case they completely block or completely pass things. They can also be used in somewhere in the middle of their ability to do that, in which case you can actually pass just certain frequency bands and separate different frequencies from other frequencies.
So it's used for radio signal mixing and stuff too.
Oh, all kinds of stuff.
Yeah. So is that what's meant by switching power supply?
A switching power supply actually is a power supply where, actually, I think that's like the next section.
Okay, I didn't want to.
It's coming up really, really soon. Okay, we'll get to that, I promise. Okay, so we're looking at batteries here. Let me close this. All right, so batteries, chargeable versus or rechargeable versus primary or non-rechargeable. Batteries that are rechargeable include like lithium ion, alkaline, or sorry, like a rechargeable alkaline, not your standard alkaline. Nickel metal hydride. You know, the battery on the back of this radio, notice it has charging pads. This is a lithium ion. This is a NiCad or a nickel metal hydride, depending on which one it is. A lead acid battery in your car. Thank goodness it's rechargeable. Right? So that's what your alternator does. Your alternator recharges it. A gel cell is a special form of a lead acid battery. A primary battery that isn't rechargeable, alkaline, carbon zinc, That's your old battery that was labeled as heavy duty, which really wasn't. A silver air battery used for hearing aids. That's not rechargeable. There's also another kind of battery that's not rechargeable. It's a lithium metal battery. That's typically like you see like a coin cell or a button cell.
So that's,
That'll run for 10 years, but it's not rechargeable. But please recycle them. Please turn them in because we need all the lithium we can get. Electrical component used to connect or disconnect electrical circuits is known as a switch. And finally, something that's used to protect other circuit components from a current overload is known as a fuse. And we're going to get to that really, really soon. All right, so now what we're going to do is do that right now, actually. We're going to draw a 120 volt circuit and draw the little black box here. And here's a resistor. And this will be, let's say, 10 ohms. Okay.
what page are you on now?
Oh, I'm just winging it here.
Oh, okay.
Okay. So if we have a 120 volt AC, a volt circuit, this is called ACRMS. Essentially, this is 120 volts AC. Let's do our Ohm's law again. E, I, R. What would our current be? Everybody?
12 amps.
That'd be 12 amps because we don't know this one. E divided by R. 120 divided by 10 is 12 amps. Okay. So now, by our calculations, what would the power dissipated by that resistor be? Going to use the other part of Ohm's law, PIE. We don't know the power. We have I times E is 12 times 120 is 1,440 watts. Everybody agree with that?
Yes,
Okay, 1,440 watts.
that's a lot of parts.
It is, but it's also not. You find this in your house. What would this be known as?
Heater.
A heater or a toaster. Yeah.
Yeah.
It generates heat on purpose.
Yeah.
Well, it draws 12 amps and generates all that heat. Okay, so now we're going to screw this thing up. We're going to say that, oops, we had a problem. There was something that went wrong. We're going to make this now 6 ohms. Okay, how much current are we now pulling through that circuit?
20 amps.
20 amps, because 120 divided by 6 is 20 amps. So now we're pulling 20 amps. And how much power are we delivering?
2,400 watts.
Yep.
20 into 6, 1,200.
So we're on 2,400 watts. Right? So we're now pulling 2,400 watts, which means we're putting out way too much heat. And also, if I've done a good job with my engineering, and this circuit was originally designed to be a 12 amp circuit, what size wire did I put in there? Because I'm trying to save my company money. This is probably number 14. Right? Because why would I put more expensive wire in when I never needed it? Now, how do I protect this wire from ever seeing more current than it should ever see?
Circuit breaker or a fuse.
I put this thing in called a fuse. And the fuse, I would, let's say, put in like a 14 amp fuse. So if I could see a little bit of an overload maybe, but at some point it would trip. I could also, let's say, make it a 12 amp fuse or circuit breaker, in which case, basically at 12 amps, if everything's running fine, it's a calibrated device that's designed to prevent current overloads. Because what did we just say would happen if you pulled, if your current went up too high? What would happen to your power?
Your power's going to drop.
Your power is going to go up.
No, right.
If your current goes up, your power is going to go up. And all of a sudden,
sure.
this number 14 wire in your wall is carrying more current than it's used to carrying. And what's going to happen to this wire?
Gonna get hot.
Fire.
It's going to get hot and it's going to burn your house down. Exactly. So That is why it is very important to replace fuses with the exact same value of fuse or circuit breakers the same way. Because in doing so, you prevent a fire. That is the main purpose for putting a fuse in a circuit. It is to prevent a fire. Okay, we're now on to diodes. Okay, so we're on to diodes. A diode has a plus and a minus terminal. And this is a cathode. And this is an anode. And notice that we actually have a plus and a minus. So if I were to hook this circuit up to something which had a plus and a minus, that would actually allow current to flow. And internally, what this looks like is what's known as P material and N material. Those are our pluses and those are our minuses. And what these are typically is a semiconductor such as silicon, which isn't a conductor and it's not an insulator. It's somewhere in between. And that's because in its outer electron shell, this has 4 electrons out of a possible 8. So it's kind of halfway in between. So by taking the silicon and putting in some other materials that have too few electrons, we can make this sort of behave kind of positive-ish. And by putting in materials that have a couple of extra electrons floating around, we can make this negative-ish, which basically means that if we try to put electrons into here, they won't go. If we do try to put electrons into the left side, that'll work. And they'll actually get to this point and they'll pass on through, which basically means we now have a one-way street in the direction of the arrow. And what's cool about this is that now we can take things that are going only in one direction and pass them through and block the other ones. Okay, so we have an anode and a cathode. If we were to build this end of the diode would typically have a stripe on it, so you can tell the difference between the plus and the minus terminal. And when you put it in the circuit,
normally went on the positive terminal.
What?
I thought the stripe normally went on the positive terminal.
Nope.
On the anode.
Nope, the stripe goes on the negative. Stripe goes on the negative.
Yeah, it's on the negative.
It's on the negative, on the cathode end.
Cathode has this stripe.
Yep. Okay, so a very special kind of diode looks like this. And you may find one on your phone and it looks like that. Anybody know what that is?
Light emitting diode.
That is an LED or light emitting diode. And by putting a forward voltage across it, that allows current to flow. And instead of just allowing current to flow, there's a separate layer inside that when current flows across it, it causes it to emit light, visible light. Although it doesn't have to be visible. It can also be infrared or ultraviolet. If it is visible and we have let's say a circuit that's turned on with a plus and a minus, then this can be an indicator that the circuit is on. We basically see the light come on. All right, next circuit is going to be kind of like a little back-to-back diode thing. And this is known as a transistor. And in particular, this is a bipolar junction transistor. Oops. A BJT. And the way that this works is that it has 2 different materials. So this is an N and this is a P and an N. Remember that from P to N, you get current flowing. If we were to draw our diode, it would look like this, where this is our P and this is our N, and current flows that way. Well, notice we have inside here a P and an N, but now we also have this additional N thrown in there. So the way that a transistor works is that it is a pair of back-to-back diodes. And by putting a voltage, so N, P, N, by putting a voltage here between here and here, that causes a current to flow. And in doing so, if we put a voltage here, this is still our negative terminal, what we get is a lot of current flow this way. Much, much bigger. So essentially this can function as a switch. This can also function as an amplifier, depending on how you're running it. And this again is known as a bipolar junction transistor, or BJT. It has 3 terminals. This is the base, this is the collector, and this is the emitter. And the important junction here is the base to emitter junction. By putting a bias voltage across that, because it can only be in one direction, it has to be plus and minus like that, that will cause this other channel to basically open up like a waterfall.
Forward bias.
Forward bias. So what would happen to this thing if I switched it around and did this? And I reversed the
Reverse
bias.
bias. No conduction.
It would completely turn off. This is actually really important because this allows me to basically have a switch that all I have to do is control these points right here. That circuit, and that separates it out and determines what happens this way. So essentially this, if you want to think of it, this becomes sort of like a water valve, where you just turn the valve slightly, you open it slightly, and the water just pours out. If you open it more, the water pours out even faster.
Okay, so it doesn't, it's not a one current going to like to a T at an intersection, but it's two currents going to one.
Yes.
Okay, so the top is bringing current from another circuit somewhere else as well.
So this would be your VCC. That's your main circuit voltage, if you want to think of it that way.
It's almost like a regulator. It'll regulate the amount of voltage flowing through.
Well, it regulates the amount of current flow.
Current flow, correct.
Yeah. What's nice about this is that you now have a function where something that's very small can make a very big copy. Well, and what is the act of taking something small and making it very big known as?
Increasing.
Gain.
Amplitude. Amplifying.
Amplification.
Amplification. You're making a bigger copy of something. And the amount of gain, it's called gain, can be measured in decibels. And each transistor actually has a transfer function known as beta, which is the amount of amplification that it can provide, output to input. But you don't have to know that. Okay, so transistor can be used as an electronic switch or amplifier. It can amplify signals very well. We're on page 18, by the way. It is the primary gain producing component in an RF power amplifier. And the ability of something to make a bigger copy is amplification, and its functionality is gain. And again, that can be measured in decibels. So how many different layers of semiconductor material make up a transistor?
3.
It's 3. It's a sandwich of 3. Okay, so now I can actually draw this a slightly different way. Remember how we did that before, where we had an NPN that looked like this? I could actually draw it like this. Well, if it was working like this before, this new one actually is drawn like that. And the flow would have to be that way instead of that way. These transistors are known as NPN, and the other one would be known as
PNP.
PNP. And if you're ever wondering how to remember which is which, okay, so which one of these is pointing outward?
The first one.
The first one.
Would you say
Left
it's not?
side.
Would you say it's not pointing in?
Right.
Would you agree with that? It's not pointing in,
Yeah.
not pointing in.
Hmm.
That's how you remember which
NPN.
transistor is which. NPN, not pointing in.
Okay.
Okay, so here's another one. If I were to instead draw a circuit that looked like this,
FET.
That would be a FET or a field effect transistor. And now I want everyone to notice what this looks like right here. It looks like a capacitor, doesn't it? Okay, so what would happen if I put a bunch of pluses here? What do you think would be attracted to the other side?
Negative.
Negatives, that's right. How about if I did the opposite?
It'd be the opposite.
It would be the opposite. So if I put negatives over here, I would get positives attracted over here. So if that were the case, then essentially this works by changing what's happening on the other side. And when you put a voltage across here, that determines whether or not it allows current to flow. And this is a different kind of transistor called a FET, or field effect transistor, because what do we have inside that capacitor? We have an electric what?
Field.
Electric field. So this is known as a field effect transistor. It allows the channel to open and close based on how much electric field is being generated inside. And because of that, how much current actually flows into this terminal. It's almost nothing. And that's why most electronic devices like phones and such, they use FETs. They don't use bipolar junction transistors, because a bipolar junction transistor will use current, like a lot of it. Something like a FET uses almost nothing. Much more efficient. All right, here we go. What we're going to do is share this screen right here, assuming that I can. I hope I can. Yep, looks like I can. All right. Can everybody see this picture?
Yeah.
Okay, so this is the picture from page 19. Okay. And this actually is really important because this actually will show us exactly why what we've just studied is the way it is. Okay, a schematic is the way that things are shown on a piece of paper, how you would show an electrical thing on a piece of paper. Essentially how everything is interconnected. So, all right, who recognizes number 1?
Resistor.
Resistor. How about number 2?
Resistor BJT.
Okay, is it an NPN or a PNP?
NPN.
NPN because it's not pointing in. Exactly. Okay, number 3 is a light bulb, and how about number 4? Battery. Okay, so the way this circuit works is that you basically have a voltage that comes in on the left-hand side. What's terminal? What's the thing marked number 5 there?
Ground.
That's a ground.
Grounding.
Right, that's our reference of 0 volts. Okay, so here we go. As we come in, if the voltage is on, the voltage is positive, we have a path that goes that way. If our path goes that way, what's going to happen from in the other direction? Essentially, that channel becomes open, and we can start right here. We go up through this light, and we come down this way because this is now open and turned on. And what do we get? We get current flow through the light bulb. So what happens?
It turns on.
Turns on the light bulb. How about if we remove the voltage coming into that transistor?
The light goes off.
Light goes off. Exactly. Okay, so that is an electronic switch. That's a simple electronic switch. All right, next one. Let me switch back to mouse. Okay, so we're on the next page. Okay. Now, who was asking about a switching power supply?
Me.
Okay. All right, here we go. All right, so now what we're going to do is we're going to start here, and coming in here is a sine wave. Right, that's plugged into your wall. All right, element number 2, what's number 2? There should be
Fuse.
one, and that would be a fuse because there should always be a fuse. Number 3,
Single pole, single throw.
Single throw.
that's yep, so basically a switch, single pole, single throw switch. How about number 4?
Transformer.
A transformer. Okay. I am going to talk about transformers a little bit because it's really important. All right. So what a transformer does is the way that a transformer is built is that you have a coil. All right. What does a coil make? Magnetic field, right? And because it's AC, what will the magnetic field be doing? It'll be going that way, then it'll be going that way. It'll be switching back and forth, right?
Right.
Okay, so even though a coil doesn't like AC, you can shove energy through it. You can do it, right? So when we said that it looks like a short circuit, it's not completely a short circuit. We're actually using it in its useful area now. So now what we're going to do is we're going to draw an iron core, and we're going to wrap our wires around the iron core. So if you wanted to make a magnet, wouldn't you say iron is a good thing to do? Good thing to use?
Yeah.
Iron is really good at constraining magnetic fields. So what this does is it takes the magnetic field, which would normally look like this, that would be floating through space, and it constrains most of the magnetic field energy in the core, right? So most of your magnetic field goes through the core. All right, so now what we're going to do is we're going to wrap another set of wires around this. So what happens when that set of wires experiences a magnetic field going through the center? What do you think will happen?
Induction.
Yeah, if
Electricity.
a current makes a magnetic field, what does a magnetic field make?
Current.
A current, yeah. So basically what you've done is that you have a current going in one side, being converted into a magnetic field, and then a current comes out the other side. But more importantly, there's no reason that this has to be 1-to-1 ratio in turns. And in fact, you can do that. That would isolate the two sides. However, what we usually do with this is we would make, let's say, 10 turns on this side versus 1 turn on this side, or 100 turns on this side and 10 turns on this side. So what this
When
does,
you say turns, you mean like coils?
like a coil around the core,
Okay.
a turn of wire. So what would our ratio be from one side to the other?
10 to 1.
10 to 1.
10 to 1. If I have 120 volts AC over here, it only works with AC. What would I get on the other side?
12 volt.
I would get 12 volts AC.
Minus
And-
decibels, isn't it?
Yeah, exactly. Well, that's in voltage, but how about power? How about current? Let's say I had 1 amp over here. How much would come out the other side?
0.1.
No, I'd have 10 amps.
10
Because
amps.
what do we know about power and energy?
Okay. Same. Okay.
Energy can neither be created nor destroyed. So if I have 120 watts over here, I better have something close to 120 watts over here. So what that means is I can now take this 120 volt coming in and I can produce 12 volts coming out. Now I also have to be prepared that the currents might be awfully high on this side. So the wires are going to be a lot thicker on the second. This is known as the primary,
If you wanted to keep going, then
and this is the secondary side.
So to switch it to DC.
Nope, it's all AC. So
No, I said if we wanted to switch it to DC.
Yep.
It's an open-ended question.
Yeah, well, we're getting there. We're going back to that. Okay, so now what I've done is I've changed the flavor of my AC circuit. Right now, can you think of another reason why you would ever want to do this?
This would be a step-down transformer.
Yeah, there we go. Who works for an electric utility?
I work in BMS, so
Okay. There was somebody who actually worked for Austin Electric Utility, right?
Yeah, I do.
So
Yes.
let's say that I have this with a whole bunch of turns. Right? And now I didn't draw that very well. Let's do it again. Here's my transformer. And I have like a whole mess of turns over here and like 2 turns over here. And my turns ratio is 200 to 1. And I have, let's say, 120 volts. Let's say I have 120 volts AC over here, and I have a 200 to 1 ratio. I will have 24,000 volts over here. So if I have power coming in at 24,000 volts, I'll have 120 volts coming out. So if I were to draw, let's say 100 amps, or let's say 200 amps at 120 volts, I will have how much current over here? 1 amp. And what do we know? E is equal to I times R. If I assume that I have a resistor in my wire, and I only have 1 amp of current, how much voltage am I going to lose? It's not very much, right? If I had like, you know, 1/10 of an ohm, I would lose 1/10 of a volt.
Yeah.
Which is nothing because I'm already operating at 24,000 volts. But if I were transmitting on the other side and I had 200 amps and I had that same 0.1 ohms, I'd lose 20 volts of the 120 that I have, which leaves me with only 100. That's not a very good system. So that's why utilities transfer power at very high voltage and low current. And a transformer is what makes that possible. A lot of your transmission lines will be operating at, you know, 300,000 volts for that very reason. All right, so let's go back to this over here. Okay, so now what we have is we're going to draw. We have our transformer. All right, so we have 120 volts coming in on the left-hand side. What maybe do we have coming out?
120.
Oh, going in.
12.
Yeah, let's say this is 10 to 1.
Oh, okay. So it'll be 12.
That'd be 12 volts, which is great because we can do something with 12 volts. And it's AC or DC?
AC.
AC, that's right.
AC.
Okay. Now we're going to draw our AC voltage. Okay. And now what's going to happen? We're getting to a diode. What do we know about a diode?
It only goes in one direction.
Rectification.
That's right. It only goes one direction. So what happens if our voltage gets down to the negative side? What happens
It
to the
does
diode?
not conduct. Open circuit.
It opens circuits. So our new voltage doesn't look like that. Our new voltage looks like this. Does that ever go negative, everybody?
No.
It's never on the negative side. So what we have now is very ugly direct current. Okay, so who was asking before about a capacitor and it building up charge, and then when the
Me.
voltage goes low, it spits some of it back out. What happens is that at the voltage peak, the capacitor will charge up. As this voltage drops down to 0 here, the capacitor will take over and start to decay, and it won't go all the way down to 0. So it'll filter out some of those big, ugly, noise-looking things.
What does number 1 symbol say?
That's like somebody has a circuit that plugs into the wall. What? I'll be there in 5 minutes.
Battery.
Yeah, that's basically somebody plugging into AC in the wall.
Oh, okay. It didn't look like the regular symbol.
No, it's not. I could
Okay.
actually redraw it and look like that.
Okay.
So now if the power is on, you'll have voltage here. The LED will turn on. Then you have a voltage and current limit here. There's a variable resistor. And now this right here is a very special kind of diode. Notice it is a diode, but it seems to be going in the opposite direction, right?
Zener.
That's a Zener diode. That's right. Notice it has the little Z looking thing on it if you turn your head sideways. What a Zener diode does is if it's, let's say you have a voltage that's bouncing around like this, a Zener diode that is rated at a voltage that is this line, for instance, will clip everything above and send that to ground.
Oh,
So it will take all the voltage above a certain point and send it to ground. And the end result is a voltage that's relatively flat. And that is kind of like the basis of what makes a DC power supply clean. All right, so finally,
Zener conducts in the opposite direction.
yeah, a
So
zener basically is working in the reverse direction.
reverse direction. So it takes the positive peaks down by conducting that current.
Yep.
So the positive peaks are kind of sort of averaged down to the DC level.
Yeah, for everything that exists, there's an exception. The Zener diode is the exception. It's a special diode. Okay, let's see, transformers. Okay, so the act of taking AC and turning it into DC is known as rectification. It literally means, to rectify something, to make it right, to make it correct. So it takes something that's bouncing up and down and flips it over and makes it look right. It turns it into DC. Okay, next circuit, we're on page 21. Okay, so notice this circuit right in the middle. This is actually a really important circuit. Okay, what is element number 2?
capacitor.
Capacitor. A variable capacitor. It's an adjustable capacitor. How about number 3?
Variable inductor.
Variable inductor. Okay, and the one that's unmarked is another variable capacitor. And number 4 is an antenna. All right, so what we have here is an antenna matching circuit. It's an impedance matching circuit. And remember we said that our capacitors and our inductors acted like short circuits and things like that. Well, in fact, they don't, that's in the extreme. In their more functional operating range, there's something that we have which is called X, which is reactance, which is also measured in ohms, oddly enough. And a capacitor and an inductor both have this thing called reactance. Reactance is how something acts in the existence of alternating current. So this reactance with resistance combine to form something called impedance, which is how something reacts overall in the presence of alternating current. So these two things create something called impedance, which again is how something reacts in the presence of alternating current. Now, we have our resistance and our reactance. And basically, these are perpendicular things. And if we were to draw our resistance and reactance as vectors, you're not expected to remember this. This is our impedance, and this is also causing a phase shift. But basically, if you think back to the time that you did the Pythagorean theorem, where if this is 4 and this is 3, then this is 5.
Yeah.
This is how we calculate our impedance. Now, it is true that every inductor, because it is still a piece of wire, is going to have a little bit of resistance. And every capacitor will have a little bit of resistance too. It does. But the reactance of a capacitor is 1 over 2 pi FC, or actually negative. And for an inductor, it's 2 pi FL. Now, the thing that you see there is that in addition to frequency, you have the values of capacitance and inductance in both of those things, right? Which basically means how far up or down this goes in the X direction is a function of how big these values are. So by picking them, you can make them equal and opposite and cancel each other. When these things cancel each other, this is known as resonance.
Resonant circuit.
and that becomes a resonant circuit. Capacitors and inductors are really, really useful when dealing with something called resonance, when you use two of them together.
Looks similar to the right-hand rule used for a directional antenna, right?
Sorta.
The XRZ.
Well,
relation.
yeah, I mean, basically if you have, yeah, yeah, exactly. So basically by doing this, we can actually take, we can actually have an impedance as shown in this number 4. The antenna represents an impedance by running it through a capacitor. And then let me make sure that's up on the screen. Gotta go switch to that. Here we go. Okay, by starting with number 4, that actually has an impedance. And then by adding it to the impedance of the capacitor, we change it to a certain number because they add. And then those become in parallel with the inductor, number 3, which is then in series with number 4. So by doing that, what we are able to do is, let's say that we have a radio that is looking for an impedance of 50 ohms resistive, and we have an inductor and a capacitor and a capacitor and an antenna that are some unknown value. So the antenna, in combination with the variable components, can be adjusted so that the radio is then happy. It sees a combination of series and parallel circuits that make it look like something that it's really not. The end result of that is that your transmitter is now happy and dumps lots of power into it instead of burning it up as heat and blowing up your amplifier. So
Would this be an antenna tuner then?
that is exactly what that is. That is an antenna tuner. This circuit that's being drawn is an antenna tuner. So that's why it has variable inductors and variable capacitors. So an inductor and capacitor connected in series or parallel to form a filter. That is a resonant or tuned circuit. We use them all the time. And somebody's phone is ringing. Okay. Finally, component number 4. Component number 4 is an antenna. That's the one that's way up here, up in the sky. All right, so that being said, what we'll do is just go through this last section real quick. This is nothing complicated. This is other components. A relay is a switch that is controlled by electrical means. So basically, if you have an electromagnet and it snaps a contact into place, that's a relay. We already sort of covered this. A device that displays an electrical quantity, such as voltage, on a display is a meter. A device that contains several semiconductors and other components in one little package, like something that's the size of my pinky, might have a billion transistors on it. Coming! Might have a billion transistors on it. That's an integrated circuit. A circuit that controls the amount of voltage from a power supply is known as a regulator. So you might have a power supply that puts out 17 volts without a regulator. If you put the regulator in, you get a nice clean 12 volts, such as what the Zener diode would do. And finally, when connecting electrical assemblies together, we use one or more conductors. What do we know about any wire that carries current? It generates what kind of field?
Electromagnetic.
A magnetic field. A magnetic field, if another wire is in it, will do what? It'll make a current. So if you have two wires, in parallel and they're not kept from each other, what will happen to the two wires in parallel? This one will conduct into this one and vice versa. The signals that they're carrying will do something called crosstalk. And you'll end up combining your signals into a big mess. And that's why we use shielded cable.
Right.
The shield protects the two. Yep. The shield keeps the two apart. And it is lunchtime. And how about half an hour?
Okay.
Is that good?
Sure.
All right, everybody. Good work. Think of questions.
Don't eat nothing. You hear me? No eating shit. I'm watching you. Duck, you wanna go out? Yeah, you wanna go out? Mm. feel better now, buddy? All right. It's all right, buddy. It's okay. Dr. B, you want to go outside for a little bit? Come on. Cut, cut. Cut, come on. Come here. Come on, Bubby.
I don't want to go. I don't want to go.
All right. Anybody got any questions? We're not starting yet, so that's a good time to tell. It's a good time to ask.
Yeah, I'm confused by decibels. I always thought decibels were sounds.
They are.
And we have decibel loss
Yep.
in radio waves that
Yep.
are electromagnetic fields traveling at the speed of light. How does
Yes.
sound waves affect that?
Yes, they don't. They have nothing to do with each other.
So how does the loss happen?
Well, I mean, is the question, how do radio waves attenuate, or is it how do decibels equal decibels?
How do decibels affect radio transmissions is, I guess, where I'm starting from.
Okay. So picture, okay. Picture, if you will, a point in space. All right. And you have 1 watt transmitting from that one point in space in all directions. With me so far?
Yep.
Okay. Now, as you spread outward, how many watts do you have going through any surface that you can draw around that first one, around that dot?
1 watt, I would assume.
1 watt. Okay.
Because you're in space. There's no
Right. There's nothing slowing it down. All right. So now, how about if you make that sphere, that surface, 1,000 times bigger? What's the total amount of energy going through it?
It'd still be 1 watt, I would assume.
That's right. But now, let's say that your antenna is, oh, I don't know, the size of this dish that I'm holding up.
Okay.
Right?
Mm-hmm.
Does it make any difference how big the sphere is where you're measuring it? It better, right?
It should, I guess. It
Yeah.
could.
Okay. So the question is, if you are right next to the thing that's transmitting, how much of that 1 watt are you capturing in this bowl?
The closer you are, the more of it you get.
That's right. And that is what we're measuring. It's not really loss exactly. What we're measuring is how much weaker the signal is because it's dissipating. It's being spread out.
Why is that measured in decibels?
Because that's the easiest way to measure it.
So Scott, let's put that as path loss. So the amount of energy radiated at the antenna, at the radiating antenna, transmitting antenna, and then this point B is your receiving antenna, and whatever is in between, that is the path loss.
Right. Well, I mean, if you think of it, yeah, there's something that's going to, I'm assuming going through empty space.
Free space path loss, yeah.
Right.
That's how we call it.
Yeah.
Yeah.
But I mean, there are, you know, if you look at the atmosphere, there are things in the atmosphere, like let's say that you have a foggy day and you're using microwaves.
Correct.
Right? Microwaves absorb, you know, microwaves get absorbed by water to a certain degree. They get attenuated. So that would figure into your path loss. But if you're just going through empty space when you don't have any loss per se caused by the medium, what you're really experiencing is what happens to your signal. I mean, you know, like the Voyager space probe is still going, right? It's transmitting at 25 watts at a distance of, I forget, what is it, 12 billion miles away. So if you were to look at its transmitting power and then figure out how much of its transmitted energy is actually being captured by an aperture here on Earth that's receiving it, you would measure that and you might get, you know, 160 decibels of loss or something like that.
Yeah.
It's not really loss. It's just how much of the signal is getting to where it's, you know, where you expect it to be compared to how much is getting out.
This is exactly, you know, when I introduced myself, I said I work for the cellular telecommunication. So this is exactly what we say. When the cell tower is transmitting something like 43 dBm, and your cell phone receives like minus 85 dBm, is a very good signal.
Right.
Minus 110, minus 120. So all of that, even the weather conditions are good, we term it as free space path loss. And there are formulas for that, which take into account the frequency and the distance. Minus 10 times log of frequency, minus 10 times log of distance. Yeah.
Right. I have my phone in my
Hmm.
hand. My
Yep.
phone, my hand attenuates the signal.
That also right. That also
You know,
right.
I mean, it's local
Yeah.
things. It's all kinds of things, and it's all
Yeah,
measured in depth.
in
So-
building penetration, in car penetration, and vegetation it takes some of the signal away. If you are in dense vegetation, that also counts.
So
And there are so many other factors of the
guess what I'm
path loss.
Yeah, go ahead, Matt.
trying to get at is that my mind keeps wanting to measure decibels as a measure of how loud something is, or volumes, or something like that in sound.
That's only because that's the way you know it. The decibels is just a ratio. It's a way of comparing one thing to another, whatever those things are.
So in radio use, why don't we say I'm transmitting at 10 watts, and because you're wherever you are and all the path loss issues there are, you're receiving me at a quarter watt. Why don't we look at it that way?
Because we're never that high. The numbers are never that big. So
if we were to do that, then I would be saying I am transmitting 1 milliwatt, and Scott, you are getting a 0.125 picowatt, and
Right.
your mind will be blown away by what I'm saying. So
Right.
the decibel scale provides you an adequate manner of thinking, actually.
yeah, so the way that I think about it is like, so let me go back online here with okay, let me share this. This is a good segue. Okay, ready? Matt, you watching? Can you see it? Okay.
with you.
Okay. So let's say that I have 50 millivolts, or sorry, 50 microvolts, right? 50 microvolts coming in down the antenna line into my radio. Okay. And my impedance is 50 ohms. All right. So I could actually do power level stuff. It's E is equal to IR. Through some manipulation, it's also V squared divided by R. Right?
Yep.
So if I were to do that, it'd be 50 times 50 times 50 divided by 1,000,000,000,000,000, which is actually 1.25. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's 125 nanowatts. That is a full scale signal on my radio.
Okay.
125 nanowatts. But the trick is that it doesn't matter what the sending station is transmitting, because I don't know what the other station is transmitting.
Right.
Right? Now, to a certain degree, I don't care what the other station's transmitting. All I need to know is that if I'm receiving that much power, that's a calibrated value of S9 on my meter. And that every X amount lower than that, every S unit is a change of, let's say, 6 decibels, which I think it is.
What is S9?
S9 is a full scale S reading on a receiver.
Okay.
So the reason that we use decibels, I mean, a decibel is just a way of comparing something to something else. And very, very often in radio, we use something called the dBm, which is a dB compared to a milliwatt. So in this case, 125 nanowatts would be 0.125 microwatts, which would be, let's see, 1, 2, 3, 1.25. Well, let's see. So I mean, basically, what you're left with is dealing with all these numbers. 0.000125 milliwatts. So that would be like negative let's see, 10, 20, 30, and minus 36 dBm. So it's a lot easier to explain things in decibels than it is to say that if I'm just barely hearing something, that at S1, my minimum discernible signal is 0.000. This is actually like true. 0.000000001 watts. That is actually true. That is typically going to be something like the weakest signal I can hear on my radio. How do you reckon that number? Right? I mean, it's really hard. But I can say that it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I can say it's minus 140 dB or minus 110 dBm.
I see. So it's just an easier way of dealing with these decimal points.
Yeah, I mean, you have all these zeros. And the nice thing about it is once you've converted it to that, then you can just add your decibels. You know, if you have a system that you're designing and you have 1 watt of a 1 watt transmitter and you have a gain, and then because of what you're doing, you have path loss, and then you have gain here, and you have cable, which has loss in the cable, and then you have loss in the cable, and then you have what we would call an MDS, which is minimum discernible signal. If your signal that comes down measured right here is greater than your minimum discernible signal, you have a functioning system.
Right. That makes sense.
So if you can characterize what your path loss is, and you know what your antenna gain is, and you know at a given frequency, this cable that you've chosen is going to have a certain amount of loss, and you know that you're 3 decibels below the MDS, you will hear nothing. So what can you do to fix it? Well, you can't do much with this because that's nature. But you can do something with this cable. You know, maybe you shorten the cable, that reduces loss. Maybe you go and buy more expensive cable. Maybe up here, you put a preamplifier right at the antenna, and that boosts your signal. That's what cable TV systems do. When the guy came out to check my cable, he said, we need to put a preamp over there and we need to replace your cable. That's exactly what he did to bring my signal up to the point where I didn't have dropouts inside the house.
Cool. All right.
So, I mean, this kind of stuff applies everywhere. So it's not necessarily for the exam, but it's as soon as you start to do stuff, it'll help you understand everything.
Cool. Thank you.
Speaking of the exam,
yep.
I'm in college. Most of the calculator I'm using is a TI-89, which I can't imagine is allowed.
Yeah, you don't really need a calculator.
I'm sure I don't, but my mental math is absolute trash, and I'd prefer to have one just in case. Is the Windows 10 inherit calculator allowed, or
can't use a computer calculator?
Okay.
However, you can go to the Kettering University bookstore and buy a crappy calculator, or Walmart or wherever, for $3.
Yeah, it'd be a CVS or Kroger for me. I'm an hour south of Kettering currently, so
okay, it's a $3 calculator.
Yeah.
Or you might have one in the kitchen drawer.
That if we do, it doesn't work.
Yeah, well, it could be solar powered. So
even then.
Yeah. Okay.
Some VEs even let you borrow calculators that they keep on hand.
Yeah, if it's in person.
If it's in person, yeah.
Yeah, we have a supply of the four button, 4 function calculators for our VE group. So, all right, we're on page 24. Okay, so very briefly, what we're going to do is talk about radio wave characteristics and recap this. Let me unshare that. And we're going to say what type of wave carries radio signals between transmitting and receiving stations. Once again, we know that's electromagnetic, right?
Electromagnetic.
Okay, radio wave is made up of what type of energy? Electromagnetic energy. Right, and the 2 components of a radio wave are electric and magnetic fields. And for extra bonus credit, what do we know about the electric and magnetic fields?
They are at right angles to each
They
other.
are always perpendicular to each other and to the direction of motion of the energy. So
Yeah.
1, 2, 3, that right hand rule. If you go into an electrical engineering class in electrophysics, you'll see people doing this all exam long.
Yeah.
I did it myself. Okay, frequency and wavelength and stuff. Okay, how fast does a radio wave travel?
Speed of light.
Speed of light, because it's really just a different form of light. Okay, about how fast is the speed of light in meters per second?
300
million.
300 million meters per second. All right, and because radio waves tend to oscillate, the distance between peaks of a radio wave is called the wavelength. That's right. Okay, and how do you calculate the wavelength? If you're given the frequency?
300 divided by frequency in megahertz.
Right. All right, and if anyone taking physics right now?
I did a long time back.
Anyone ever seen this?
What's new?
Anyone?
Nope.
Over lambda, what?
P over
P
lambda?
over lambda.
Anyone get it? It's a classic
F.
physics joke that every physics teacher loves.
Oh.
Do you get it?
F frequency.
In physics,
New.
this is frequency. That's new.
Yeah.
Get it?
New.
What's new? C over lambda. Every physics teacher loves that. They'll give you extra credit for coming up with it.
Hmm.
You say what's new? C over lambda. Okay. Let's see. For converting frequency to wavelength, we just did that. 300 is equal to C is equal to frequency times wavelength. Speed of light is equal to frequency times wavelength. So that's it. C is equal to frequency times wavelength. How do we call certain frequency bands? By their what?
By their range. No.
Wavelength.
By their wavelength, their approximate wavelength. So for instance, the 2 meter band, let's do a quick calculation. If C is equal to F lambda, or 300 is equal to F times lambda, like that, and we don't know the frequency, we would get 300 divided by 2, which would be what?
150.
150 megahertz. But looking at our chart, we know that this is not the case, right? So we're going to go to our band plan. We're going to go to the 2 meter band. What do we see about the 2 meter band? What is our frequency?
144.
144, and it goes up to 148. So that is why it is the approximate number of the approximate wavelength. So it's the approximately 2 meter band. Okay, what frequency range is referred to as high frequency? What are the limits?
3 to 30 megahertz.
Yep, if you learn nothing else during this class, you'll know that. 3 to 30 megahertz. VHF?
30 to 300.
30 to 300. And UHF?
300 to
300.
Yeah, okay. So does anybody remember having a TV with a tuning knob?
Yes.
Oh, yeah.
Where you had a VHF knob and a UHF knob?
Yeah.
Yes.
There you go. So it turns out that channel 13 and channel 14 were actually very, very far apart on the frequency spectrum. Okay, a radio signal of any frequency is called RF. Radio frequency is known as RF. Okay, we are now on to page number 27. Okay, communications at VHF and UHF frequencies are generally known as line of sight. That is because they tend to not bounce off of things. So UHF signals, it is very rare to hear UHF refracted or reflected off the ionosphere. Extremely rare. Once in a while it'll happen, but it's very, very, very unlikely. Okay, so if you think about radio waves, and I draw the Earth, the point at which you can no longer see is known as the horizon. Radio waves, because the frequency is longer than light waves, tend to curve a little bit. So the radio horizon is actually further away than the visible horizon. So the Earth seems less curved to radio waves than to light, and that's because of the wavelength of radio waves. So the radio horizon, the visible horizon, the radio horizon is always longer. Okay, let's see. If a 2 meter signal, 2 meter station signal was weak a moment ago, but now you're weak or distorted. All right, this is a good opportunity to do a little bit of drawing. So, okay, what I'm going to draw is a transmitter, which we mark with the letter TX, and the receiver is over here. Now, it is entirely possible that between these 2 points, you'll have a straight line, right? That would be ideal. Now, it is also possible that between these 2 points, you will not have a straight line. And in fact, what you'll end up with is you'll end up with an obstruction here, and you'll have something that reflects signals, that your signal will now go this way and then bounce, because radio waves, just like light and mirrors, will bounce. This is also not a problem if your signal bounces off of another object. However, what if you are in a condition where you have a radio wave that travels from here to here, and it goes this way, but there's also an obstruction, but you're getting over the obstruction, and there's another object here that is allowing you to bounce signals like that. And you have radio waves that are now passing along 2 different paths. What will happen?
Multipath.
Multipath. And
So,
what
yeah.
will actually happen?
Is that like
So
an
phase
echo?
difference of the received signals, they will be out of phase with each other.
Well, not necessarily. They could be in phase with each other.
Distortion?
True. Well, yeah, what will happen is if they're in phase, so picture this, you have a signal that's going like this, right? And then you have another signal which left the same initial spot that went like this. But this one, upper one, had to travel further to get there because it had this extra distance.
Time delay.
Yeah, well, and let's say that this one arrives and it's at the bottom of its wave. This one is over toward the top of its wave. If you look at these, by the time they get there, you'll have this plus this. It is entirely possible that those 2 signals might actually look like this. What is the sum of those 2 things?
They cancel each other.
They cancel. That would be a big old 0. Now, it is entirely possible that those signals might actually get there like this. And the sum of those would actually be really good, right? You'd actually have a nice strong signal. So this would be known as
interference.
Yes, this is destructive interference. And if they add together, that would be known as constructive interference. So now we're talking about physics and physical things. How long is one wave at 2 meters? This is not a trick question.
2 meters.
2 meters.
Oh, 1 meter.
2 meters. No, that's one wave. One full wave is 2 meters long. So in order to be half a wave apart and cancel, they would have to have a path length difference of 1 meter or 3 meters or 5 meters, some odd number, right? So can you predict where this thing is going to be, that obstruction, that reflecting object? Not really, right? So how do you, let's say you're in an area of destructive interference, how do you change these path lengths?
Move a little bit.
Move, yeah, it's really as simple as that. And actually, you would move to here, and that makes this path now here, and this path is now here. So maybe now you've moved from an area of destructive interference to constructive interference. So that's why you would literally move a few feet. Now, interestingly, we have two different bands that are very popular up in that range. There's the 2-meter band and the 70 centimeter band. So which band would you have to move further on physically?
2 meters.
2 meters, yeah. Because the wavelength is actually slightly bigger. It's 3 times the size. So on the 2-meter band, you might have to move 2 or 3 feet. On this band, you might have to move 1 foot. And what you will notice, for those of you who have actually been on a radio before, sometimes taking an antenna and moving it around a little bit actually makes a difference, because it actually does work. And what's cool is that this is a microscopic thing if you're dealing with light. If you're dealing with radio waves, it's actually macroscopic. You can actually see these things. Not only can you see these things, you can hear them. If you're in a car and you're driving down the road and you're passing very rapidly from an area of constructive to destructive to constructive to destructive, as you drive down the road, you'll actually hear something that sounds like this. And the other person will be all distorted and warbled, and you will be too. And that's actually known as picket fencing. And that's a real thing. And that actually could be on the exam too, if I'm not mistaken.
But the destructive and constructive interference isn't on the exam, just the moving of the antenna.
Correct.
Okay.
But that's why. But this is why. And it just comes down to geometry.
Scott, sometimes that happens with large metal objects too, correct?
Oh yeah, I mean, it can be a truck. It could be any number of different things. It could be an airplane passing overhead. That would be, transient, but you'd still know it. What can happen if you're using data being ones and zeros? If your signal fades out, your error rate would probably go up. Basically, your signal would disappear for a little while and you wouldn't hear much. Okay, so when using a directional antenna, let's take a look at this picture that we just drew here. If we don't have a direct path, and we know that there's a building way over here, and it's a reflective building, it's got metallized windows and stuff like that, very nice modern building. And we have an antenna that we can actually point in this direction. It's entirely possible that if we know that this person is over here, we can actually aim our signals directly at the building. So, and that's where having a little bit of extra gain can be useful, because there's no point with these signals going off in other directions. They don't do you any good. And potentially the same on this end. They don't do you any good. A directional antenna allows you to put the signal where it's going to do the most good. And what is the gain of a directional antenna measured in?
dB plus 2.2.
Yep. Well, once again, we're in decibels. It's just everything's measured in decibels. So maybe your path loss caused by the building, because there's a little bit of absorption, can be overcome by the gain of the antennas. Okay, there's another phenomenon called knife edge diffraction, which is, let's say you're aiming at a mountaintop. Okay, so you're aiming at a mountaintop. There's another station down here. Is there a direct line of sight path from this point to this point?
No.
No. Okay, so if everybody remembers back to doing physics, you'll remember something called a single slit diffraction experiment. Yes, and actually what will happen is when a light wave hits a sharp object, it actually diffracts the light in a whole bunch of different directions that are defined by the wavelength of the light. So usually that's not that big of a deal because it's light, But for radio waves, what can happen is you actually do get some signal that goes down. Part of the diffracted energy will actually go down. And this is known as knife edge, which allows you to potentially transmit from one place to another over a large object. So again, that's known as knife edge diffraction. Okay, the next question is about picket fencing again. Okay, another condition that can impede the transmission of VHF and UHF signals is vegetation. So if we think about winter, what do a lot of people not have much of during the winter outside?
Leaves.
That would be leaves. And since leaves have a lot of water and they're also largely flat objects, leaves tend to both attenuate and reflect signals around, which essentially, if you're aiming at somebody else and there's a bunch of leaves in the way, some of the signal gets attenuated, absorbed in the water, and some gets bounced away. You don't really have as good of a path between you and them anymore. So in the wintertime, you don't have as much absorption by vegetation as you do in the summer. Okay, who was asking about polarization? Remember we were talking about polarization?
That'd be me.
Okay, so polarization. So we're going to draw an antenna. So this is in the vertical direction. This is our vertical piece of wire. Our E field is going to be in the vertical direction if our wire is vertical. So that's our E field. Our magnetic field is going to be in the horizontal direction. So the E field, the direction of the E field defines the polarization of the antenna. So if I have an antenna that is oriented like this, which direction will the electric field be? That will be a horizontally polarized antenna. Okay, so if I have a signal where if I have an antenna that's transmitting a vertically polarized signal, and it makes it to an antenna where it expects the signal to be horizontally polarized, because remember, what is an antenna wire made of?
Metal.
It's made of metal, and metal has electrons in it. And the job of those electrons is that the electric and magnetic fields will cause these electrons to move back and forth. And electrons moving back and forth is known as?
Oscillation.
No, known as current.
Current.
And that is what you are looking for. You're looking for current to be formed in your wire because of the electric and magnetic fields. Well, if they're not what the antenna is expecting, what will happen? They're moving in the wrong direction to make any current. If they're moving in the wrong directions to make any current, what are you going to hear?
Nothing.
Nothing. That's exactly right. So if your polarization is wrong, you will hear almost nothing, which is why if we're using a vertically polarized antenna, you would listen to it on the other end with a vertically polarized antenna. So that being said, how come most mobile systems use vertically polarized antennas?
Because you can make them directional, sort of.
Yeah, but you don't even need to.
You can fit them on your vehicle.
That's right. You can sit them on top of the roof of the car.
Oh, yeah. Okay.
And what directions do they transmit? Where's the axis of symmetry?
Vertical.
Vertical. So if you looked at it from the roof, you would see an antenna in the center of the roof transmitting almost equally in all directions, which is exactly what you want. In addition to that, you also, depending on the height of the antenna, get propagation fairly low to the horizon, which you also want because most people that you want to talk to are
on the ground.
On the ground, exactly. You're not really talking to people in space, unless, of course, that's your goal, in which case it would be a different antenna. So because you're talking to most people you're talking to are fairly close to the ground and can be in any direction. That's why vertical antennas on mobile vehicles, mobile equipment are so popular. They're easy to mount and they talk equally well in all directions. Similarly, if I'm building a building and I put up an antenna up here on the roof and it's a vertical antenna, what does my propagation look like? What direction am I talking?
All the way around.
all the way
All
fairly low to
horizontal.
the ground and all the way around. Omnidirectional, which is exactly what I want. So the fact that they're vertically polarized is really just an offshoot of the fact that this is what works really well for VHF and UHF. And that's why most antenna systems for VHF and UHF are vertically polarized.
Is it the same thing on like a handheld radio?
Yep.
Is that vertically polarized?
It is. Well, it depends. Depends how you hold your radio. If your radio is held horizontally, then no. If your antenna is held horizontally, then you have a horizontally polarized antenna.
God, so when I was into CB, they always talked about your ground plane.
Mm-hmm.
How does that affect your antenna?
That's a really good question. And the answer is really, really important. So, okay. So I wasn't going to get to it, but it's as good a time as any. All right. Let's see. Okay, let me just say that we're on the bottom of 28. If you're looking at long distance weak signal, single sideband and CW is Morse code, single sideband is voice, but an amplitude modulated form of voice, not FM. Then you would typically use horizontal polarization. The reason being, this is how I see it at least, that it's more directional, forward and backward. And because you're trying to get more of your signal in one particular direction, it's easier to build an antenna that's horizontally polarized. That and the fact that the signal that you send out, if it happens to hit water or something, will tend to skip up really well and extend that range. So if you're doing weak signal work, that's basically low angles of radiation. All right. Now, as far as vertical antennas and ground planes, okay. Let me do a quick little example here. Let me turn off my light if I can reach it. Okay, let's see if I can trick Zoom into working here. Okay, I'm going to unshare this. And let's see. Okay, can everybody see that?
Yep.
Okay. Question. No, that's not a good enough reflective surface. Need a better reflective surface. Here we go. That's a good reflective surface potentially. Okay, now I'm going to lift this up here. Do you still see a light?
Yes.
Yes.
Like, okay, how about now? How many do you see? If you consider the thing that I'm holding to be reflective, how many are there?
One.
There's really two. Right? There's the jar that I'm holding. And then there's the actual light. So now here's the question. If you were in the outside world and you didn't know that I was holding up a reflective surface, how many lights are there?
One.
No, I think there's two. If I didn't know any better. And the reason is that if I were to draw this, let's have a nice reflective surface, right? Here's my nice reflective surface, and here's my light source. And I am looking here with my eyeball. Here's my eye. I'm looking at this surface. I have one ray trace that comes in this way. Right? But what's the other path to my eyeball?
The reflection.
The reflection. And if I continue that out, I would see that there's a second light source down there. Everyone agree with that?
Yeah.
Okay, if I do not know that there is a reflective surface, I see two things. What that really means is if I have an antenna that's making that, transmitting that signal, there's one here and there's one here. This is indistinguishable from whether or not this actually exists to the outside world.
Yeah.
So that antenna to the outside world is functionally equivalent to this antenna. which is a quarter wave. This would be a half wave, and this would be a quarter wave ground plane. But that is why it is so important to have a good solid ground plane. Because if you don't have that ground plane, essentially this antenna does not work. A quarter wave with no ground plane does not work. It is a very, very, very poor antenna. So the other question is, how come I can get away with doing this and having my antenna here and having a magnetic mount, which is isolated from the roof, and still have it work?
Does a magnet bounce a negative?
Keep going.
Like a supposed ground plane does?
I'm going to draw a nice tight close in of it. Ready?
Okay.
What does that look like?
Capacitor.
That's a capacitor. So guess what?
Yeah.
Guess
Oh.
what? This is AC, and in particular, this is RF. And what happens at this point? What does the AC do?
Stored.
Stored.
Yeah, it jumps. Well, but remember what a capacitor looks like at AC.
Oh,
It
okay.
looks like a
Jump the
short
graph.
circuit.
Yeah.
So it jumps right across, and that becomes the negative side of the antenna. That becomes the other side of the antenna.
Yeah. That's what I
So-
was trying to say. I just didn't know how to say it.
So here's the top side of the antenna, and here's the bottom side of the antenna, and it's capacitively coupled to the roof of the car.
Yeah.
And that's why a mag mount antenna works.
That's why you need a certain amount of room on the ground plane for the capacitors.
Well, what you really need is, that's why it doesn't work on a fiberglass car.
Right. Yeah, but if you like the antenna say, well, you need 19 inches around. Is that why to get a good
Compared to a
base?
CB, yes. It has to be at least a certain size to be functional.
Okay.
So yeah,
I got a couple
exactly.
of questions.
Yeah.
So is there an insulator
Yes.
for that capacitor? And also, I've seen people use the formula to determine the elements for the ground plane, the distance, like the length of the elements. I'm not certain if I'm using the right term. They just like come up with this number, and I think I looked it up, and it's like some sort of like velocity of something. Can you explain the formula that they use to, and all the factors that are in the formula?
Well, I don't know if I can explain that per se, but if you have a vertical like this, and you take your cable and you tie one side of it to there, you take the shield of your cable and tie that to your ground. Essentially, what you have are radials.
Radials, yeah.
Right. And your radials, typically you want them to be at least a quarter wavelength. And then it's plus a little bit. So now the other thing is that if you're trying to like pick a certain, if you're trying to use coaxial cable, for instance, and do matching with the cable or cut it to a certain number of wavelengths. So let's say that this is a quarter wavelength long and you want a quarter wavelength of cable. Inside your coaxial cable, you have something called a velocity factor. Is that what you were talking about?
Maybe it was just a number that no one could explain what it comes from, and I had to look it up, and I still didn't
And
understand.
velocity factor is basically a result of the fact that inside your cable, you have the outer shield, right? And the inner conductor. And inside those two, you have a dielectric, which is usually not air. It's usually like polyethylene or some kind of foam or solid polyethylene. And what's going to happen is that your dielectric is going to have, I don't think the mu is going to change. That's the magnetic permittivity, but the epsilon, which is the electrical permeability, oh heck, what is it? I can't remember. Is it permeability?
That's right.
Is it? Okay. And you're basically going to have something that is not equal to 1. And because of that, we'll say that the mu is 1. That's your magnetic permittivity or magnetic permeability and electrical permittivity. And I believe it's that it's 1 over square root of mu E.
Yeah.
If I remember right, or square root of mu E. No, 1 over square root of mu E. This is going to set your velocity inside your cable. And this will actually slow down the travel of your waves. So that one wavelength, let's say that your velocity factor is 0.65. That means that a quarter wavelength inside the cable is not a measured quarter wavelength long. It's whatever the quarter wavelength would be times this factor.
You have to take that into account so that you really match them.
If you're trying to cut a cable so that it's a multiple of something, you have to know what the velocity factor of the cable is.
Is that like an absorption rate or something?
No, it just changes. It literally just makes the cable act like a certain length that it isn't really that it isn't really physically.
Right. Right.
Because of the differing speed. So if you've ever seen, like, this is the easiest analogy I can come up with. Let's say you have a glass of water. And you take a spoon and you put it in the glass.
Right.
And the spoon looks like this.
It bends it.
Right.
Yeah.
But you pull it out and it's not really bent.
Right.
And that's because your index of refraction in the material is different than it is in the air.
Right.
It's the same thing. Basically what's happening is that the velocity of light inside that material is different than it is in the air.
Right. Okay, I got you.
It's the same thing.
It's like a bare wire, something moving over a bare wire versus being shielded.
No, that's different.
That's even different.
Yeah, this is index of refraction of the material.
Yeah, okay, refraction. Okay.
And that's what happens inside your cable. I don't know, does that sort of answer the question?
Well, it was all over my head. There was just a formula I'm trying to find now that just gave a number like 200 and some feet. And then you throw that into a formula to find like 19 inches.
Oh, well, there's 468 divided by F.
Yeah,
Or
that's over my head. That's kind of what I was asking.
Well, no, or 234 divided by F.
Yeah, that sounds about right. What are those numbers?
All right, here we go. Ready? Okay, so 300 F and lambda. Agreed?
Agreed.
We're back to that. 300 F and lambda. Okay. This will give you the length of a wave in meters, right? So let us say that we want our wavelength. It's 300 divided by our frequency. Agreed?
Yes.
Okay. How long would a half wave be?
150.
150, whatever, M divided by F, right? Okay, what would a quarter wave be?
75.
75.
75.
Okay. Now, take this and multiply it by 3.3. That would give us feet.
Right. Okay, so
That
you
would
have
be
25. Yeah.
So that would be 200 divided by 200 meters divided by F. No, we'll take that back. Excuse me, 500 feet divided by the frequency. And this one would be 250 feet divided by the frequency.
Okay.
All right, everyone in agreement so far?
Yeah.
Yeah.
Okay, so what it turns out, this is the leap of faith that you have to take with regard to that. A full wave antenna would be 492 divided by F. Or sorry,
Okay.
a half wave. A half wave would be 492 divided by F. A full wave would be 984 divided by F. Right? These are the formulas that we know. But in fact, 492, right, or 500 or whatever it is, actually becomes 468.
Because of its refractory.
And 246 becomes 234.
Okay.
The reason this happens is because of the real world effects of the real world, which is that when you're making an antenna, you have to actually shorten whatever you get by 5%. And this is something that we cover. So basically, if you went with this number, it would be 5% too long when you actually build it. And that's because it's a piece of wire. It has self-inductance. There's stuff around it that makes a capacitor, right?
Yeah.
Okay, this makes inductance. Because it's a piece of wire. Anyway, what ends up happening is that the real world forces you to abandon the math a little bit and make it 5% shorter. And if we were to take 5% of 246 is about 12.
Right.
Well, 246 take away 12?
234.
234. 5% of 492 is about 24.
So are they kind of standard for shielding?
Well, this isn't even shielding. This is just if you're making an antenna.
Oh,
This
okay.
is just calculating the length of your wire.
Oh, okay. Okay.
And yeah, the velocity factor was something else. I thought we were going down that route, but we're not. This is actually just calculating wire lengths.
And this is feed line?
No, this is just wire.
Just wire.
This is
okay.
if you have a radiating wire.
Okay. In your
that
earlier
if you're
example.
just making an antenna, what it really means is that your antenna, if you follow the math, is going to be too long.
Yeah. Okay.
So you have to follow the math and then take away 5%.
Make the adjustment.
That does make sense because the video as I watched, they would just pull the number out of thin air, like off
Yeah.
of some sort of table
It's
somewhere.
not out of thin air.
Well, yeah, I was trying to figure out where they
Yeah.
get the number from.
It's experimental and it's been done for 100 years.
Thank you for that.
Mhm.
You saved me like a day's worth of research just to find very little.
Excellent. Okay. So next thing we're going to do is we're going to draw the ionosphere. Now that we've done that, let's make the Earth. We're going to make the Earth kind of greenish. Now we're going to make the ionosphere. All right. So basically way down here is where we live. This is the troposphere. And above that is stratosphere where airplanes fly. And then above that, there's a few other layers in there that are defined, but then we have this thing called the ionosphere. And this is where we get into atmospheric physics. And this is really what got me into radio in the first place. The fact that everything that we experience with regard to the ionosphere is driven by interactions between the sun and the atmosphere. So here's the sun. And name something that the sun emits.
Light.
Okay, we got light.
Ozone.
Radiation.
No ozone. We have light. We have heat. Heat in the form of infrared. What else?
Electromagnetic.
Yep, EM waves, radio waves. Lots of it actually. What else?
Cosmic rays, gamma rays, X-rays.
All right, we'll go with cosmic and gamma and X-rays and what else?
Visible light, and then the
We got
infrared,
UV.
and then
We already got light. We're gonna go with ultraviolet.
then radio frequency.
Yep. So we got RF. Okay, so we have lots of stuff coming out of the sun. The sun is a radiating object. It radiates a lot of different frequencies of that electromagnetic spectrum. So what makes it largely down to Earth?
The most filtered parts.
Well, we're really lucky. So what makes it down to Earth? We have light. And what else?
UV, heat.
We have
UV.
heat. And we have some UV. And some of the radio. Some of it. That's pretty much it, thankfully. Right? Okay, so what gets stripped out by the atmosphere?
A lot of the ions.
Well, not the ions.
Cosmic
Gamma
rays,
rays,
gamma
X-rays,
rays,
cosmic
Yeah,
rays.
gamma, cosmic.
ultraviolet.
Basically all that hard radiation, as we would call it. The radiation, which if it made it down to the surface of the Earth, would sterilize the planet, and we would have no life here. So we're really lucky. Bet you didn't think this was a class on atmospheric physics and planetary physics, but it really is. So basically, UV, X-rays, gamma rays, cosmic rays, for the most part, these get filtered out by our roughly 600 miles of atmosphere that we have. And so what is the atmosphere largely made of?
Air.
What is air?
Hydrogen?
No hydrogen.
Nitrogen, oxygen.
Nitrogen.
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 Largely, it's 99% nitrogen and oxygen. 78% nitrogen, 21% oxygen. And what happens is that all this solar radiation, which comes out of the sun, has some very energetic particles. Basically, those rays, those photons have a lot of energy. And every so often, what will happen is during the daytime, you'll have a photon which has the right energy that strikes, for instance, a nitrogen atom and splits it into free nitrogen and maybe an electron here, or it will take it and then make it an N2 plus and an electron. It'll strip an electron off, and then we'll have some oxygens that become O3, which is an ozone and a plus and an electron, or we'll have an oxygen, my O2 with a plus and then an electron floating around. All right, so what are these things? What do you notice is true about all of these things that have now been created?
They're charged.
They are all
Polarized.
charged. That's right. We have electric charges on them. We have electrons floating around and we have positively charged ions floating around. So what happens if we take an electromagnetic wave and aim it up at that cloud of electrically charged things? Well, what we end up with is that cloud of electrically charged things can actually reflect or refract those electromagnetic waves. And what we end up with is propagation of signals that are aimed toward the sky over great distances, because the layer that they're bouncing off of is 500 miles up in the air. So when you start looking at the geometry of that, you can cover a distance of, let's say, 2,500 miles with radio waves. So we break our atmosphere into these different layers. There's something called a D layer, an E layer, and an F1 and an F2 layer. That's our ionosphere. So obviously the D layer the energy has to travel through a lot of different things before it dissipates in the ionosphere at the D layer, because it's the deepest layer. This is the last one to form during the day, and it's the first one to go away at night because your solar radiation disappears. The E layer is slightly above it, and then above that are the F layers, which split into F1 and F2 during the day, and they merge into one F layer at night. So now let me ask this question. What happens if one of these electrons floating around someday runs into one of these positively charged nitrogen molecules? What will happen? Because opposites attract. They snap back together. So then this now disappears from play. So during the day, what you end up with is that you have a lot of ionization because the sun is directly overhead. And at night, what happens?
Everything stabilizes.
Everything stabilizes. That's right. So what happens is that during the day, you get a big blanket of ions forming, and at night, it fades away. So has anyone ever listened to AM radio at night? Like from a moving car? Long distance AM radio. Have you ever noticed that at night you can pick up stations from 1,000 miles away?
Yep.
Whereas during the day you can't. And that's because the D layer absorbs frequency less than or equal to 10 megahertz. And that forms during the day. As soon as night falls, the D layer disappears, which basically allows all those signals that would normally get absorbed to pass on through. And all of a sudden, your signals are able to propagate at night. So you can hear AM radio at night, but not during the day. Well, this also has impacts for us as hams because we have access to, let me share this right here. Okay, so notice we have a lot of different frequencies, right?
Yep.
This all the way down from 1.8 megahertz, even lower than that. And then we go way up into the gigahertz range. We have lots of different frequency bands. This 160 meter band way down here, this is right next to AM radio. So basically what that means is you'll hear absolutely nothing on that band during the day. As soon as night falls, you'll start to get propagation. What it also means is that this band, for instance, will not work terribly well during the day, but at night it'll cover thousands of miles. This band right here at 14 megahertz is above that absorption range, which basically means that that signal will pass day and night up into the upper layers of the atmosphere. The higher you go in frequency, the more ionization you need for this whole thing to work, or else it falls apart. So when the sun is making a lot of energy, spitting out a lot of energetic photons, this band at 21 megahertz might be really, really good. At the bottom of the sunspot cycle, because it follows an 11-year cycle, and the solar and the radiation coming out of the sun is diminished, this band might be dead for weeks at a time. Similarly, this band all the way up at 28 megahertz, when the sun is very active and it's daytime, this band can be good for worldwide communications from anywhere to anywhere. If you've ever been on CB and you can say the skip is in, that's what that means. Basically, the propagation is such that it's carrying signals over thousands of miles because you have enough solar radiation to create enough ionization to make that work. So we have this 10 meter band, which we use for that same thing. Then you come up to here at 50 megahertz. 50 megahertz is usually too high for that normal F layer to work on. You would need so much radiation that this only happens at, shall we say, 1957. If you were alive during 1957, you stood a chance of having experienced that. That's the last time the sun was making enough energy at those frequencies to make the F layer actually skip those frequencies. So we basically rely on 6 meters, 50 megahertz band for local communications and for something called sporadic E, which uses occasional enhancement on the E layer, which is below the F layer, for interesting things to happen. And so you can get because it's not physically as high, you don't get skip distances that are nearly as far, maybe 500 to 1,000 miles. But still, it's 500 to 1,000 miles when usually it's nothing. So,
hey Scott, is this phenomenon independent of cloud cover at all the bands?
Completely independent. Yep, it can be pouring down rain and it still works, unless you're up on the microwaves. Then it'll make a difference.
Notwithstanding the effect of heavy rain on your higher frequency bands, right?
Unless the wind blows your antenna down, you're okay.
Yeah, but I was just saying.
I've had that happen. So
not true that like your 2 meter bands and stuff, that the heavy moisture in the air can affect those.
A little bit.
Just a bit. Okay.
Just a little.
But definitely higher frequencies are affected more by vegetation.
Right. The higher up you go toward that resonant frequency of water, which is at 2.4 gigahertz, the closer you go to that, the worse it is. So I know for a fact that I've seen microwave links, and Masood, you may have experienced this as well. We have a museum, the museum that I participate with. They actually get one of their they get some of their internet connectivity, or if not all of it, I guess,
Yeah.
via microwave link. And
Uh-huh.
they had on top of the building, they had a dish, and over on this hilltop, they had another dish, and they actually had to cut a hole in the trees to get a clear path.
That is right. That is very much common.
Yeah.
Yeah, you have to have the clear line of sight. Yes,
They actually had to cut away a bunch of branches in the tree to get a nice clear shot.
absolutely, that happens.
Hey, Scott, I didn't want to side tangent it, but when you're talking about the solar effects,
Yeah.
could you just quickly tell us what happened with the Carrington event?
Yeah. The Carrington event was during a solar peak. And 1859, it was basically, you know, the sun goes through 11-year cycles of high activity and low activity. And we are coming out of the bottom again, thank goodness. But we had the 1859 was a really high peak, but there was very little in the way of anything, you know, and electrical at that point, except for telegraph lines. And essentially what it was when the sun gets active, it can also, in addition to throwing off a lot of radiation, it can also throw off coronal mass ejections, which are large numbers of charged particles, which can, when they impact the Earth's magnetic field, they can actually distort the atmosphere. And what you end up with is, if it's coming from this direction, it can actually
charged or something.
Yeah, because it's charged particles. If the polarity of the particles is such, they can actually temporarily strip away layers of the atmosphere. And in addition to that, you end up with a large number of particles that are bent down and over the North and South Pole. And when those high energy particles impact the atmosphere, they give up a lot of their energy in the form of an aurora. So basically what you ended up with is the Earth being blasted by large numbers of charged particles from the sun, which caused, auroras like down to Hawaii. And essentially what you ended up with was, in addition to that, a lot of telegraph lines, because telegraph line is a long piece of wire. They picked up a lot of the electromagnetic energy and were actually, causing sparks and people getting shocked because they picked up so much energy. So yeah, that was the Carrington event. If it happened today, we'd be in a lot of trouble. There's no saying it won't. So we were just lucky that our technology wasn't, at that point where it could be damaged yet. Okay. So let's see, sporadic E. Sporadic E is a condition where the E layer of the atmosphere, which is about 100 miles up, is really good at bouncing around signals on the 2-meter band, the 6-meter band, and the 10-meter band. So again, here's the D layer and here's the E layer. So sporadic E is basically when this layer becomes highly ionized, and you end up with conditions where so this is 2 meters, 6 meters, and 10 meters, which would normally be, 2 meters is usually line of sight, 6 meters is often line of sight, and 10 meters usually requires a lot of ionization up here in the F layers, where it still actually works on 10 meters on the E layer. And that's known as sporadic E because it's sporadic. You can't, after all these years, nobody's really been able to predict it.
Is it like a skip wave?
Well, it is, but it's out of a different level of the atmosphere that normally doesn't do anything.
Oh, okay.
So essentially what you end up with is these clouds that form for some reason, still unknown. A characteristic of VHF signals received via auroral reflection. So if you picture again the Earth and you think about what the aurora looks like. So here's the Earth and here's our magnetosphere, magnetic fields. Basically the stuff coming from the sun will get sort of directed up and around the poles because at the poles, the magnetic field comes down toward the Earth. So basically what you end up with is a lot of particles that come down, energetic particles that come down into the atmosphere, which is why most people, if they think of the aurora, they think of, you know, going up to Alaska, because you'll end up with these auroral areas where you have nice shimmering lights. So let's say that you live right here. So what is the aurora made of, everybody?
Light.
Well, what is light?
Well, energy.
It's essentially, it's an electromagnetic thing.
Yeah.
Right? You basically have electric particles floating around. You have ions floating around. Well, does it really matter if the ions are 400, 500 miles up, or they're sitting here in the aurora? The answer is no.
No.
If you have an antenna and you can point it into the aurora, your signal can be bounced out and received by somebody else.
Wow.
Yeah, and that's known as auroral scatter.
Okay.
And because of the shimmering, if you think about what the aurora looks like, signals fluctuate rapidly and sound really weird and kind of ghostly. If we have some time, I'll actually go and see if I can't find an audio clip of what an auroral signal sounds like. What band is best suited to communicating via meteor scatter? All right, so what's a meteor, everybody? What is a meteor actually?
A rock.
A rock from space.
A rock, yeah, a
that's
rock.
gone into the atmosphere.
Right. What happens when it hits the atmosphere?
It becomes a meteorite.
Right. And what happens? It gets really hot.
Mhm.
And
It
what,
starts to burn up in the atmosphere.
it burns up. And in the process of burning up, it gets really hot and creates an ionized trail in the atmosphere, which might last for 30 seconds.
Right.
6 meters, believe it or not. If you know that there's a meteor shower coming, you can point your signals at where you think the meteor scatter or the meteor shower will be up in the air and work people on the other side
Yeah.
via something called meteor scatter. You're
Yeah.
basically bouncing 6 meters, the 6 meter antenna, 6 meter band off of the trails in the air, in the sky. That's known as meteor scatter.
You could do that with a comet too?
Comets are outside of our atmosphere.
Okay.
So it has to be something that in the process of burning up, it causes that same ionized trail.
Okay.
It
Why not
basically,
10 meter?
just because you typically don't have as much gain. I mean, there's no reason it wouldn't work, but the antennas are just that much bigger. I mean, you can do meteor scatter on 2 meters. You can do it on 70 centimeters. Most commonly done on 6 meters though. Yeah, but there's no reason it wouldn't work any higher. At
So
least not that I'm aware of.
that's pretty similar on like doing like a moon bounce, huh?
Well, except that moon bounce, you're aiming at a stationary target. In this case, you're aiming at something that, you know, flashes into existence and lasts for 30 seconds. So part of it is that, let's say you're doing moon bounce. We do moon bounce, by the way. So here's the moon and here's Earth. Not to scale, obviously. So let's say that we have, this is 250,000 miles. And you aim at the moon and a signal comes back down 250,000 miles. So given the fact that this is actually a very long path, considering what we would normally do, this actually requires very high gain
Mm-hmm.
and also typically legal limit power.
Is that 1500
That's
watts?
1500 watts. And usually it's at, you know, 432 megahertz.
Okay.
It can also be at 144 megahertz. But what do we know about antennas? The lower the frequency, what happens to the wavelength?
Higher the gain.
The higher.
The higher the bigger the antennas have to be.
Right.
Which means if you go, you can do 50 megahertz or 6 meter moon bounce, but you're talking some big antennas, because I can actually show you a picture of a typical here moon bounce array, EME array. Oh yeah, there we go. This is something that I have never done. The reason I've never done it is because of expense.
Yeah.
I mean, that's an EME array. And essentially you've noticed you've got 16 Yagis all fed in parallel and they're all on a big rotator. Like here's another one.
Holy moly.
But you know, the moon is far away.
Yeah.
Here's another one.
So that's really a 500,000 mile path.
Yeah.
Okay.
And the other thing is that the moon is not a reflective surface. Number one, it's round.
Mhm.
And number two, it's rocky and bumpy.
Mm.
So it is not a perfect surface. So yeah, this is a what, 4x6 array. But typically the other thing that you get into, here we go. There's a nice one.
Wow.
The other thing that you get to, and notice the people down below.
Yeah.
The other thing you get into when you start doing things like that is you start looking at signal loss. And the fact that when you do that, you actually have to put preamplifiers outside at the antennas themselves to amplify what it's receiving before they get lost, before the signal gets lost.
Yeah, that's a long way.
Yeah, it's a lot of it's a lot of money. It's a fair expense, and I don't really have any desire to do that. And but you know, I respect those who do.
When I see that, he did it in actually like a big satellite or a dish.
Yeah, you can do a huge dish too.
Yeah.
Well, and that's how we communicate with some of those really far distant satellites as well, right? I mean,
Exactly.
you know, the Voyager, which is outside of our solar system now, is still communicating with radio transmissions.
Yeah. Well, and Roseanne, the other thing you mentioned, the moon is a reflective surface. We see sunlight at night, but that doesn't mean it's radio reflective.
Mhm.
So it's not the best reflective surface. All right, let's see. What mode is responsible for allowing over the horizon VHF and UHF communications to about 300 miles? That would be known as something called troposcatter or tropospheric scatter. Again, the troposphere is where we live, right? In the very lowest 5 miles of the atmosphere. Signals that go up into the atmosphere will sometimes hit the atmosphere and scatter in different directions, which means that somebody here could actually be hearing it. Someone here could be hearing it, even though normally it would just pass right on through. So that would be known as troposcatter, because literally the signal is being scattered by the atmosphere, the same way that, you know, blue light is scattered and makes the sky look blue. Tropospheric ducting, that's another thing which is similar but different. So if I were to draw, has anyone ever driven a car and noticed on a hot day, you see what looks like a reflection of the sky in front of you in the road?
No, I've just seen like heat waves off the road.
Right. But basically they look kind of bluish. And the
Yeah.
reason they look blue is because they're reflecting the sky. Well, what's actually happening is that you're getting, so here's the road, and you have multiple layers of air above it. Typically, as you go up, you expect the temperature to go down, except that right at the road surface, you're really hot, and then you're
Right.
cooler, and then hot again, potentially. And what you end up with, the same way that when you're looking at a spoon in a glass, it'll look bent.
Right.
What will happen is you can actually get this index of refraction forming a waveguide, which catches the wave and bounces it around until it gets up and you look at it, which means you're basically looking at a reflection of the sky having been
Wow.
bounced around. This also exists if we're doing it from the ground up in the air on the radio, where we have a temperature inversion where we get something that we don't expect, a nice little, you know, hot, cool alternating. We can get an index of refraction where we get signals that are coming from the ground and get trapped in between layers of different index of refraction. This is actually very common over the Pacific Ocean. This is known as tropoducting or tropospheric ducting, and this is caused by a temperature inversion in the atmosphere. Every year between Southern California and Hawaii, we get one of these. And from the top of a mountaintop in California to the top of a mountaintop in Hawaii, you can very often communicate on UHF because you're sitting up here close to the point where the duct is. So it's really easy to push a signal up into the duct that forms. It's not really a reliable way of communicating, but it can operate at, up into the gigahertz range. And that's known as tropoducting.
Tropoducting.
Yep. It actually forms a duct. What weather condition would decrease range at microwaves? Rain, fog, snow, anything that has water in it. And on the 10 meter and 6 meter bands, basically, if you're on high frequency or even VHF, you're going to have very little impact from rain compared to microwaves. Okay, so now we're on. Yeah, go ahead.
I have a question about the tropospheric scatter for
Yeah.
VHF and UHF. That doesn't work for HF. HF only bounces off the ionosphere.
Well, yeah, because it doesn't work at on the tropo layers. I mean, you may get something, but you typically don't even notice it.
So the tropospheric scatter is something that anybody can do with UHF, VHF pretty
Mhm.
easily.
Well, I mean, the conditions have to be right.
Yeah, what are
okay.
conditions, Scott, for tropospheric scatter? What are ideal conditions?
Honestly, a lot of that's kind of random.
Really?
Yeah.
So, like humidity.
It could be any number of different things. I'm sure that I've worked troposcatter before, but I think that would probably be like what would give you propagation between like, Eugene and Portland, 100 miles, because ducting is not common here. Like I was watching TV when I was in college. I lived on the 8th floor of my dormitory, and one Sunday morning in, I guess it was June, early June. So, we had a lot of heat, a lot of humidity. We actually had a duct that was forming between Maryland and Connecticut, and I was able to watch UHF TV stations from Connecticut on a little black and white TV. So that was definitely a duct. Okay, let's see. HF propagation. All right, you guys probably already know the answers to these. Here we go. What part of the atmosphere enables the propagation of radio signals around the world?
Ionosphere.
Ionosphere. That's the high altitude stuff. So we're going to draw that here again. So DE, F1, F2. Okay, this is collectively the ionosphere. DE, F1, F2. How come there's no C?
Because we've used it too many times.
Honestly, I think that they weren't sure that they wouldn't find something lower, so they left some letters there. To my knowledge, no one's ever found a C layer. So I think it was just they just figured that maybe someday they would. All right, so there's the ionosphere. The advantage of HF versus VHF and higher frequencies, long distance ionospheric propagation is much more common on the high frequency bands. And again, that's because you can get signals up into here and they can cover long distances just because of the geometry. Which of the following bands can provide long distance communications during the peak of the sunspot cycle? That would be 6 meters and 10 meters during the sunspot peaks. So the reason that, again, those are only typically good during the sunspot peaks, everybody, let's hear an answer. Let's hear somebody take a guess.
It charges the upper atmospheres.
Yep. All right. So basically, during those sunspot peaks, sunspots are typically correlated to high output of energy, ionizing radiation, which tends to cause higher levels of ionization up in the atmosphere. And when that happens, the more there is, the higher the frequencies you can go. So that would also mean that during the day, when would you typically get 10 meters? During the day or at night? If you had a choice.
During the day.
During the day. Okay. A common phenomenon of HF signals propagation is fading. All right. So why would you get something called fade? Well, it turns out that the atmosphere way up there is not flat. So the same way that you ended up with multipath interference on VHF, we have the same thing on HF. So random combination of signals arriving via different paths. It's multipath. Now, if I'm holding a handheld radio on VHF, what can I do in case I see a problem? I can move a couple of feet, right? But what if I have an antenna that is up in my trees?
You can't do anything.
I can't do anything. Basically, what you do is you wait for the signal to come back. You wait for the fade to go away and wait for the signal to come back. The other thing is that by the time a signal goes up into the upper atmosphere and gets absorbed and re-radiated, and twisted around, the polarization of a signal is elliptical, which basically means that there's a vertical component and a horizontal component both. What that means is it does not matter for the most part whether you're using vertical or horizontally polarized antennas on the high frequency bands. For
So
VHF,
back
it
in the
does
day
matter.
when we use like coat hangers for our antenna, and we would just move it just a hair this way and a hair that way to get that one station. It's the same concept as moving the antenna.
Yep.
Because of the
exactly right.
frequency so much smaller.
Yep. That's exactly right. All the wavelengths are smaller.
The wavelengths, yeah.
So your distance between peaks and valleys and spots where you had constructive and destructive interference, there was a very, very small change. All right, so we are now on page 33, and who would like a 5-minute break?
I would.
All right, see you all in 5 minutes. Think of questions.
Hey, take care, Scott. Have a good one.
Bye, Joel. Thanks for stopping in.
You bet.
Hey, Scott, I got a quick question for you. Are you there? Hello? Okay.
Scott, you there?
No, he's not there. Hey, Bob, can you hear me?
Yeah, I can.
I got a question you might be able to help me with here. This is like taking a sip of water off of a fire hose for me, and it's going pretty fast and it's fascinating, but it's a lot more than what I thought I'd be biting off right now. So are we well beyond the technician level training material here and into the general and approaching the extra? Or because I see that you already have a call signal here.
I got a technician, but it's been a long time since I took that test.
Okay.
We're getting, go ahead, Scott.
No, go ahead. Go ahead.
I was just gonna say, we're into a lot of theory, and the test isn't going to be so much theory, but like Scott says, you got to understand the principles before you can understand the total theory and what's behind all this.
Yeah. So Scott, what I'm thinking here, what I was asking Bob here, since he's already had his technician license here, are we well beyond the material here for the basic technician license, or are we getting into general and beyond? Or because it feels like I'm drinking out of a fire hose here. This is a lot. It's fascinating.
Well, all I can say is radio is radio. The same principles that apply to this apply to everything. My goal is really to teach you some of everything, but not like, a full treatise on everything. But, if there's something that's going to help enhance your understanding, rather than just like, well, I could go through all the questions and just do all the questions. But really what it comes down to is why are the answers what the answers are?
Yeah, I understand it's the theory of it all and the understanding of it. And
well, if it makes you feel any better, today is the hard day by a lot, by a long shot. By a long shot. That, basically it really comes down to a lot of very, very, very basic and straightforward things. We're past all the math. We're into just like understanding, concepts of what signals do and things like that, and why they do what they do.
Yeah. And if I can, as somebody who just passed their test, I found it helpful. Like even though I passed it, taking this class is sort of helping reinstate like what I already know, but I just don't know why. So it might be helpful after you take the test to come back and do another class like this. And then it might kind of put 2 and 2 together, and that might help.
Carl, take the test and see how you do. And
well,
yeah.
Have you taken practice exams?
No, I have not. And now I want to go and review your recording of this probably even before tomorrow. Although I've got a football game coming up at 6 o'clock between the Aggies and LSU that I want to watch.
I know the feeling. The Ducks are playing right now.
Yeah, but anyway, and if the Aggies are losing, then I'll watch your recording of it again and kind of get away from the game for a while there. But anyway, I want to watch your recording to review and reinforce a lot of this information here, so that I have a better understanding of it.
If you're going to take an exam tomorrow, I would recommend doing some practice exams tonight.
Okay.
Absolutely, because then some of the things you'll see that the questions like, oh, I remember that. Oh, I remember why. Even if it's like stored somewhere deep in there, it'll because if you take the practice exams, they all have the answers. It's not like you have to just guess, and you can see what the answers are. And what you'll find is that typically for every question, 2 of the answers are really, really wrong.
Yeah.
And now you'll know why they're really, really wrong.
Mm-hmm.
They don't make any sense.
I've got a question.
Yeah.
I was thinking that even today or maybe tomorrow at some point, we would even get to see a ham radio. And
Like this?
well, I've got a little handheld, you know, that I bought in anticipation of passing the test, but I had just kind of assumed that part of the study would be to see a radio and know what some of the dials are and what
Well,
you
we're
do.
going to do that too.
Oh, cool.
Yeah, we
Okay.
do that too.
Hey,
Oh, Scott,
Yeah.
real quick here. So where do we find the practice test here? I was thumbing through this material here, and the practice questions here, you have them referenced to the practice test, but I know they're probably all multiple choice.
Yep.
So
They
like
are,
you said,
right here. Hamstudy.org.
Okay, I'll go there and look it up here.
I sent off for a book that has 10 tests in it. And it's supposed to be good till next year.
Yeah. I mean, the
Yeah.
question pool changes at the end of 2022.
Right.
Okay.
Yeah.
Uh,
Hey, Scott.
Yeah.
I have been doing some practice tests and I end up having almost 65%. And the areas that we have covered so far, those are the areas that I have no problem with. And I have only problem with like some regulatory kind of areas and essentially the things that we are going to cover now.
Yep. Well, we do the regulatory stuff tomorrow. So.
Okay.
Hey, Scott, real quick, Bob.
Yeah.
And we've got one of our emergency vehicles is a Ranger, which is pretty much either plastic roof or fiberglass bodied.
Yep.
What would you recommend for a good ground plane for a 2 meter 440?
Do you have access to the underside?
Yeah.
You can just put up like a layer of foil or something, or like a thin piece of sheet metal if you can go through the roof.
Okay, I can mount underneath the roof, and it's plastic.
Yeah.
Okay, good. Thank you.
All right, here we go. Antennas and feed lines, probably my favorite part of class. Basically, how do we get power from one place to another? All right, here we go. Which of the following describes? We are now on page 33. Which of the following describes a simple dipole oriented parallel to the Earth's surface? First of all, what is a dipole? A dipole is an antenna that looks like this. It has two legs, each of which is a quarter wave long and is fed by some feed line of some kind. Now, what do you notice about the fact that I say a quarter wave long? Why is that significant?
Half wave, lambda
Right.
by 2.
It's a total half wave. And what else do you know of it? What else do you know about it? If it's a quarter wave long, how long is it?
In terms of meters,
yeah,
it could be 100, depending upon the frequency band which you want to use.
Exactly.
100 to 12.
It could be anything. It could be
Yeah.
any number of different lengths, right? So
Mhm.
the problem here, of course, is, well, how do you pick an antenna that works on lots of different bands? A half wave dipole on the band that you've chosen has an impedance of 72 ohms. And remember what impedance is? That is the opposition of flow to AC. And AC is alternating current, and radio frequency is in what form? Sine waves. So radio frequency is a form of AC. So the impedance of a half wave dipole is 72 ohms. And we follow this down our feed line to here. And ideally, we have 72 ohm feed line, and we have a 72 ohm radio, which has a characteristic impedance of 72 ohms. Well, this is never
Is
the
it
case.
72 or 75?
No, it's not. Well, it's 72, 73. And let's say that we find something called 72 ohm cable. Well, this never happens. There's no such thing as 72 ohm cable. So usually this is 50 ohm cable, and this is a 50 ohm radio. Okay, So what we have here is this antenna is fed by cable that's usually 50 ohms. And up here at the antenna itself, right where it splits from the cable, we have what's known as an impedance mismatch. Ideally, if you think of it this way, let's say that you have a 1,000-foot long piece of rope, right? And you tie off that rope somewhere way at the end and you whip the rope. It's 1,000 feet long. Are you ever going to see a signal? Like, are you going to ever see a reflection of energy on that rope? Probably not, right? As far for all intents and purposes, that wave that you just made on that rope is going to dissipate by the time it gets there, and you'll never see it. But let's say that you have a 3-foot rope and you tie it to your doorknob and you whip the rope and you make a wave that travels down the rope. What's going to happen when it hits that doorknob?
It'll stop.
It will not stop because energy can
Never be.
created or destroyed. So what's going to happen to that wave that you created on that taut rope?
It'll travel
It'll go backwards.
back.
It'll bounce back, right? So this is an impedance mismatch. If that rope went on forever, you'd never see it come back. But since it doesn't go on forever, this is it. This is what's known as a mismatch. The energy has to go somewhere. The same thing is true with antennas and power. Antennas, transmission lines, so that if you put a signal out and it hits a mismatch, this right up here where it goes from 50 to 72 would be a mismatch. It's not a complete mismatch. If you had an open circuit or a short circuit, that would be a complete mismatch. But what ends up happening is up here, some of your signal goes out and some of it comes back. It's proportional to how bad of a mismatch that really is. So now what happens is the signal that comes back down the line. And where does it end up? Because energy can neither be created nor destroyed. Some of it gets burned up in the feed line because feed line's not perfect. Where does the rest of it go?
Back to your radio.
Back to the radio. So you have to dissipate that energy, at least some of it, in that radio. Well, you're already not 100% efficient, so you're already making some energy just to make the signal that's going up. So what that's doing is causing extra heat dissipation to be necessary, extra voltage inside your equipment, which can destroy your equipment. So what we do to take care of this is, because we know there's no such thing as a perfect match, is we put a box here and we do this. Tell me if this looks familiar.
A variable
antenna tuner.
That would be an antenna tuner. And so here is your transmitter now, connects to here. And what this does is this creates the ability to make adjustments and create a match that looks like 50 ohms for here, so that your transmitter's happy. And for your antenna, you're like, well, I don't really know what it is, but it's 50 ohms looking this way. And now what happens is that the power that comes back down on the cable hits this antenna tuner and gets re-reflected back up toward the antenna, where it still has a mismatch. That never really went away, right? This is still a mismatch, but now the power just sort of like goes out a little more and then bounces back down and then goes back up. And every time it goes through, it gets a little weaker and some of it gets transmitted. So what ends up happening is that it heats up your cable instead of destroying your transmitter. And that's why we use an antenna matching circuit.
Couldn't you put a capacitor and inductor on the top at the point of the wire hitting the antenna so that you could try and tune in the
Yes, you could.
impedance there?
You absolutely could. Now, the tricky thing is that what do we know about capacitors and inductors? Their impedances are frequency dependent, right?
Right.
So if you were going to build an antenna that worked for just one frequency, absolutely, positively, you could do some matching up here. Absolutely. And that would be a great idea. Yeah.
Is the impedance mismatch intentional?
No.
Okay, that's just something you want to avoid.
That's something you want to avoid.
Okay.
But
I don't
it's something
remember this.
that you might be able to tolerate. like for instance, my antenna looks like this. This is 450 ohm feed line, and this is a half wave dipole. What's the impedance of a half wave dipole again? 72 ohms. And my feed line is what?
72 ohm, yeah.
Oh,
450 ohm.
450. That's a pretty bad mismatch, right? What I do is I
Mm.
run that down to a tuner, which makes the transmitter happy. And what happens is I get a little signal out, a lot of it comes back, then it goes back out and back up and down and up and down and up and down many times. But whereas
Okay,
this
baby. Okay,
cable that I have might have a loss of 3 dB per 100 feet of length. This is like 0.1 dB per 100 feet because it's open wire feeder. It's very, very low loss, which means that basically I can actually tolerate that terrible mismatch and get away with it. Now, the other thing I could do is I could actually put a transformer up here, because in addition to using transformers for transforming voltage, you can also use transformers for transforming impedances. So if I did, let's say this is like a 6-to-1 mismatch, I would have a 2.5-to-1 turns ratio. I'd actually build a transformer that had that ratio, and I could transform this impedance to this impedance. Antennas are the best. They're just the most fun. Okay, so, all right, which of the following describes a simple dipole oriented parallel to the Earth's surface? That again is a horizontally polarized antenna. That's a dipole. If you look at a dipole antenna, the radiation pattern of a dipole is like this. It makes a donut shape around the antenna. So you'll have almost nothing along the wire. Your signal will be strongest up and this way and that way and that way. So you'll basically have a donut around the antenna that represents what your transmitted signal looks like. So broadside, as it's called, and it basically perpendicular to the antenna's axis.
Is that pretty much the same with the NFED?
It is. Yeah, and the reason being that I'm actually going to change this right here. This is a really good segue. Ready? I'm going to make a half wave antenna. Okay. This is another one of those fundamentals that you are not required to know, but is really, really helpful. All right, here we go. This is a conceptual question. What is the current at the end of a piece of wire? It can only be one thing.
0.
0. It has to be 0, because once the current gets here, you have nowhere to go. It can't go off the end. So if I were to draw a current, a look of what the current looks like, it would have to be 0 at both ends. Well, if my wave looks like this, right? If my wave looks like that, show me if this is a half wave long and this is a half wave long, I can pick either of these sections and draw that on my antenna, right? So I will. All right. So does that violate anything yet? It does not. Perfect. Okay, so that is my current distribution on my antenna. Now, if I were to shorten the antenna, what I would have is that my current peak wouldn't get as high, because I still have to have something that looks like that. It still has to be 0 at both ends. So it would actually have to come up and drop off somewhere. Now, what if it was longer? That would also work, but then my antenna would look like this. I still have to have 0 at both ends, right? You can't get away from physics. You still have to have 0 at both ends. And my current curve would go like this, and then it would start to dip down, because that's what the path looks like. And this one would have to do the same thing. So my current curve would look like that. This is longer than a half wave. So a half wave dipole is really one of your best options. It's almost a perfect solution given to us by nature. Now, as far as feeding it, let me ask this question. If I look at this antenna and I'm actually going to draw the voltage profile, I can have a high voltage at the end. We're going to have a minimum voltage in the center. It's not going to be zero necessarily, but it's going to be something low compared to the ends. Okay, so now let's take a look at this right here. This is my voltage, and this is my current in those colors. What is my formula for resistance, everybody?
R is equal to V over I.
E equals I times R. So R
E over
equals
I.
E divided by I. Okay, so now we're not going to do this numerically. We're going to look at this empirically. Is my voltage E going to be small or big in the center?
Small.
It's going to be small. And how about the current?
Big.
Big. Okay, so something that's small divided by something that's big is?
Very small.
It's small, right? We're going to have a low impedance. And actually, I'm going to take this R and I'm going to replace it with a Z. That's my, because that's my impedance. Okay, so now we were talking about an end-fed antenna, right? So I'm not going to feed it exactly at the end. I'm going to feed it right here, pretty close to the end. All right, so at this point, what do I have? Is my E big or small?
Big.
Big, okay, so Z is equal to E divided by I. And my E is big. And how about my current?
Small.
That's small. All right, so empirically speaking, big divided by small is?
Very big.
Very big, okay. So what that means is by changing the feed point position, the antenna pattern looks exactly the same. What was my ideal impedance right here at the center of the dipole? How many ohms?
72.
72. How about here if I feed it all the way at the end? This might be 2000 ohms.
Infinity open.
Well, it won't be completely open, but it will be big. So it's typically you'll find it's about 2000 ohms.
Okay.
So what kind of feed line do you use to feed 50 to match 50 ohm cable to 2000 ohms? How do you do that? All right, who was asking about the end-fed antenna?
That was my question too.
That was you, Bob? Okay. So how do you match 50 ohms to 2000 ohms?
No, you don't.
Sure you do.
Okay, so you're going.
You use a matching transformer. And that's why when you buy or build an end-fed antenna, you have to build typically something like let's see, it's got to be a 49:1. So you have a 7:1 turns ratio, because that gives you 49:1 impedance match. And that will take 50 ohms up to about 2000, a little below 2000.
What's the N for in-fed?
Literally feeding it at the end.
Oh, end. Okay.
End fed, as opposed
So
to
not in the
center
middle.
fed. Right, as opposed to center fed. It's really convenient because it's really easy to mount, but it's not so easy to feed. And they're very popular because they're really portable. Very easy to string one end up in a tree as opposed to both. Okay.
Scott, Scott, is a vertical end fed same?
A vertical is a special case.
Okay.
So if let's say you have a half wave vertical, a half wave vertical is an end fed antenna. That has a very challenging feed point because your feed point impedance is, 1000 ohms.
Oh, it's that high.
Right, because it's a half wave. I mean, this is now if it was a quarter wave antenna, it would basically be about 37 ohms, which is much easier to feed, but it's not going to have as good of a radiation pattern. But you might be okay with that. A half wave antenna is really, really useful if you're using it on like a boat where the whole thing is fiberglass. Or if you have a car with, fiberglass or plastic parts, you might consider going to a half wave antenna, a half wave vertical.
Are you going to talk about balance?
I don't actually talk about balance. I can answer questions about balance, but
Their purpose?
To force equal current on two legs of an antenna. So you have basically a transformer up here, usually 1-to-1 turns ratio, where you basically feed power into one side and it forces the other legs. It forces the currents out here to be equal, even if the antenna is not completely symmetric. Because a coaxial cable is unbalanced and a dipole is balanced. It's symmetric. But a coaxial cable, just by virtue of the way it's built, looks like this. Right? It's got a center conductor and it's got the outside conductor. That's not symmetric. So, it's possible for them to not carry the same current. So if you want to force your antenna pieces to carry the same current, you would basically push them through a balun, which is a balanced to unbalanced transformer. And that would force them to carry the same current. And since they carry the same current, then your pattern looks perfect, as opposed to imperfect.
Okay, thank you.
All right, let's build an antenna. Okay, we have a 6-meter antenna. Somebody look at the frequency chart and tell me what the frequency is for the 6-meter band. We're doing real world stuff here. Give me a frequency to work for.
50 megahertz.
50 megs, perfect. We're going for the low end of the band. Okay, 50 megs. So somebody tell me what the formula is to calculate the wavelength.
Lambda is equal to F over 300 over F.
Yep, so we'll do our circle again, 300 F lambda.
Over 50.
Right, and our frequency is now 50. This is the one we don't know. 300 divided by 50. Sorry, I drew that wrong. 6 meters. All right. Wow, what a shock. Look at that. It really is 6 meters. That's great, right? Okay, so now we need an antenna that's a quarter wavelength long. Oh, sorry, half wavelength. My bad. We're going to make a half wave antenna. Okay, what would a half wave be?
3 meters.
3 meters, okay. And we're going to convert that to inches. It's 39.36 inches per meter.
39.4. 39.36.
All right, how many inches are we talking? Who's got a calculator?
117.
Okay, 117 inches. Okay, well, what is the one thing that we haven't done yet?
You have to divide that by
5%.
We have to take away 5% because it's 5%.
Okay.
It's going to be 5% too
95%
long.
of it.
Right, so multiply by 0.95. What do we get?
112.
Okay, that's our 6 meter half wave antenna. It's 112 inches long. That's exactly right.
12 inches long.
But then you got to divide that by 2 for each side, right?
Each leg, yeah. So each leg would be 56 inches.
Right. Okay.
Yep. So if you were making a dipole, the overall length is 112. Each leg is 56. Okay, so let's say that you made this antenna and you put it on an antenna analyzer and you found that its resonant point was at 49 point. Hold on. Sorry. Okay, so an antenna analyzer is basically a sweep generator that generates a bunch of frequencies and measures the standing wave ratio or the impedance at all those frequencies, and you found that it was perfect. You found the dip that it was perfect, but it was at 49.6 megahertz. What does that mean? If your target was 50 megahertz, what does it mean if if you actually came up perfect at 49.6?
What's the question?
Oh, well, think about it.
It's a little too
What's
short.
the question again?
If your antenna came up as being perfect at 49.6 megahertz, and your target was 50 megahertz,
You got to make it a little longer.
you don't. Think about it. If you increase the frequency, what does that do to the wavelength?
Increase the frequency, the wavelength reduces.
That's right. So if the wavelength is too long, right? Because it's working here. If the frequency is too low, that means that the antenna is, if the frequency is too low, that means the antenna is too
Big.
Too big. That's right. And there's a really good rule of thumb. It is a lot easier to cut something off than to add it back. So what that means is that you made an antenna that's now 49.6 megahertz. It's resonant there. What should you do with it?
Snip from each side.
Take a 1/4 inch at a time. Snip, snip. And eventually you'll find that what'll happen is that you'll test it again and it'll look like that. Okay, well, we're not there yet. Well, let's do it again. Yeah, almost there. You'll take it again, and eventually it'll be, oh, well, we went a little too far, but that's okay. Right, we're a lot closer. So now we have a good antenna.
Got a question.
Yep.
So let's say we're using the 2 meter, we want to use the 2 meter band.
Yep.
And we wanted an antenna for it. Do we tune it for the middle of the band?
Depends what you want to do with it. Typically, I would.
Because I want to hit the whole band.
Right. Typically,
I'm
I
allowed
would.
to.
If I were, but let's say I was doing an antenna for 6 meters. Right. I would, because I tend to gravitate toward the weak signal stuff at the low end of the band. I would typically go and make it for like 50.3 or something. I would, it depends on what you want to do. Then you start looking at other bands. Here, let's bring up another one that is of particular interest. Oops, sorry. Let me get the right thing. There we go. Okay, let's look at the 80 meter band. Okay. What is the frequency at the bottom end of this band right here?
3.5.
3.5. How about at the top?
4.
All right. So let's do a little bit of math, shall we? Okay. 300 F and lambda, 300 F and lambda. All right. So in this particular end of the band, we know that our frequency is 3.5.
Which meter?
On the 80 meter band.
80 meter, 3.5.
And at the upper end, we're at 4.0. Okay. So
yeah,
somebody give me a calculation for the bottom end. 300 divided by 3.5.
85.7.
Good, 85.7.
Yes.
Okay, how about at the upper
Meter.
end? 300 divided by 4. I know that's 75 meters. Well, let's make a half wavelength antenna out of each one. That'd be 42.8 meters. And on this end, it's 37.5.
37.
How do you use the same antenna for both?
I have to take 5% off also, and then
Right. But let's
tuner.
let's say this comes down to 40 point. Let's say this one comes down to 40.6, and this one comes down to about 35.3, 35.6.
Find the average.
Yeah. Well,
No.
You could actually build one right in the center. But what's probably going to happen is that your peak is going to look like this at 3.75. And at 3.5, it's not going to be very good. And at 4.0, it's probably not going to be very good either. So what you'd end up doing is having to either build 2 of them, which nobody's going to do, or this is where you start to have to use an antenna tuner. Because you have a fairly poor match. You know, you have your peak where you're resonant at 3.75 like you designed, but you know, no antenna is going to have that wide of a bandwidth. So there are certain design constraints that you do have to take into account.
I read somewhere that when you do this kind of thing, you're supposed to be considerate of being too close to the edge of the band, something about overlapping into another band or something like that.
When you're transmitting, yeah.
Okay.
Yeah, I mean, that's to keep you from being illegal. But as far as designing antennas, that's just, you know, that's just putting it in the right place. All right, let's see. Approximate length of a quarter wave vertical antenna on 146 megahertz. So who was asking about making the antenna for their car or for just 2 meter use? I think that was that Lou?
Yes.
Okay, here we go, Lou. Do the math. 300 F and lambda. You're going to make yourself an antenna.
300.
And here's our 146.
Divided by 146. On new calc.
300 divided by 146. Get a what? About
It was 2.09.
Okay, 2.09.
Yep.
Sounds about right.
2 meter band.
Yep. Okay, so we know it's a 2 meter band because that was the pick. All right, so 2.09. Now we're going to take it's a quarter wave. What's a quarter of that?
Half meter.
0.522 meters roughly.
Mm-hmm.
Okay, and we're going to multiply by 39.36 inches per meter. Convert the units. What do we get? I don't have a calculator handy right now.
I'm doing it right now.
Okay.
This is a 9.8.
That doesn't sound right.
This is inches. And then you
Lou, how much do we get?
20.54.
That sounds about right. Okay, and now we have to multiply by 0.95. What do we get?
Hold on. Oh, that ain't right.
Getting close to.
19 and a half, roughly.
19 and a half
19.51.
inches. Okay, so 19 and a half inches. So what that means is we now have our quarter wave vertical, which is 19.5 inches tall. And our radials are going to be about a couple of percent longer. So these would be 20 inches, bent down at about a 30-degree angle. So, Lou, you see this antenna?
Mm-hmm.
It's been homemade, been on my roof for 5 years.
Nice.
What is this type called?
It's quarter wave
What
2
is
meter
this?
and quarter wave 2 meter vertical. Cost
So
me
you
a total.
have one big dipole and what the out of the other letters?
Cost me a total of $5 to make. It's been on my roof for 5 years. Cost me $1 a year.
Nice.
Okay.
That's my
Keep it longer, it will cost you cheaper.
That's my primary 2 meter antenna.
And when you make it out of?
I made it out of number 12.
Okay.
AWG solid.
Okay.
So it's just like THHN.
Mm-hmm. Yep.
Got it at Home Depot. Cost me almost nothing.
Could you make it out of copper?
It is copper.
Pipe? No, copper pipe?
You could, sure.
Okay.
I mean, but the tricky thing if you're making it out of copper pipe is feeding it. Like this right here, if you look at the connector, like
Right.
here's the connector and it has a square base on it with a hole,
Right.
a hole, a hole, and a hole.
Right.
This comes up to the center, 1, 2, 3, 4.
Oh, I see what you're saying. Okay.
And this just screws in, your cable just screws in down here and runs down to your
Right.
station.
And how did you wind up mounting it? with
Just PVC. I
PVC?
ran this up through PVC and used a lot of electrical tape.
Wow. Okay.
5 years, man, at least. And it's the best. It helps that I live up high, but it works great. Every time I go up on the roof and look at it, I'm like, I can't believe it's still working. But I put it up as a temporary antenna.
Why do you need the radials?
Hmm?
Why do you need the radials at 30 degrees?
Because what's the impedance of a quarter wave antenna over a ground plane? How many ohms?
72?
That's 37 ohms for a vertical. Right? By bending the radials downward, you increase the impedance.
Mm.
So you get a better match that way.
Got it.
So yeah,
Go ahead.
Go ahead.
Did you run the 12 gauge in PVC up at the
No.
top, or
No.
so it's just hanging straight up?
Yep.
Straight wires straight up. Okay.
Yep. That's
Cool.
it. Just a really simple antenna. And before that, when I lived in a townhouse, I just had one hanging in the attic. I formed the top of it into a little loop and just put a nail up on there. Just hung it from that.
And did you notice any difference between hanging in the attic and outside?
Worked great.
All right, cool.
Yeah, antennas are one of those areas where you don't have to spend a lot of money to get a lot of performance. Because it really comes down to, ingenuity, and how much does wire cost?
Do you do a class on figuring out your own antenna?
I don't, but we actually it's me and the two Garys here in our club. We do a class on antenna modeling using software.
Good.
Oh, cool.
Yeah. Using something called 4NEC 2, which is a free software package.
Oh yeah.
Okay, so here we go. The next one. So we just made a quarter wave antenna. Now we're going to take a look at this antenna right here. Can everybody see this?
Yes.
This little rubber duck on top of my radio. Okay, so this antenna, would you believe me if I said this is 19 inches long?
No.
Did you measure
No, absolutely not. Right? Okay, well, the reason that it is not 19 inches long is because it's actually built like this.
Spiral.
it? Yeah, coil.
Right?
Coiled up.
Okay, and this is known as loading. And the
Loading
reason that
coil.
you do loading is basically if you look at all of the wire that's coiled up in here, it's not shorted together, it's all separate. If you look at all the wire that's coiled up in here, the total electrical length is 19 inches. Hi, Nate. I'm teaching.
What is electrical length?
Electrical length, that's just the actual length of the wire
Yeah.
itself.
You uncoiled it.
Right, if I stretched it out, it would be 19 inches long. But its physical length is only 7 inches. Top to bottom.
Okay.
Okay. So basically, the reason that we do loading is to keep something electrically long while physically shortening it. So this can have some really, really useful things about it. Like, for instance, we can have an antenna that looks like this. This can be an 80 meter. Let me draw another one like that. Where we feed it right here. That's a terrible looking coil. Let's draw a real coil. There we go. So now that's an 80 meter antenna, which could be only, let's say, 50 feet long instead of 132 feet long.
Will it still work the same?
Well, that's a good question. What do you trade? What's the trade-off? So here's the trade-off. Ready? Okay, so if I were to take a full-size dipole antenna and I were to draw the current on this antenna, it's a full-size dipole. What does it look like? It goes up, it peaks in the middle, and goes down. It's essentially half of a sine wave. I get full current. Current is what makes RF fly out into the air. And
Propagate.
current is the thing that makes radio energy propagate into space. If I were to shorten this, and I did this with it, I put a coil here, and another one here, and then I cut this one off right here, and I made it so that I have 132 feet of wire. Okay, so what are the laws of physics that I am not allowed to violate?
Can't take away energy.
Right, and my current has to be what, where?
0 at the end.
Right, 0 at the ends. So basically, this little segment of antenna is this. This little segment of antenna is this. So I can draw my current distribution like this, but then what happens when I get to all of this stuff? It's all
Balloons?
bunched up. It's all bunched up, right?
Mhm.
So it doesn't really work very well.
Oh.
So what do I give up when I do that?
Propagation.
Peak power.
Efficiency.
Efficiency. My efficiency goes way, way down. Basically, my ability to radiate is much, much worse. So why would I do it on this antenna? Clearly, I have done it on this antenna. That's essentially what this thing is. Why would I do that?
Just to have access to
Portability.
that frequency.
That's right. And it might be so that I have a loss on this antenna of a gain of minus 4 dB compared to a dipole. Well, if I have a repeater and it's 10 miles away and it's line of sight, okay, that's okay. I don't care. You know, if I'm trying to get optimal performance, this is not the way to go. But it might be that it's good enough. It might also be that if I'm building this antenna and I have these loading coils in here, that it is good enough for me to get heard by the people I want to hear me. It might also be that I only have 50 feet of space to put it in instead of 132 feet, in which case something's better than nothing. So anyway, that's why antennas are so much fun to me, because you have to look at the space that you have and decide what will actually do what you want it to and how to make it optimized.
Yeah, the best you can.
Yep, make it the best you can, because even a bad antenna is better than no antenna.
Okay, so I've seen people take their my mic on. It is on. I've seen people take their antenna on their handheld and just like wrap it up into their backpack or into some other item that they're carrying, and it's all just coiled in and woven in. Does that affect the efficiency too, or is that something different?
Nope, that should be fine. Yeah, that should make no difference at all, unless there's something metal for it to interact with. So, I mean, RF doesn't really interact with anything that isn't metal, except for like, you know, anything conductive. And people, because we're mostly salt water, are actually, you know, conductive.
Non-conductive.
Yeah.
So don't touch your antenna when you're transmitting.
Ah, that's a good point. Okay, so here's another question. Let us say that I have this antenna, which is a quarter wave. All right, what does a quarter wave antenna need on the other side?
Another quarter wave.
Yeah, it needs a ground plane, right? Okay. Here's my hand. Here's a very ugly drawing of me. Okay. Where's the ground plane? I am the ground plane. That's right. It is capacitively coupled through the body of the radio to me. I am the ground plane. That's why a handheld radio in your hand works better than a handheld radio sitting on the tabletop.
Or sitting in a belt holder.
Exactly. Or sitting on your belt holder.
So if it's on your belt holder, can you just touch it with your hand to get a little bit better signal?
Yes, you can.
Nice little tricks.
Uh-huh. Okay, what's a beam antenna? This is a beam. A beam antenna is it's a Yagi. A Yagi is a kind of a beam.
Yeah, directional antenna.
Yeah. Okay, so a directional antenna, a Yagi antenna, it's known as a YAGI. It's a Yagi beam. A Yagi beam consists of a dipole right here, and then a reflector, and then driven elements, or sorry, directors. Okay, so basically the dipole is a half-wave dipole known as the driven element. The reflector is slightly longer and the directors are all shorter. And the way that this thing works is that the energy that is radiated by the dipole radiates forward and backward. The energy that goes in the backward direction is re-radiated toward the front. And the energy that's radiated toward the front is radiated in a stronger direction toward the front. So your overall radiation pattern looks like this.
Which makes it a directional antenna.
Which makes it a directional antenna. And if you were to try to measure the effectiveness compared to a dipole, what would this be known as?
Lobe, main lobe. Gain.
That would be your gain. And what would you measure it in?
Gain.
What units?
dB.
In decibels. What do you know? There it is again. Yep.
Yeah.
Okay, so a Yagi, a quad, and a dish. A quad antenna looks similar to this, but a little bit different. Basically, a quad looks like this.
A Yagi, a quad, and a dish walk into a bar. That's what I thought you were about to say.
Yeah. So this would be a quad, where you basically have a driven element, but it's a full size loop. And then you have a longer and a shorter.
Okay.
So it forms like a rectangle in space. I guess it would be a parallelepiped actually.
Is this horizontal or is this vertical?
It depends. The polarization depends where the feed point is.
Because that Yagi you drew, wasn't that more like of a vertical?
Well, no, it can be. Whoops. I mean, if I draw it like this, that's a horizontal Yagi. If I drew it like this, that would be vertical. If I mounted it on a tower like that, if I mounted it on a tower like this, it would be horizontal. The neat thing about a quad is that depending on where you put your feed point, that determines what the polarization is. So
Hex beam.
Hmm?
Hex beam.
What? Oh, a hex beam. Oh boy. Okay. A hex beam is a form of a 2-element Yagi. Essentially, or also known as a Moxon. It looks like this. Oops, that last leg was ugly. And then we're going to connect the dots like this. So a hex beam actually looks like this. And then the other element looks like this. So basically what you have is a hexagonal support structure, and you have a driven element right here. Oops. You have a driven element here, the W shape, and then this back shape is the reflector. And it's a really ingenious thing because basically the support structures themselves are typically bamboo or fiberglass, so very, very strong and very light. And the elements themselves are just wires. And by selecting the lengths of those wires, it actually has, a fair amount of gain. I want to say it's like 7 dB of gain.
And what's that called again?
That's called a hex beam.
Hex beam.
They cover various frequencies, right?
Well, and the reason they cover various frequencies is because once you've got that support structure, you can actually do this with it too. You can make a different size hexagon inside the first one. So now you've got the ability to do this and have a second one and an element that goes like this. And they can coexist on the same support structure. And you can actually put up to 5 or 6 different ones all mounted off the same support structure.
But you just have to transfer power from one to the other when you want to change your band.
Well, no, actually, not even. They're typically they're fed off of the exact same feed point. And because the bands you're using are not typically harmonically related, the only wire that accepts power that shows like a reasonable impedance that accepts the power is the one that you're feeding into it at any given time. It's a pretty cool design.
I just picked up one for $200
That's
with
a good deal.
with a 40-foot crank up tower.
Yeah, okay. I don't want to hear it. I'm jealous now.
I know, I'm ashamed.
All right, let's see. The gain of an antenna is the increase in signal strength in a specified direction compared to a reference antenna, which we kind of just covered. The disadvantage of a rubber duck antenna, this is known as a rubber duck. Doesn't transmit or receive as effectively because its efficiency is considerably lower. What's the problem with using a radio inside a metal car?
The vehicle.
Shielded, all signal will be shielded.
Yep, your signal is shielded inside the car. Now, if you put the antenna up toward the window, you stand a better chance. A 5/8 wave antenna compared to a quarter wave antenna, in addition to being a little bit longer, like actually a lot longer, it's going to have a considerably lower angle of radiation. And since most of the people we want to talk to from a car are on the ground, we don't need to aim our signal toward the sky. All right, so we're into feed lines and connectors. Okay, so I'm going to, let's see. Okay, feed line loss chart. Okay, there we go. I'm going to share this. Here we go. Okay, notice what this chart says. Coax loss chart, decibels per 100 feet. So if your cable is longer, your loss goes up. If the frequency goes up, your loss also goes up. So if you have a really long cable operating at UHF, your frequency, your loss might be really, really high, and it's measured in decibels. So what this really shows is, notice, let's pick 7 megahertz, and we want to compare like RG58, 1.2 dB of loss per 100 feet. But let's say we want to use the same antenna at 28 megahertz, same feed line. We have 2.4 dB of loss. In other words, just by changing the frequency, the same cable is twice as bad. We've lost twice as much power. Now, also notice that let's go to 7 megahertz at RG58. Right here, we're at 1.2 dB. Let's go to our RG213. Notice we're at half a decibel of loss per 100 feet. So by switching cable and essentially going to a higher quality cable, they're all 50 ohms. They have completely different numbers. So depending on what you're actually putting up and how you're doing it, that determines what you're going to use. So notice at 2400 megahertz, this LMR 400, you're going to lose 6.6 decibels per 100 feet. So if you have a 100-foot run and you put 100 watts in, you're going to get about 10 watts out, maybe 20. And that's the best case. And that's why people who put
25, close to 25. So 6 dB would be 4 times reduction in watts. So 100 watt will come out around 22 watt.
Yeah. So basically you lose 78 watts just by going through the cable. So what this really means is that if you're running at 2.4 gigahertz or 2400 megahertz, you're basically moved into something called hardline, which is not even coaxial cable at that point. It's coaxial feed line. And so instead of looking at something like that, now you're looking at something like this. Let's see. Here we go. Andrew Heliax. And notice that it
exactly.
Yeah, and if you do commercial installations at very high frequencies or at microwave frequencies, you're into this stuff. Very specialized cables, very specialized connectors. Maybe you're doing air core and you're feeding it with pressurized nitrogen to keep it dry. Oh, it's a lot of fun and very, very expensive. And it weighs a lot and it's a pain to work with. So, all right. So why is coaxial cable the most common feed line selected for amateur radio systems? Coaxial cable looks like this. So this is coaxial cable, where you have a shield on the outside and a center conductor on the inside. So if you're familiar with cable TV, that's the same stuff, right? Typically, what we'll use is a 50 ohm characteristic impedance cable, and that would be RG58, RG8X, RG213, and so on and so forth. Now, what makes cable 50 ohms, right? You would think that, okay, so RG58 is actually really small. RG213 is almost half an inch in diameter, but they're both 50 ohm cables. You can also get like 3-inch hardline, which is also 50 ohms. What makes it 50 ohms is the ratio of this diameter to this diameter of the center conductor and the type of material used to separate them. Basically, if they are proportional, your characteristic impedance will be exactly the same. If you have a cable that's instead 75 ohms, some measurement in here is going to be different. And if those same proportions are maintained, your whole thing, your impedance will be maintained. So if I were to go with, let's say, RG174, all right, I'm going to bring up a picture of RG174. Okay, so here is RG174. And I don't know if you can really tell, but its total diameter is 0.11 inches. Think about how small that is, right? 0.11 inches. That's teeny tiny stuff. Now, I can also pick RG213. Right, that's also 50 ohm cable with an outer diameter of 0.4 inches. So almost half an inch. So what do you think are the differences between the teeny tiny stuff and the really big stuff?
The amount of wattage.
The amount of power you can put through it. What else?
Loss.
Price.
Loss. Yeah, exactly. So it's two different things. It's the amount of loss that you have at given frequencies, as well as the amount of wattage you can put through it. Largely because of, no, the amount of wattage, amount of power you can put through it. So typically a bigger cable will be able to provide less loss and more power handling capability. If you have, if you're building something on the inside of a radio and you have 6 inches of space, maybe having that short, you know, that really short, tiny piece of cable is fine. You wouldn't want to run it 100 feet out to your antenna though. All right, why is coaxial cable the most common feed line used? Because it's completely sealed if you do it right, and it requires few special installation considerations. A lot of it is ultraviolet proof, so you can put it outside in the sun. Some of it is actually known as direct burial, which means you can dig a trench and put it in the ground and it'll survive just fine. Impedance, again, we're on page 36, by the way. Impedance is a measure of the opposition of AC current flow in a circuit. So resistance is DC, impedance is AC. The measure of impedance is ohms. Most coaxial cables are 50 ohms, which we use. And it turns out that they're 50 ohms because it optimizes power transfer as well as availability. As the frequency
But
of
a while ago, we said the 72 ohm was the standard in the industry.
Yeah,
Is that right?
72 ohm is standard in cable TV.
Cable TV industry.
Yeah.
Okay. Yeah, because in cellular antennas also 50 ohm is the standard.
Yeah.
So with radio, ham radio also 50 ohm is the
50
standard.
ohms. Yeah.
Correct.
Now, a lot of people do use 75 ohms just because there's so much surplus available.
But then you have to apply the tuner and the antenna tuner.
Well,
to
you're gonna do it. You're gonna do it anyway. So, okay. As the frequency of a signal goes up, what happens to the loss of cable?
Also goes
It
up.
also goes up. So
it also goes up. Yeah.
if your frequency increases, your loss gets worse.
Yeah.
As your cable length goes up, the loss gets worse.
Yeah.
The difference between RG8 and RG58, RG8 is big fat cable. RG8 is really skinny cable. So RG8 is going to have less loss.
Wait, say that again.
So RG8 is fat cable.
Okay.
RG58 is the stuff that you have on your in your car that you smash in the window. You know, when you close the door on it.
Yeah.
And it doesn't destroy it. But you could never get away with that with RG8.
Okay.
So RG8 is going to have a lot less loss, but you can't put it through your door because it's you know, it's almost 4/10 of an inch across. Okay, which type of feed line has the lowest loss at VHF and UHF? That would be something called air insulated hard line. Hard line is that stuff that I showed you, which is a pain in the neck to work with and weighs a ton, but it's also really, really good. It works very well if you can afford it and if you have a way to transport it and put it up. The most common failure mode for coaxial cable is moisture contamination. Basically, if you get water intrusion into your cable, it will corrode and then it won't be good anymore. And at some point, you're going to have to rip it out and replace it. And why is it important for cable to be resistant to ultraviolet light? Because if it's out in the sun and it's not resistant to ultraviolet light, the jacket will crack. As soon as the jacket cracks, what happens?
You're open for moisture problems.
You get water in. Exactly. So that's why your cable needs to be UV proof.
What are you going to notice if you've got water contamination? Lack of signal or
Your SWR would go a little crazy. Yeah. You know,
get more noise.
Lousy signal, could be noise. It could be any number of different things. A disadvantage of air core cable compared to foam and solid is that foam and solid are solid, you know, basically if you don't have to squirt anything into them like air. And if anyone's ever worked in a factory where they have compressed air, they have to have dryers on that air because compressed air will tend to carry water into your system. And again, what does water do to a cable?
Ruins it.
Ruins it.
Corrosion.
Exactly. Okay.
They wouldn't pump nitrogen in?
You can do nitrogen, but you have to have, you know, you have to have a nitrogen tank and you have to have somebody who's qualified to do it. But yeah, you can do nitrogen too. Which of the following is true of a PL259? Okay, I'm going to bring up a picture of a PL259. This is your standard connector in most pieces of radio gear. The reason that this is the most common is because they're really easy to work with. Has everyone seen one of these at some point?
Yes.
Yes.
Okay. So on the right is a PL259. That's the male. On the left is an SO239. Now, notice this says up above UHF male. Okay. Now, very important to note, UHF does not stand for UHF in this case.
Okay.
These are terrible for use at UHF frequencies. In this case, UHF stands for universal high frequency. And these were given the names before there was a lot of UHF radio. So this actually stands for universal high frequency, and these are good at HF frequencies and a little bit at VHF. If you want to go any higher than that, you would typically go to something called an N connector or a BNC.
BNC.
All right, so here's an N connector. We'll go to Fairview Microwave. All right, so those are N connectors. Notice they look very, very different. They've got rubber gaskets and they're well sealed, and there's actually a separate inner and outer shield on the left-hand side. And so these are known as N connectors. These are good up to several gigahertz in frequency.
And your antenna has to match the base of the antenna.
Your antenna has to match as well. So when you buy an antenna, if you're looking for a VHF, UHF antenna, and there's a specification as to whether or not you want a UHF connector or an N connector, it has to match your cable.
Is that saying that a 1 is 12 inches long to 9?
No, that's just the cable length. But this is a pre-molded cable.
Okay. Oh, okay.
Yeah, you can buy just plain old connectors. I just wanted a nice picture of the connector itself.
Okay.
Yeah, it's a very good connector. All right, why should all coaxial connectors exposed to the weather, even these, be sealed against weather intrusion and water intrusion? And that's because water makes feed lines bad. It increases feed line loss. All right, next, what can cause erratic changes in SWR readings? The most common thing is that something's loose. If you have a loose cable connector and it's making occasional contact, when it's good, it's good, and when it's bad, it's bad. And if you're transmitting into it, you'll see your standing wave ratio jump all over the place. So now the question is, what is standing wave ratio? All right. So we
touched that earlier a little bit.
Yep. Now we're going into it. Okay, standing wave ratio is a measure of how good of a match something has to something else. So it's a match of, it's always something to 1. So a standing wave ratio is basically a measure of how much power is going up into your antenna and how much energy is coming back from your antenna. Or if you have a piece of cable and there's a connector here and another connector here, power going out versus power coming back because of a mismatch right here. So essentially, standing wave ratio is a measure of how well or poorly matched something is to something else. Ideally, you want the exact same impedance. So if this is 50 ohms and this connector is 50 ohms and this cable is 50 ohms and you measure it, it should be 50 ohms. If you have a resistor that's 50 ohms, you would have a perfect match of 1-to-1 when you measured it. If you have something that isn't 50 ohms here, let's say this is 200 ohms, right here, you would actually have a 4-to-1 mismatch. And then this is what you do on the extra class exam. Depending on the electrical length of this cable and the electrical length of this cable, those can actually act as impedance transformers, which can be good or bad depending on how long they are. So, all right, in general, what is standing wave ratio? It's a measure of how well a load is matched to a transmission line. And a load is something that uses power. In this case, it's an antenna.
Yeah, antenna is a load.
Antenna is a load. A resistor is also a load.
Yeah.
Okay, a perfect match is 1-to-1. That is perfect. That is what we always shoot for. 4-to-1 is an impedance mismatch. So that's sort of our threshold. If we see 4-to-1, we have a pretty big problem.
What is an acceptable match?
I'd say 2-to-1 is okay, personally. 2-to-1 is okay. But I mean, but what's okay depends on what you're doing. If you're running a TV station, 1.2 isn't okay.
Is not okay.
Yeah, even 1.2 isn't okay because you'll get reflections.
Okay.
So yeah, it totally depends on your frame of reference. Why is it important to have low SWR when using coaxial cable feed line? because every time you have a spot of high SWR, your signals go up and down and up and down and lose power. It reduces your signal loss. And everybody, what happens to power that gets lost in your cable? What does it turn into?
Heat.
I've done my job today. Thank you. All right. What's the proper location for an external SWR meter? So I have my transmitter right here. I'm going to have my meter as close to the antenna as possible. Because I honestly, I kind of care what's happening up here, but what I really care about is right here. Okay, bye. What I really care about is what's happening right here, what my SWR is right there. So basically, my meter really needs to be as close to the transmitter as possible. Why do most solid state amateur transmitters reduce output power as SWR increases?
Protect itself.
Protect itself. That's right. They're protection circuits. Because if my transmitter's here and I have signal that goes up and it's been designed to run 100 watts and I'm generating 100 watts, maybe I'm generating 100 extra watts of heat in the transmitter. And then I have, let's say, 20 watts going out and 80 watts coming back. How much power am I actually dissipating in my transmitter? Well, it looks like 180.
180.
Right? Yeah. Okay. Well, what does that turn into?
Heat.
Heat. Okay. And what is the killer of electronics?
Heat.
Heat. Yeah. So heat kills transistors. So if I don't, if it doesn't fold back the power, I have a dead transmitter.
Yeah.
Okay, so why do most solid state amateur transmitters reduce output power? And that is to protect the output amplifier. What instrument other than a standing wave ratio meter could you use? Something called a directional watt meter. If I have power that's going this way and this way, here's my antenna again. I can put something right here that says, here's my forward power. And here's something that has reflected power. And I can plug this into the formula for standing wave ratio based on the numbers that I get out of here. That allows me to calculate my standing wave ratio.
What was that meter called again?
It's a directional watt meter. And you can actually build one. It's, let's see. Schematic.
So it's not just a calculation, it can be by a meter method.
Yeah. Here. There you go.
Wow.
There's a couple of diodes, some calibrating resistors here and there. And it's basically looking for power for voltage and current that are in phase going out and in phase coming back. And that allows you to determine how much power is going out and how much power is coming back. Any idea what this is here? This donut looking thing up top is?
Ferrite.
Solenoid.
That is a solenoid. Yeah, it's a ferrite. Any idea what it's used for?
It is used.
Transformers.
Is it like a fuse or?
Nope.
No.
Transformer.
So let's ask what exists
Impedance
around,
matching kind of a thing. It's like
what exists around every piece of wire that's carrying current?
magnetic field.
Magnetic field. All right. So
Yeah.
that ferrite is actually a donut of powdered iron. So essentially it constrains the magnetic field that's being generated by the wire, by the current carrying through the wire. And then on the bottom part of it, you notice that it looks like 3 loops of wire that go around the bottom of it.
Yeah.
Yeah.
That's actually coupling to it, using that magnetic field to generate a voltage and a current and sample it.
So does it absorb the energy?
No, it actually is. It actually, notice then it then passes that through a pair of diodes. Those do rectification and then allow them to compare the signal that's coming in versus the signal that's going out.
Went out. Man, look at the difference in the prices to the left.
Oh, yeah. Well,
2 units.
but you know, you look at what it is. This is actually known as a cross needle meter that I'll bring up. And what this thing does is it measures current in the forward and reflected direction simultaneously. And it has, notice those SWR curves in the background.
Yeah.
By seeing where the crossing is, that allows you to calculate what the SWR is.
Wow.
So this is a particularly useful thing. I have several of these. This is actually what I mainly use at my station. And
why would you need more than one?
I have 2 different antennas that I run. And then I have a couple of spares that I picked up over the years in case one decides to die. Just cause.
So it's something that you would keep hooked into your system.
Always.
Always. Okay.
Always. Especially if you use a single antenna for multiple different frequencies, because then you have to tune it repeatedly.
Yeah.
Okay, next. Which of the following instruments can be used to determine if an antenna is resonant at a given frequency? Okay.
SWR meter.
Well, an SWR meter, but let's say you wanted to be able to sweep it across a range of frequencies and you wanted to see where this dip was. So yes.
My question is, what does the sweeping antenna mean actually?
This
what do we
actually,
do in it?
So what this would do is, let's say this operates from 10 megahertz up to 20 megahertz. Now notice, what do we have in these frequency bands? These are not ham bands, right? There's a ham band right here, and there's another one here at 14, and another one at 18, and another one at 21. But those are not ham bands outside of those areas, right? If we look at your allocation chart, those are not ham bands. So what this thing does is it's about a 1 milliwatt transmitter that puts power out into the antenna, and is, because it's only a milliwatt, it's legal to do so. And it measures what the standing wave ratio and the impedance of the antenna are. And then it gives you a nice little plot. So here's like at 12, at 13, at 16, at 18, and it will say your peak is at 15.4 or something like that. And what's nice about that is that you not only know, okay, well, if I was transmitting here and I saw that my SWR was, let's say, 3-to-1, is the peak over there? Or is, okay, where is the peak? Does it look like this? Or does
Close
it
to
look
that.
like
No.
this? And I don't really know. The antenna analyzer gives me the ability to actually test it outside of the ranges that I would normally be able to use.
So at 15.4, what is this? What is special about this antenna?
Well, I don't know.
Resonant.
Yeah, this is where my resonance point is.
Resonance point. Okay.
Let's just say that I was building an antenna and I found it resonant at 15.4.
So that is the best suitable frequency for this antenna.
I certainly hope not. That just happens to be what it is. I certainly hope not, because I don't have the ability to transmit there. I can go up here, I can go here, and I can go down here. It looks pretty bad at all those frequencies, right?
This allows you to see where you're at so you can tune it.
Right. This allows you to see, oh, okay, well, it's way too long for the 20-meter band. It's way too long for the 20-meter band. I better tack 6 feet of wire on the end of it and see what happens. Or I can trim it down and say, oh, okay, this is my new 17-meter antenna. So that's why it's such a useful device. And
so then how would you have it? I'm assuming it couldn't be a dipole, but how would you have an antenna that can be used for multiple bands?
Okay.
Antenna tuner.
Well, yeah, I mean, basically you'd use an antenna tuner, or here's the other thing. Okay. So let's say that I had an antenna that was a 40-meter half wave. Okay. All right. So here's my current distribution. Everything looks great. Now, on 20 meters, if I keep the same physical length, which is 66 feet, on 20 meters, it's going to look like this. right? Okay, where am I feeding it? Where's my feed point? It's at the current minimum, right? So on 20 meters, no, that doesn't work. On 40 meters, yes, that works. All right, so now let's keep going. I could actually try this on a different band. I can try this on 15 meters, which looks like this. Well, that actually looks pretty okay to me. So on 15 meters, that's actually good because I'm feeding it at a maximum, same way as up here. Well, it turns out that 15 meters is 21 megahertz. 40 meters is 7 megahertz. What do you notice about those?
They're multiples.
And in particular, 20
3 to
meters,
1.
20 meters is 14 megahertz. That's also a multiple.
Mhm.
What do you notice about 7 versus 21?
It's a 3 to 1.
It's an
1 to
odd
3.
multiple.
Yeah.
That's right. And it also turns out that 50 megahertz, which is 6 meters, is pretty close to working too. That's actually the 7th harmonic. This is the 3rd harmonic. So odd harmonics actually will work. You can use the same antenna for multiple different bands.
Boy, this sounds like music theory to me.
I know, doesn't it? It kind of is. Okay, here's the other thing. Let's say that I pick an antenna that is not resonant anywhere. So I draw the current and it looks like this, and it never quite gets to the top on this band. Well, I draw another one and it looks like this. And on another band, the current looks like this. On another band, the current looks like this. Well, I can actually work with that. If I use a tuner, I can actually work with those. And that's how you would use an antenna for multiple different frequencies. And there's something actually called a G5RV, where you basically have feed line, which is 450 ohms. And then this is coax that goes down to your station. And this is 102 feet long. And it's roughly 3/8 of a wavelength long at its lowest frequency. And it doesn't work great on any band, but it works adequately on all of them. So it's the ultimate compromise antenna for people who don't want to put up 4 different antennas. Okay, next. The major function of an antenna tuner or coupler matches the antenna system impedance to the transceiver's output impedance. The purpose of a dummy load is a resistor in a box. And what is the point of a 50 ohm resistor in a box? If you hook that up to your transmitter, what's it going to do? Actually, I shouldn't draw it like that. I should draw it like this.
No signaling.
Yeah, but what's it going to do to the power?
Dissipate the power.
Yeah. So basically, it's a resistor in a in a box with a heat sink.
So you don't fry your radio.
So you don't fry your radio, and you also don't transmit the signal. So the idea being that it allows you to put signals out at full power without actually transmitting. The other nice thing about this is that because you can run full power, you don't have to really, and no signal gets put out for the most part. You can be a little less careful about where the signal goes. I've actually made a contact with somebody on a dummy load before. So I do know that a little bit of RF gets out. So, but the other thing is that this has to be a non-inductive. Why? Because a lot of very large resistors, so this maybe is like a 100-watt resistor. That's a lot of heat. Why is it important for this resistor to be non-inductive?
So it doesn't affect the rest of it.
All right. When you say the rest of it, I think you're on the right path. What did we say that an inductor does? It has impedance. 2 pi.
You want this to be
FL.
strictly resistive.
You want it to be strictly resistive. And what happens if you have an inductor with inductance? You
Yeah.
actually have
Yeah.
resistance and reactance. And it's not straight out here anymore. It's now up here. And if this is 50 ohms and this is 20 ohms, well, you have to use Pythagoras' theorem. And let's say this is 60 ohms
35.
now.
60.
And that's not 50 anymore.
No.
And if you change frequency, guess what happens? Now it's here.
Yeah.
because the frequency changes. So now maybe it's 80 ohms. Well, that's not a very good test instrument, is it?
No.
Okay, we are on to
Just a second. So
Yeah.
if in a toolbox, we could probably be looking at an SWR meter or directional meter,
Yep.
a watt meter, an antenna analyzer, and an antenna tuner.
well, the antenna tuner you're going to have in your station. I mean,
Yeah, it'll be
Oh.
in the system.
yeah,
Okay.
that's something that you'll have in your station. I mean, that's permanent.
So the other three are like just things in a toolbox.
Yeah.
Okay.
Okay, here we go. Amateur radio signals. We are on page 42. Modulation modes and signal bandwidth. Okay, so you're probably wondering why we spent time on inductors and capacitors, right? Okay, well, here's why. Now, I'm gonna get you guys used to something else. This is actually a frequency chart, and this is our amplitude chart. And we're gonna put a center frequency, FC. Right? That's our center frequency. And now we're going to look at something called FM, which is frequency modulation. And when we transmit using FM, our FM signal will basically fill up an entire space around a certain center frequency. It will go plus and it will go minus. It will go symmetrically both ways. And depending on how you're speaking, that will cause it to spread different distances from the center frequency. That's why it's called frequency modulation. We're actually changing the transmitted frequency. So when all is said and done, this fills up from between 10 and 15 kilohertz of space. So this is FM. It takes up about, and if you're wondering why it takes up between 10 and 15 kilohertz of space, the reason being that that is how we have actually decided to do the modulation. So that is most commonly used on VHF and UHF voice repeaters for talking to the space station, just general land communications. They're mostly FM. This is also used for something known as packet radio, which sounds basically like a bunch of squawking. And basically that's computer to computer digital communications. And let me see if I can remember where to find it on this thing. But anyway, I can't offhand. But basically packet radio is digital communications using FM. All right, so again, that takes up between 10 and 15 kilohertz of space, which is 10 and 15,000 hertz, which is also why we don't usually allow FM on the high frequency bands. It just takes up too much room. So now let's draw our FC again. We're going to do something called AM. So amplitude modulation. In amplitude modulation, we take a carrier signal, which in time looks like this. That's just a single carrier frequency. And we use somebody's voice to literally their voice envelope to modulate it. And then we trim it and it looks like what's inside here. So a bunch of ups and downs inside here. If we were to transmit that, that would now look like something called amplitude modulation. If you look on the airwaves, you'll see that. You'll also see that there's this thing called a carrier frequency. And then you have something that looks like this, which is an upper sideband. I'll make it smaller. and a lower sideband. And what's interesting about these is that the carrier frequency is just a reference point. It contains no information at all. As you speak louder, some of the energy that goes into the carrier gets sent into the upper and lower sidebands. Now, the weird thing about AM is that the upper and lower sidebands contain the exact same information. So here's the next question. This takes up about 6 kilohertz of space. So it's a little more efficient than FM. So now, if I were to ask this question, do you see anything, given that upper and lower sideband have the same information? Can you think of anything we can do to save bandwidth?
Get rid of one side.
Get rid of one, yeah, because why would we want to transmit the same thing twice? So now here's our carrier frequency. And how much information is in that carrier frequency? It's just a marker. None. It has no information at all. So what we do with single sideband is we say this one over here, for instance, that's the lower. We're not going to transmit it. And then we do transmit the upper. So here's the upper sideband. We could choose to do upper or lower. And this only takes up 3 kilohertz because it starts here and ends here. So notice we're getting more and more efficient as we go. Well, I could get even more efficient than this. The next thing I'm going to draw. Go ahead.
What is the channel bandwidth for the audio signal?
3 kilohertz.
Okay.
Okay, so here's our next signal. Here's our center frequency. And we're going to draw something that takes up about that much space. And this is known as CW, or Morse code. This fills up about 150 hertz, which is why a lot of people who operate low power operate Morse code. Because if I have 5 watts, for instance, or if I have, let's say, 100 watts to fill up this space, 100 watts to dump into this bucket, or 100 watts to dump into this bucket, which one is going to give me a taller bucket? The Morse code is a much narrower bucket to fill up. I can fill it a lot higher than I can fill up a single sideband space, which is why people who operate very low power really like Morse code, because it's very, very efficient. All right, and finally, I'm going to get to one of the digital modes. Go ahead.
Sorry, I was just going to ask about your digital mode. Sorry, no.
Okay.
You did that at the same time I asked.
Okay, so here's our frequency center again. And we're going to do something called PSK 31. And PSK 31 is a digital mode that uses something called phase shift keying. And it's actually basically it'll transmit as quickly as you can type manually. And this fills up 31 hertz of bandwidth. Very, 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 very tiny. Almost no space at all. So really, the real world impacts of this is that you could fit 5 of those inside one Morse code signal. Inside a single sideband signal, you could fit 20 Morse code signals. You could fit 2 single sideband signals inside an AM signal, and you could fit 2.5 AM signals into an FM signal. And that's why we have all these different types of modulation, which are used in different places. Sometimes you have, a good enough conditions that you can use FM. You can spread your signal across that big of a band and still have a decent signal, but sometimes you can't. So if you're talking about weak signal work on VHF and UHF, typically you would not go to FM. FM is very much a bandwidth and power hog. So you would typically go to single sideband because it's much more efficient with your power. Above 50 megahertz, which are the frequencies that technicians are allowed to operate without question, full privileges, you have single sideband privileges in every one of those bands. If we look at the frequency spectrum chart, by convention, and I know this is gonna, there we go. The dividing line is at 30 meters. There's no voice allowed on 30 meters. Anything of a longer wavelength, 40 meters and down, as it's called, those typically use lower sideband. Everything 20 meters and up, so all of these bands use upper sideband, and that's just by convention.
Hey,
So,
Scott.
yeah.
Sorry, I don't mean to break your flow of thought, but just about the digital modes in general, speaking, using the web, like, how are you able to put voice over the internet? Or sorry, there's so many different modes. I'm just starting to research it in a little more depth. But how can you shrink? Like, does it shrink down the packet sizes to emulate your voice? Is that how it works? And just can you do a quick, a quick elevator speech synopsis on
Well,
that?
I mean, if it's like there is something called digital voice. Is that what you're referring to?
Well, I was actually looking at this digital mobile radio system.
Yeah, that's digital voice. Yeah, DMR is basically, if you think about analog, an analog signal takes up its full bandwidth all the time.
Right.
If DMR is a time multiplexed way of doing it, and essentially what it does is it just basically takes your voice and it creates a digital bit stream out of it.
Right.
And
takes it from analog to a digital format.
Right. And what you do then is you will essentially give up some of your, some of the quality of your signal in exchange for bandwidth. It's basically like, if people complain that a CD doesn't have the same sound as an analog signal. Well, that can certainly be true if your CD sampling rate goes down to the point where you can't regenerate everything. So you intentionally take a lower sampling rate and throw out some of your signal, and it's good enough for voice. And basically that bit rate is now low enough that you can actually have two signals sharing the same, the same frequency at opposite times.
And I guess the advantage of the net is you don't have to deal with RFIs and stuff like that.
No, you still have that.
Right? So
You still have that.
my head around it, all the advantages and disadvantages.
It's like if you're watching a digital cable channel, the signal's either good or it's blocking and you can't see anything.
So it's either black or white, really.
Yeah, it's either working or it's not. Whereas FM, you can be sort of halfway in between. Voice analog, you can be halfway in between, working and not working.
Head around is the amount of resources it's extracting from to produce that actual signal of voice. Like, what is it actually? What do you? I guess over the web, you have a cleaner.
It all depends on bit rate. I mean, it all depends on bit rate. I mean, if you look at, let's say that this is a voice signal, right? And you take samples and you say, okay, well, my maximum level is blah, 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 and I'm going to take a certain number of bits to take my sampling. All right, so this is 326, 342, 318, or 348, 292, and I basically just encode all of those levels.
So it really just goes back to a binary coding.
It is. And basically it sends them it encodes this and this and this into a bit stream. And on the other end, it reforms it. And the rate at which you sample determines how fast or how basically what you're able to reproduce.
Oh, that's cool.
By Shannon's sampling theorem, in order to regenerate a signal of F hertz, you have to sample at 2+ or 2F or higher hertz. And in reality, it's 2.2 times the frequency. So if I want to capture everything that's 3000 hertz or up to 3000 hertz, I have to sample 6,600 times a second. That's it. That's the whole thing. And then once you have a bit stream, you send that to somewhere and they can reassemble it.
You do Windows too?
Huh?
Do you clean Windows too? No.
Only my own, yeah, not very well.
Oh, you're a great teacher. Thanks. That really explains a lot in a nutshell for me.
Okay, and again, this is basically Shannon's sampling theorem. It's from information theory.
Nyquist sampling.
Thank you, the Nyquist rate.
Nyquist.
I haven't thought of that in a long time.
Yeah, it happens. Nyquist sampling, and then in order to convert it to the digital, you have to quantize it and convert it into samples,
right?
Based on 2 raised to the power n. Usually it is 8 bits per sample, and it ends up at 64 kilobit per second.
Right.
So that is
the other thing that happens there is that then you have to do anti-aliasing as well.
Yes, anti-aliasing.
Aliasing is basically that something that is of a higher frequency than you expect can appear as a lower frequency. So, and it can be something that's an artifact that isn't really there, that you're creating. So
yeah, when your sampling rate is not exactly matched to the frequency 2.2 times,
right,
then you get some shadow frequencies which are not really there, and you sometimes get some minus frequencies, and you wonder where it's coming from.
Yeah, exactly.
Why some people's voices are much more clear than others.
I think that's a big part of it. Yeah, I mean, when things are digitized, a lot of it depends on what the sampling rate was.
Yeah.
So, okay. Let's see. A form of amplitude modulation would be single sideband. Single sideband is like half of an AM signal. For weak signal work, again, single sideband. An advantage of single sideband for over FM is that single sideband signals have a much narrower bandwidth. You can put more of them in. You can have a higher power spectral density in a single sideband signal. A single sideband signal, I'm going to share this. This is very important stuff. All right, a single sideband signal is about 3 kilohertz wide, like we drew. A VHF repeater FM phone signal is between 10 and 15 kilohertz. Takes up a lot of space. All right, we actually still do NTSC television. That's analog fast scan TV. We're still allowed to do that. All right, notice this says it takes up about 6 megahertz. All right, so think about 6 megahertz. If you look at the HF frequency band, what is our total bandwidth between 3 and 30 megahertz? How many bandwidth? Or how many megahertz? 27. Right? A single TV signal takes up 6. That's why we don't use those bands for that. That's why television was sometimes in VHF and there were a lot more channels in UHF.
Yes.
All right. And again, that fast scan TV is known as NTSC. We also do something called slow scan television, which is like, I want to say 2 frames per minute, essentially sending pictures. Morse code signals have a very, very narrow bandwidth. Morse code, another name for it is CW, or continuous wave, because we basically just take a continuous wave and turn it on and off. In order to transmit a Morse code signal, we need about 150 hertz. And we use something because, believe it or not, you do have Morse code privileges. So any band that you're allowed to transmit on, you're allowed to transmit Morse code on.
But you cannot do the voice communication using Morse code, can you?
You can't do what?
The audio communication.
Well, depending on when you say audio communication, I mean, sure you can. I mean, if you're doing Morse code.
I mean, can I talk to Morse code like that?
Yeah. I mean, you can have a Morse code conversation if you know Morse code with somebody.
Do you have to break in verbally?
No, you're not allowed to do that.
Yeah, that's my question.
Yeah, no. But you're allowed to operate on those bands where Morse code is allowed, using Morse code.
Yeah.
If you have privileges. And you actually have privileges on, as a technician, you have privileges on 80, 40, 15, and 10 meters Morse code. Let's see, an electronic keyer is a device that sends Morse code electronically by taking a lever and going back and forth, and it automatically creates dits and daws. Okay. We are on to digital modes. So ones and zeros. What makes ones and zeros? Okay, so what is a digital communications mode? It's a mode that sends ones and zeros. IEEE 802.11 is also known as Wi-Fi. JT65. JT65 is a digital mode that was invented by Joe Taylor, who is a ham radio operator and a Nobel Prize winning physicist. And packet radio, that's basically digital communications over a handheld FM radio. Packet transmissions. A packet transmission contains a checksum. A checksum basically is, let's say that I was to send a series of ones and zeros, and I said, okay, well, I went 100110. Okay, count them. 1, 1, that was 3. All right, and at the end, you received something and it said that there were 4 ones. Well, the 4 does not match the fact that I sent 3, does it?
No.
So that would be a bad checksum, and that would basically be a rejected packet saying, okay, well, this is no good. If I were to use more bits to do that, you could actually figure out which bit was wrong and figure it out on your own. So that's known as a checksum permitting error detection. There's also a header. Header contains information about where the packet is going, who it's actually going to, and automatic repeat request in case of error. So basically, in exchange, I sent you that packet. You said, I didn't get it. Your return packet would say, automatic return request, please repeat. I didn't get it. So an ARQ system, ARQ is automatic repeat request. So again, detecting an error and sending an automatic message saying, I didn't get it, please send it again. A lot of people get into something called APRS, which is the Automated Packet Reporting System. Essentially, it's a combination of maps, global positioning system, and ham radio that allows you to put tactical information and other cool stuff on a map. For instance, a weather station, or you're driving a car and your radio is connected to a GPS, and the GPS says, here's your altitude, here's your speed, here's your position. We also use this for balloon launches. So we'll take a high altitude balloon and we'll put a little transmitter on it with a GPS. It'll fly up to 28,000 feet and circle around the United States for 2 weeks. Or maybe if we're lucky, it'll go overseas and end up in Europe. And that allows us to map it on a map. The APRS system allows you to provide real-time tactical digital information in conjunction with a map. How does it do so? Basically, it has to have GPS built into it. So it's a practical application of GPS and ham radio. PSK is phase shift keying. So instead of just turning something on and off, I can demonstrate that by going like this. Can everybody kind of hear that?
Mm-hmm.
Okay, that would be Morse code. That would just be on-off keying. Something is being turned on and off. Phase shift keying gets down into the nuts and bolts of what's being sent and actually looks at what's being sent, and if something was in phase, when I say phase, I mean something like this. When it changes, it does a phase shift. It says, okay, well, we were on the way down. Now we're going to shift by 180 degrees. Here's our signal. So now we're going to go up to here. So this right here, where it changed, would be the indication that something changed. And that would be a 1 or a 0 being sent across the, being sent digitally. Okay, so that's phase shift keying, where you actually alter the phase of what's being sent. Okay, digital mobile radio. Who mentioned DMR? We were talking about DMR. So digital mobile radio is a form of like digital voice over radio. It's sort of like voice over internet protocol, which is a system that basically allows two different signals to send FM data, which is voice, over a single channel. Essentially, each of them gets half of the time. So the nice thing about it is that each of them gets half the time. And if you set it up correctly and your radio is synchronized correctly, you never even hear the existence of the other station that's using it. What that means is that two different stations can use the exact same resource at the same time.
Going to different locations?
They could be going anywhere.
Okay.
They could be coming out of the same repeater. So two digital voice signals at the same time on the same channel. A talk group. Okay, so you could also have, let's say, 8 different people using a single half of a repeater channel by basically getting into a talk group. The other thing is that if your radio is connected to the internet or the repeater is connected to the internet, the people who are participating in that talk group don't even have to be local to you. They could just be connected to another repeater that's on the internet as well. And basically the internet then handles all the traffic between the 2 points. Okay, so how do you join a talk group? You program your radio with the group ID or code. That basically synchronizes you with all of their signals. Okay, which of the following operating activities is supported by digital mode software in the WSJT suite? Again, that's WSJTX. It has FT8. It has the JT modes. It's the thing that was created by Joe Taylor, the physicist, the Nobel Prize physicist, who was a really big fan of moon bounce. Did I mention he was a radio astronomer as well? So anyway, moon bounce is his thing. Weak signal propagation and meteor scatter are all supported by that WSJT. Another one of them we use terrestrially is known as FT8, which is a really, really, really slow, really good weak signal mode that allows people to transmit at 15-second intervals and communicate back and forth. And when I say really slow, it allows you to send a 13-character message every 15 seconds. Really slow. Finally, something called broadband hamnet. So this is actually really big out here on the West Coast now in Oregon. And essentially what this allows you to do is take commercial Wi-Fi gear, such as Ubiquiti routers, dump a different firmware into it, and it becomes a ham radio on a self-healing network that allows you to basically send information from one point to another. And it's at extremely high speed, which is really cool because then people are able to do cool things like, they want to see if they can actually run a Minecraft server. This is something that our club actually did. They ran a Minecraft server over the radio. It was actually fast enough to do it. All right, so we're going to do this. This is the last section today. Safety, safety, safety. Does anybody want a 5-minute break or does anyone have to go?
Are you stopping at 1 or story? Are you stopping at what is it, 4 your time?
Yeah, it's 4, but it's like 1 minute to 4, and we basically just have safety to go through now.
Oh, no.
7 out here.
Yeah.
Yeah.
Right.
Scott, if you want to take a couple minutes and come right back.
I don't need to. If you guys are good, I'm ready to just go through it.
How long is it going to be, you think?
10 minutes.
All right, let's buzz through it. Okay,
here we go. What health hazard is presented by electrical current flowing through the body that can cause heating of body tissue, electrical function of cells can be disrupted, or involuntary muscle contractions, like when I accidentally touched 250 volts DC as a kid, and I found that my arm ended up way up here. I didn't know how it got there. So you're all lucky that I'm here today, because maybe that might not have happened if I was in a slightly different position. In the United States and probably Canada as well, the green wire in an electrical plug is ground. It's equipment ground. In order to stay safe, use 3-wire cords and plugs for all AC powered equipment. Connect all AC powered station equipment to a common safety ground and use a circuit protected by a ground fault interrupter. That's that thing with the test and reset button that you'll find in your bathroom that often trips if you drop your hairdryer into the sink. What's the purpose of a fuse? We covered this morning. That was actually still this morning. Hard to believe, right? That's to interrupt power in case of an overload of current. So why should you never install a different fuse other than the one the manufacturer specifies? Yeah, you can start a fire. So if you ever thought that it was a good idea to put a penny in the fuse box, if you have one of those old fuse boxes, don't do it. If you build your own piece of equipment, you should always put a fuse or circuit breaker in series with the AC hot conductor. In the United States, that is the black wire. The white wire is typically going to be your neutral. The green is always going to be ground. If you have a power supply and you turn it off and you start sticking your hand in there, why should you not do this?
Residual power.
Residual power in a capacitor. That's right. So what's the safety hazard of a 12-volt storage battery? This actually happened to a friend of mine once. He shorted out a 12-volt storage battery briefly. It was already a little discharged. There was a nice little cloud of hydrogen there, and the battery went kablooey and showered him with lead and sulfuric acid. Fortunately, he was okay. But those are dangers of a 12-volt storage battery. So if a lead acid storage battery is charged or discharged too quickly, you could overheat, give off flammable gas, or explode. All right, antenna and tower safety. All right, I have never put up a tower. I have no desire to go climbing towers anymore. I know a lot of people who do. There are professionals who do that. I'm going to leave it to them mostly, but it's still good to know, and it still could be on your. It's still going to be on your exam. Which of the following is an important safety precaution to observe when putting up an antenna tower? Look for and stay clear of overhead electrical wires, because every year there are a few hams who put up an antenna and end up getting electrocuted. Yeah. The minimum safe distance from a power line to allow when installing an antenna. Basically, if something comes down, it has to be at least 10 feet from any energized parts. Why should you avoid attaching an antenna to a utility pole? Who works for the utility?
Electric.
Who works for that utility again?
Yeah, all of these are all familiar to me here.
Uh-huh. You know, it's funny. You don't own the utility pole. It's not yours to go up.
Yeah.
And that, and the fact that I know for a fact that a lot of residential power lines carry 12,400 volts. And that will ruin your day. Why should you never touch an antenna that's transmitting? Okay, so there's something called an RF burn. It's like a regular burn, except that it's worse. Because what happens is that if you touch something that's carrying RF current, RF likes to travel on the outside of things, including your skin, except for the fact that once it gets to your skin, it'll then put a little tunnel inside it and tunnel into you and put a little hole in you. Very uncomfortable. That's known as an RF burn. When should members of a tower work team wear a hard hat and safety glasses? Basically, if there's anybody up on the tower doing any work, there's a fair chance that they're going to drop something. So hard hat and safety glasses. Personally, when I'm at work, I also wear steel-toed boots just to be safe. And also a reflective vest and lots of other stuff. A good precaution to observe before climbing an antenna tower. It used to be that you used to wear just an antenna climbing belt. Well, we don't do that anymore. There's something called a fall arrestor, which is basically a full harness and a spring. Yeah, it's a springy thing that goes on your back that clips to the tower, so that if you happen to fall off the tower, the fall arrestor will go boing and you'll bounce a few times, hopefully, before hitting the ground. So And you also need to wear safety glasses. It is never safe to climb a tower by yourself. Why is that, everybody?
Because you might need help.
Yeah, you might need help. And sometimes what else can happen?
Unconscious.
You could go unconscious. Yeah, actually, every so often somebody has a heart attack on a tower,
Wow.
right? Good luck getting them down. Good luck getting help. Somebody gets stung by a bunch of bees and passes out.
Yeah.
Yeah. So, okay. Never climb by yourself. When putting up a crank up tower, never climb it unless there are mechanical safety locking devices in it, or the tower is retracted and in a climbable state. It's not designed to carry your weight unless there are locking devices in it. And the worst thing that can happen is if you climb a retractable tower and it retracts with you on it. Let's see, safety wire. Why would you put a safety wire through a turnbuckle? If you live in an area that is subjected to any wind, and there's wind everywhere, what can happen is that the vibration can cause the turnbuckle to turn and loosen, and then your guy wires will be loose. A gin pole. What is the purpose of a gin pole? A gin pole is basically a little crane that allows you to mount a pulley up above your tower so that you can pull down on the rope to pull your stuff up instead of having to haul it up and potentially hurt yourself. When grounding, follow local electrical codes. NEC kind of governs everything. You might have local codes in your own neighborhood. For grounding a tower, you have an 8-foot long ground rod for each leg bonded to the tower and to each other.
Where do you get the local codes at?
Well, I mean, depending on where you live, you just be able to ask if there's like, state codes, county codes, city codes.
Do you go to your electrical company or do you look?
Honestly, you could probably go to an electrical supply house. They should know.
Okay.
Alternately, you can go to the county building offices.
You can go to the city office also.
Yeah. Depending on where you live, you may actually need to get permitting to put things up like a tower as well.
Yeah.
If you're in the country, probably not. If you live within city limits, there's a really good chance that you will. Proper grounding, we did that. Avoid sharp bends when connecting wires to grounding stuff because lightning doesn't like to go around corners. Lightning likes to take the shortest route possible. Make sure that all connections are short and direct when doing lightning connections. And all external ground rods and connections have to be bonded together with a heavy wire or conductive strap because you don't want it to melt. So the other thing about that is why you would do that is because why would you never solder anything like a ground rod?
Solder melts.
Solder melts. That's right. You want to weld it, or just use a mechanical clamp. But yeah, solder will melt. What precautions should be taken when installing devices for lightning protection? If you have a set of lightning protection lightning arresters, you want them all grounded to the exact same plate, and then those all tied to ground. And here we go with the very last section. Here we go, the very last section for today. Then everyone can take a big deep breath.
Scott, one more thing on
yes.
location for ordinances and everything.
Yeah.
If you're in a HOA, which is a homeowners association, in all probability, they don't like big antennas, but that would be a source to check and find out before you put it up and find out you got to take it down.
Well, what I found about HOAs, it's a lot easier to ask forgiveness than permission. So I've lived in many of them. Yes. But the other way to get by with an HOA is if you're on the board.
Yeah, there you go.
Like, go ahead. I'm the board. All right. What type of radiation? We're on page 53. What type of radiation are VHF and UHF radio signals? X-rays, ultraviolet, those are ionizing radiation. They will actually, X-rays in particular, can actually have enough energy to cause genetic damage. Radio waves do not. They can cause a little bit of heating, but they're non-ionizing and they won't basically rip your DNA apart.
What if you?
Go ahead.
Well, I was just gonna say that so no microwaves can have any effect to your DNA. Like,
Nope. Nope, they're all heating.
Really?
Oh, they can cook you, but you know, cooking you is different from genetic damage.
So they can't have any effect on the human body at all.
Well, they can cause heating. So, I mean, power exposure levels do. There's a variety of power levels depending on the band you're on.
Right. So, for example, 5G technology has no effect on the human body or anything to do with how the body reacts. Doesn't have no reaction to it at all.
It shouldn't.
And you're
that is nothing. The high frequency being used in 5G is very, very low power, and that's very short range. So it does not even have any impact, any significant impact on the human body.
okay. So even if you have any type of say a high metal content in your bloodstream or anything like that, it wouldn't have any effect.
I mean, basically, there's not enough energy in the photons to do anything. I mean, radio is, you know, it's electromagnetic radiation, but there's that wave particle duality. And, you know, a photon is a particle. And, you know, you look at the energy in a particular radio wave based on its frequency, and there's not enough energy in a radio wave or radio photon to do anything genetic. You know, other than cause heating. That's why a microwave oven works. So, I mean, I personally still don't like to transmit, you know, let's say I have a handheld radio. I don't like to hold it for long periods of time with the antenna right next to my head transmitting. You know, but that's largely because of heating of tissue. I just don't want to do it. Okay. What is the maximum power level that an amateur radio station may use at VHF before an RF exposure evaluation is required? That's 50 watts PEP. PEP is peak envelope power at the antenna. So if you have a 100-watt transmitter and you lose half your power or more on the way up to the antenna, you don't even have 50 watts at the antenna. You don't have to do it. However, it's a good idea to do it anyway. How do you do it? You can actually go around and walk around with a calibrated field strength meter. You can do computer modeling, which I don't know anyone who's ever done it. The other way to do it is FCC OET Bulletin 65. And there's actually a website out there at a site called HintLink by a guy who has a US license as well as a Bahamian license, or no, Bermuda license. And he basically has taken the FCC tables and turned it into a website. And it's really, really easy to use because, you know, the tables are not particularly easy to use. So it's a lot easier to just go to his website. Duty cycle, basically duty cycle is the percentage of time that you're transmitting. Why is duty cycle one of the factors used to determine safe radiation exposure levels? Basically, if you have a 50% duty cycle, that means when you're transmitting, you can transmit twice as much with twice as much power. So if you have a total on time for 6 minutes and you're transmitting for 3, you can transmit twice as much power during that 3 as you could for 6, because your duty cycle is only half. You're only transmitting half the time. Exposure limits vary with frequency because the human body absorbs more energy at different frequencies than others. The lowest value for maximum permissible limit is at 50 megahertz, which is the 6-meter band. And that was done experimentally, again, showing that there's basically more absorption at 6 meters than anywhere else. RF exposure of people near an amateur station. I come across this at our museum station. Basically, frequency and power level of the field, distance from the antenna to the person, and radiation pattern of an antenna. Essentially, you want, in this case, everyone to be safe. You don't want to put anybody at risk. So you run through the safety calculations and find out that, you know, you have a safety factor of 10 or something like that. So you know that even if something really bad happens to one of your pieces of equipment and it starts transmitting all the time, you're still going to be safe. Which of the following actions might occur, might an amateur take to prevent exposure to RF radiation in excess of limits? You can move your antennas further away. You could also transmit for a lower duty cycle. You could also turn your power down. All of those things would work. And finally, you should regularly evaluate your station for RF safety. Anytime you change a piece of equipment, that changes essentially how the equipment works. So let's say that you're transmitting with a 50-watt transmitter and you replace it with a 500-watt amplifier. Clearly, things are going to be a little bit different. However, if you went and took a 50-watt transmitter and replaced it with another 50-watt transmitter, you're probably going to be okay. So if anyone is curious, I have a link to this website, and this is a really, really helpful website, RF exposure calculator. So what this allows you to do, notice it mentions all the FCC stuff and things like that. Basically, what it allows you to do is punch in information. So let's say I'm transmitting with 100 watts, and notice the antenna gain in dBi. There's that decibels again, using a dipole. And distance to the area in meters, let's say we're 6 meters away and we're at 50 megahertz, and go. Okay, so here's my power density in milliwatts per square centimeter. And we're allowed to, in a controlled environment, which means I'm in control of everything that's happening, go up to a milliwatt. In an uncontrolled environment, we're allowed to go up to 0.21. So we have a safety factor of 2. So basically that means you don't even really have to tell people that there's anything happening. It's categorically safe. I mean, you can still, like at the museum, we actually ran this calculation and put a sign up right next to the station. So, and that's basically just to, you know, to make everybody comfortable with the fact that we've gone and done this. So I just put that in the chat too. All right, well, congratulations on finishing day 1, everybody.
Thank you very much, Scott.